We have a theory which is called quantum electrodynamics, which is our pride and joy. It's so successful and it's so wide in its application. And what I would like to tell you about is that theory, how it works, or how it looks like it works, and what the world looks like from that point of view. The physics has got a history, at least its theoretical history, of synthesis perpetually. Of course, experiment is always finding new phenomena. The problem is to work them together, and sometimes we see that they're different aspects of the same phenomenon. An example is, of course, the simplest and earliest one is that the laws of motion became, in the theory, explained the properties of heat, because heat was motion, and if you knew how motion worked, you could understand the thermal properties. It also explained the properties of sound, which is otherwise a mystery, as the motion of the atoms and waves in the gas. Aside from that, knowing the laws of motion, you had to know Newton, who gave us the laws, worked out the laws of motion, also gave us another theory about the forces between large masses and distances from one another called the theory of gravity. Well, that's just that thing, the theory of gravity, is well known and understood pretty well, but is not what I'm going to talk about. As the time went on, phenomena associated with electricity, rubbing combs in your hair and things like that, and magnetism became interesting to the experimental physicists, and they discovered relations between them experimentally until they saw, ultimately, there were not two different phenomena, but different aspects of the same thing. Another phenomenon that Newton had studied was light. So without time, it looked at first like there were many things: motion and gravity, electricity and magnetism, later, and light. But when Maxwell put together the laws of electricity and magnetism, he found out that the behavior, that the equations that he had produced expectation that would be behavior of waves that would propagate at a speed which was figured out from electrical measurements, but came out the same as the speed that light actually propagated. And so there was a new theory of light, which is that it was an electromagnetic wave, and Maxwell's great synthesis in 1873 was to connect electricity, magnetism, and light. Light is just one aspect of the electromagnetic wave, which can have different kinds of wavelengths from that point of view. And if you have different wavelengths, if the wavelength is very short, between about 400 millionths of a meter, no, the centimeter, 400 millionths of a centimeter and 700 millionths of a centimeter, then you see it directly with the eye. But if it gets longer, the wave is, well, it's a long end, it's red, and then the other end, it's blue. And if it gets longer than the red, we call it infrared. The rays are there, but the eye doesn't see them. The pit viper has an eye that sees the infrared. And if you go in the other direction, to beyond the violet, then we can't see it again, but the bee has an eye that sees the ultraviolet. And if we go still further to the far ultraviolet, no animal has it that can see it, but we can make instruments that detect it, or photographic plates, and so on, up into X-rays and so forth. And down in the other direction, far infrared, you get into radio waves, and we can build instruments that detect them, and we can use them to advertise soap. In addition, so that is an enormous range of one property, the wavelength. A range of phenomena that's a complete, enormous spectrum. The spectrum we see with the eye is a very narrow range, and it's the entire spectrum. It's all put together with the one theory of electromagnetic waves. I'm going to talk about that part of it. I'm going to call it light, instead of saying electromagnetic radiation. Light is what we see, is only one little part, but from the physicist's point of view, the accident that the human eye happens to be sensitive to waves from here to here is not essential. The phenomena are the same over the whole range, and I'm going to call them all light, but it could be radio waves or X-rays or what have you. Next thing that was discovered was the structure of the atoms, and that, I'd like to remind you that you have, I believe, a Nobel Prize winner from New Zealand before, Mr. Rutherford, who was, I believe, a New Zealander, who worked out that the atoms had nuclei. You know, it seemed always here, I've only been here a few days, everybody's talking themselves down. I thought this would be a happy country, but something's happened to you. You've got plenty of room and not too many people, and it looks like it ought to be good. Anyway, you don't forget you had Rutherford, so it's okay. Anyhow, he had a theory of he developed our understanding of the atoms as having a tiny core, it's very heavy, with the particles going around it, electrons. Now, supposing that the electrons went around according to the laws of motion of Newton, some properties of matter could be understood, supposing the atoms were made that way. But most of the time it failed. And it became more and more of a crisis in physics to understand what matter was like, because it looked so obviously right that it had to be electrons going around nuclei, and yet nothing worked when you worked it out. And the discovery was made then in the discovery of quantum mechanics, first in the behavior of light and then in the behavior of matter, and finally culminating in 1926 with the full equations of quantum mechanics, which told us that the laws of motion of Newton were not right and had to be modified through other laws, which are quantum laws of motion. And when this quantum laws of motion were applied to electrons to explain the properties of matter, it was a fantastic success. The properties of the atoms can be all worked out mathematically, in principle at least, and the simple atoms in detail. And therefore, the theory behind chemistry, which atoms combine with which, at what rate, and so forth, is in principle. Theoretical chemistry deeply is physics. It's not a joke. The chemist will admit that's exactly his point of view, that the understanding of the atoms in the deepest level is physics, except that the atoms have so many particles in them, it's very hard to calculate what's going to happen, so he has to use a lot of empirical rules to help him. But as far as we can tell, there's nothing about chemistry that's not understood ultimately as the behavior of electrons following the laws of motion of quantum mechanics. This defines the properties of all substances also, and so that the whole theory of the properties of ordinary substances and the chemical properties and so forth have all been reduced to the motion of electrons. In the meantime, the theory of light and its interaction with matter, which was Maxwell's equations, had to be modified to become a quantum theory also. Oh, I forgot to mention that during this time, somewhat to one side of the way I want to go in these lectures, I'm not going to discuss much about relativity, but the theory of relativity was developed, and that just makes it easier for us to guess laws. It tells us if we know how something varies in space, then we know how it varies in time, or vice versa. That there's a nice relationship between the behavior in space and behavior in time, and that it's all sort of different aspects of the same geometrical thing called space-time. At any rate, Dirac, using the principles of relativity and the new quantum mechanics, found a wonderful theory, as simple as possible thing you could write down for the motion of electrons, Dirac's theory of electrons, and that was the situation about 1927 or 8. But the problem of the interaction of electrons with light, which was a complete quantum theory of electrodynamics, in other words, make Maxwell's equations of light, of electricity and magnetism, and the theory of motion of electrons, all into one grand theory, was accomplished in 1929 in the theory that was called quantum electrodynamics. Trouble with it was nobody could figure anything out, or better, when they did figure it out, they got nutty answers. If you didn't do it too carefully, you got a reasonably good answer for a problem, but if you carried it out very carefully, you would get some silly answer like 0 or infinity, or absolutely absurd results. This strikingly lasted for 20 years while people tried to figure out what the correct theory was. During this time, experimenters were measuring things more and more accurately. The theory of they found a few things with very subtle effects that the theory of interaction of light with electricity should explain. And then they measured them and they found these effects, but they couldn't explain, that is, the theory didn't explain it quantitatively, because when the people made the calculation, they got infinity instead of the right result. As an example, an electron in a magnetic field precesses at a certain rate, and the rate, according to Dirac, was a certain amount. But he didn't take into account the interaction of electricity and light. And when he took it into account, we knew that the answer should be wrong. Let's say that Dirac's answer was right, but when an experiment was made, it came out not to be 1, but to be a little bit more. This number here, the experimenters weren't good enough to tell us exactly. It's somewhere between 5 and 21 here. We write it as 8, plus or minus 3 as the next digit. That means this is not measured accurately. So by 1948, 20 years, we had at last measured something which showed that the original theory was without interaction is incomplete. This is supposed to be the result of interaction. When you went to calculate it, you got infinity. So there was a very strong effort made then in 1948 because of the fact that experiments were showing such accuracy to try finally to get that theory straightened out. And it turned out, surprisingly, it was worked out more or less independently by 3 guys who got Nobel Prizes, one of which you see here. And Professor Schwinger, that's not me, but one of the other ones, first worked out a correct way. We found out that the original theory that was written in 1929 by Heisenberg and Dirac and Pauli was very nearly correct. And the problem was that there was something wrong with the way they handled doing the calculations, and we straightened it out. And then we could do calculations, and Schwinger, for example, calculated this and found out that it was something like this, theoretically. And that was a tremendous achievement. It's a great excitement, because that meant we really understood more subtle details, and that the original theory of Heisenberg and Dirac and so on was fundamentally right, just a little switch on how you calculated things. Now this is the theory, then, that we're going to talk about. This theory has lasted now for 50 years. 30 years. I can't add. From 1979, 1949. Oh, it's 50 years, yes, from the time that Dirac and Heisenberg wrote it, and it took 20 years to figure out how to calculate with it. Then the remaining 30 years, the methods of calculations improved. They calculated things much more accurately, and the experimenters became more and more adept at measuring things. And this particular rate that they measured in 1948 to here, now in 1979, has been measured to be, in fact, 100.11596524, and the 4 may not be 4. It could be somewhere between 2 and 6. After all, the more you write it, somewhere you have to stop, right? And this, I write to show you the tremendous achievement of experimenters during the last 30 years in order to test with the precision the correctness of the theory. In the meantime, poor guys using calculators and sweating and writing marks on pieces of paper, so on, calculating the results of the theory under the same circumstances for the same phenomena, produced a predicted value that it should be 6523 within plus or minus 3. Why should the theories have a plus or minus? Well, they get exhausted in computing the number of decimal places that they need to keep up with experimenters. This is not atypical. There are 2 or 3 or 4, perhaps, different places where it's been measured and checked to that degree of accuracy. This degree of accuracy, that number of decimal places, corresponds to a precision something like this. If you were measuring the distance of me to the moon, the question would come up, do you mean from my chin or from the top of my head? The difference between whether it's from the chin or the top of my head to the moon is the plus and minus 2 on the end of that number in proportion, all right? That is to intimidate you that the theory is correct in high accuracy. I don't need to produce a large number of other experimental results. They all have this feature. It is remarkable that at this time it is possible to say that there's no experimental discrepancy known between the predictions of the theory anywhere and the results of experiment. That doesn't mean we can compute everything. The rules of the game by which we make the computation, the laws underneath everything that makes nature work, are simple. It doesn't mean we can really figure everything out. To give an example, if you play the game of checkers, I think you call it checkers here, maybe draughts, something. The rules of the game are very simple. The way the pieces move is simple. And if you want to make it even simpler, make the rule no kings, but when you come to the end of the board, you start at the beginning. It doesn't make any difference. The rules are simple. But imagine a checkerboard with 100 million piece squares on each side. Hundreds of millions of these checkers in different positions moving through the board, taking pieces and being taken from the other. Which way are they going to swirl? Which way is the game going to go? That takes a lot of thinking. difficulty of the rules that's involved, but the multiplicity of its action and interconnections. Matter, as you all know, is made out of atoms and all that stuff, is such a multitude of little particles that in ordinary circumstances, so much is happening that in spite of the fact that the rules are relatively simple, not quite as easy as the checker rules, but pretty easy, it still is very difficult in almost all circumstances to figure out what could happen exactly. Well, when we can't figure it out exactly, but can do a pretty good job of approximating, the phenomenon is in the range that we expect. When we have a situation that's sufficiently simple, a corner of the board where there's only a few pieces, then we can compute exactly what ought to happen, and when we do experiments in those circumstances, it fits exactly. And that's all we can say at the moment about this theory. This theory was originally designed in ideas of space and time and a geometrical framework. And the question is, how small a scale can we go down to? And during the time of this period of time, we not only tried to measure accuracy, but also tried to see how small a distance the theory would be correct at. And I can only tell you the distance is 10 to the minus 15 centimeters. That means 0.015 zeros before you get to 14 zeros, before you get to a first digit of distance in centimeters. That thing is that accurate. We know that the laws are that accurate. To put it another way, it used to be thought that atoms were small. That was a limit of measurement. But at the present time, with the new instruments and design during all this time, we've been able to make instruments that can test this theory down to distances that could be described this way. If the atom is made 100 kilometers on a side, then we're measuring with 1 centimeter accuracy inside. So the theory is right. The distances correspond to a centimeter when an atom is 100 kilometers. So altogether, I can only emphasize with delight and excitement the fact that so much of nature is so accurately describable by one theory. There's an enormous range of phenomena, all the things you ordinarily see. The best way to describe what the phenomena are: colors of things, the softness of materials, the weight of things, the way their temperature, when you change the temperature, how much heat it takes, and sounds, and all these phenomena. The only best way to describe is to describe the phenomena that are not included in this theory. And one of them is the accelerations produced by gravity. The force of gravity is in another theory, gravitational theory, or general relativity. Another range of phenomena have to do with exciting the interior of nuclei, nuclear physics, protons and neutrons, radioactivity, and nuclear phenomena. That excluded, all the rest of the phenomena of nature are contained in this one theory. Now you can see why it is that I feel a bit uncomfortable when someone asks to give a talk, please tell us the latest things, because then I'm talking about our problems that we have in trying to understand the insides of a proton. For example, for a proton, to tell you a contrast, our understanding of the outside of the atoms, the electrons and light that I'm going to talk about, the theory is our jewel and great achievement, to the things that people ordinarily have to talk about at these lectures. It's as follows. If you take the corresponding number for a proton, I don't remember it. It starts at 273, I think 19, I'm not sure, or is it 2719? I don't remember. And it goes on for a number of decimal places because the experimenter can measure it so well. Now we have a theory of the protons recently developed involving quarks and so on. We can't make any calculations yet. We haven't developed the technique good enough. So the best I could say, really, and probably exaggerating, is that the theory does say that this number should be around 3, and the error, and that's what I think it must be bigger. I can't prove that it's as small as it might be 0.3. That gives an idea of how sloppy our understanding of protons is compared to that joule precision that we understand electrons, all right? So that gives us some idea of why it is I feel so uncomfortable talking all the time about what we don't know much about, and nobody asks me about the stuff we do know everything about. So, therefore, I'm forcing upon you a lecture on the things that we think we know something about. Okay, so that's our job. Now the question is, what am I going to do? I'm going to tell you what the theory is. I'm going to tell you what it looks like, what we do to make the calculation, just what the thing is, because otherwise, how are you going to understand what world picture, in other words, this thing is. And it is a world picture because it describes all the phenomena, except for radioactivity and gravity, in the world. It's a lot of phenomena. It's possible even, it might explain and should explain, if everything is thoroughly understood, the laughter of the audience when you make a dumb remark. Now, if I'm going to explain this theory, the question is, are you going to understand it? Will you understand the theory? When I tell you first that the first time we really thoroughly explain it to our own physics students is when they're in the third year graduate physics, then you think the answer is going to be no. And that's correct. You will not understand. But this business about not understanding is a very serious one that we have between the scientists and an audience. And I want to work with you because I want to tell you something. The students do not understand it either. And that's because the professor doesn't understand. Which is not a joke, but very interesting, I think. And I would like to explain it. My task, really, to explain all this, is to convince you not to turn away because it appears incomprehensible. That's what it takes 4 years of us to do to the student, is to get him so he doesn't run away because it looks crazy. The thing that's exciting about this is that nature is strange as it can be, in this sense, that the rules that are going to be obeyed, that I'm going to tell you about, by which this stuff is analyzed, by which we understand nature, the rules of the checkers, yeah, are so screwy, you can't believe them. Nevertheless, if you follow out the consequences and see what they do, sure enough, all the ordinary phenomena that happen, you can understand. That's hard to do, because you have to know how to count big numbers and do lots of arithmetic and so forth to see how it is that these rules really explain common experience. That will be more difficult for you to understand. What is not difficult is this. Well, that's difficult enough, yes, because it's so strange, but it's no more difficult for you than for the students, and no less difficult. I know sometimes I hear people coming to my lecture to say, oh, I'm going to come to your lecture, although I know I'm not going to understand anything. It makes me feel bad. Or when they come up afterwards, they say, oh, I enjoyed your lecture. It was lots of fun, but I didn't understand anything you said. I really am trying to make myself clear. So I would like to discuss this with you. Will you please keep coming in spite of the fact that you don't understand it? Because I don't understand it either. And the fun of it is that it's so mysterious. Okay, that's the fun of it. So this business about understanding requires just a few words. And so I'm going to say something about the relationship, and I hope we get some of your cooperation. Sometimes you don't understand because, say, the languages, the fellow comes from America and he talks too fast. That's my fault, and I apologize. I hope it's all right. That's a kind of trivial difficulty, relatively. Next kind of not understanding is because you perhaps use new words. That's an accident that comes because I'm working technically and I use the words every day, and I forget that everybody doesn't know what they mean, and I have to be very careful. Again, my job. And then there's a kind of saying that you don't understand it, meaning I don't believe it, it's too crazy, it's the kind of thing I'm not going to accept it. The other part, well, this kind, I hope you'll come along with me. You'll have to accept it. Because it's the way nature works. If you want to know the way nature works, we looked at it carefully. Look at it, that's the way it looks. You don't like it? Go somewhere else. To another universe where the rules are simpler. Philosophically more pleasing, more psychologically easy. I can't help it, okay? If I'm going to tell you honestly what the world looks like to human beings who have struggled as hard as they can to understand it, I can only tell you what it looks like, and I cannot make it any simpler. I'm not going to do this. I'm not going to simplify it. I'm not going to fake it. I'm not going to tell you it's something like a ball bearing on a spring. It isn't. So I'm going to tell you what it really is like, and if you don't like it, that's too bad, okay? There's also the possibility that you don't understand because you get a bit confused and you're sure that you must have misinterpreted what I said or something like that, and you get turned off, and that's, of course, a difficulty. Let me assure you that most of the time you did interpret correctly what I said, because if it does, it's going to be so shocking the way nature actually works that you're not going to believe that either. I faked it. I'm not telling you the full story, that for the students I have another way of explaining it, or something like that. It is not true. I'm going to be honest, okay? So I'm going to ask you to try not to get turned off, and not to be afraid, relax, and enjoy it. Realize that nobody understands it. Well, what the hell were my students learning for 4 years if nobody understands it? I'm going to explain, and I'm going to explain by a kind of an example. I like to take the Mayan Indians. They had a writing system, and we know some of the things they wrote were astronomical things, and they had a scheme for predicting many things in the sky, eclipses and so on. And let's take the example of when Venus, which was important to them because it represented evil of some sort, was a morning star and when it was an evening star. So they could predict ahead of time whether this bad influence was going to be in the morning or in the evening. And so they discovered that if they waited, that this cycle of morning, evening, morning, evening, morning, evening, 5 of those occupied just exactly the same time as 8 times a certain period that was important to them, 365 days. It's not exactly a year, and they knew the difference, but they still counted in 365-day intervals, which they called a tune. So they said that 5 of these cycles is 8 tunes. Then they discovered, of course, very quickly that if they did this 5-cycle bit per 8 tunes 10 times, they were off by about 6 days. And so they had a rule for shifting, making corrections as they went along, and thus had a very good way to predict when Venus was coming up. Okay? Now let's look at this thing from a point of view. Suppose that the professors, the priests in those days, who wrote this stuff and taught their students these rules, were giving a lecture to try to explain what they did in order to make these wonderful predictions about Venus. Then, if the fellow was any good at exposition and really knew what he was doing, he would say, what we're doing is we're counting the days, just like you're putting nuts in a pot. And we keep on counting 365 nuts, and then another 365, and another 365, and another 365. The guy says, what a lot of work. And we get all finished, we say, that's 5 of these periods. Now they understood what he said. That's easy. They did not know a quick and tricky way to add 365 times 8. I'm sorry, I said 5 times, I meant 8 times. The students were learning in the meantime the laws of arithmetic, something which is to us now, because we have public and free general education, almost everybody has to struggle through and learn how to add numbers by a tricky scheme of writing them in place system and making carryings and so on, so that if you buy wine for $4.15 and your meal is $2.87 or vice versa, it costs $7.02. And the girl who does this, the waitress, just an ordinary person, in 2 minutes does that. How did she do it? What is she doing when she's adding $4.15 to $2.87? She's doing this, counting out 415 pennies, then counting out 287 more pennies, and telling you how many pennies you would have got if you counted them all from the beginning to the end. But it's highly educated and very trained to be able to do that with those large numbers quickly. This training is something, in spite of the fact that everybody's got it. It's something pretty good, because in the 14th century, mathematicians they were called who could do that. Almost everybody in our civilization can do that, but I took this example, you can understand what's involved. What the students are taught, you see, in our particular problems now about physics, there are many bigger numbers. The numbers are much bigger. It's hard to, the numbers are so enormous you can't count them directly. And so we've invented a fantastic array of tricks and gimmicks for putting together the numbers, adding, counting, checking, and so forth, without actually doing it, the way I could describe what we're trying to do. If I say, I draw this and I draw that and I draw this and I draw that and I see where the end point is, we don't actually sit down and draw 7,000 arrows and find out where the end point. We have a way of figuring out where it comes, just like we don't actually count 415 pennies and 287 pennies to find out that you owe me 702 pennies. We do it by another trick. These are the tricks of mathematics, and that's all. So that's the part I'm not going to worry about. We're not going to worry about that. So don't relax. You don't have to know mathematics. All you have to know is what it is. All it is tricky ways of doing something which would be laborious otherwise. So it's true that in the years we have developed enormous abilities in mathematics, and it takes a long time to train the students, and so therefore they're very highly educated in that. But if you ask them why, now we go back to the Mayans, we ask them why when you fill up a tub 8 times with 365 day markers, it comes out that the Venus is up 5 times. They don't know. They don't understand at all. The more accurately they can do it, the fact that they know that they have to change it by 6 days and so forth, adds nothing to their understanding of it. The student who has learned all this mathematics and is able to make these calculations, not only of Venus, of the Mars, the Sun, the eclipses and everything else, is a super priest. Doesn't know why any better. And if he would explain it's nothing but counting days, he would be reduced to the truth on the one hand, and to an honest statement that he doesn't understand it on the other hand, and could tell somebody all about it who doesn't know how to count all these numbers so trickily and so cleverly as this priest students knew. Okay. Now, probably, I don't know about philosophy of Mayas. We have very little information due to the efficiency of the Spanish conquistadores and, well, mostly their priests, who burned all the books. They had hundreds of thousands of books, and there's 3 left, and one of them has this Venus calculations in it. So that's how we know about that. And just imagine our civilization reduced to 3 books. The particular ones left by accident, which ones, see? So, anyway, I get off the subject. If I make this up now, what I'm saying now is just a story. Suppose now that the students would discuss, or people would discuss the possible meanings of this. Why? Then they would begin to think about, well, 8 times 365 is 2920. That's got 2 2's in it. Now, 2 is a lucky number, and it has 2 2's in it. And then the 9 represents the god of so-and-so, which is related to Venus, and so forth, and that would be a good argument. Then, but in another city, some other guys getting together will have a different kind of an argument about it. They say, look, now, the fact that there's a 20 at the end, if I subtracted that away first, I get 2,900, which is a especially good number from blah, 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 and so on. And they would have different theories. And then someone would come along and say, you know, it doesn't make any difference which one of these theories is right. We still have this fact to go along with. And that is our modern scientific point of view. In the earliest days of science, we got confused arguing philosophically what was a reasonable reason for nature abhorred a vacuum, or it seemed to be nice that gods were doing it. Different kinds of psychological reasons for thinking it probably is all right after you discovered what it was. These things were never useful for predicting what should happen next, and we soon learned not to make these arguments. It's useless. It doesn't add anything, and so we're not going to make my imaginary Mayan arguments about the various gods that make the numbers. And so I'm left, if I'm a modern scientist, with a description of the situation. All right? Now I prepared the audience. Used up all my time to prepare the audience. Doesn't make any difference. I will continue anyway, in spite of the fact I used up all the time, to describe the theory. And in describing it, I will first describe some part of it. The theory is the properties of light, electrons, and the interaction of light and electrons. It's all one theory. I've cut it into 3 parts that way. And the first thing I'm going to start with is the properties of light. Okay? I'm going to tell you some of the properties of light, and I hope, if I can do it, to get to the key point, and then we'll continue in the following lectures to elaborate on it. First, I don't go through the history of the theory of light. It had various things. The first and most important thing I would say is that Newton found out that what we see as white light is a mixture of otherwise purer stuff that's easy to understand. And if you understand how each of the parts works, you just put the mixture back together again. And then you separate the light in a prism, which is done automatically in Auckland very often, as far as I can tell, in rainbows. And the various colored, if you would separate light in a prism and take out the part that looked, say, yellow, then you couldn't separate that any further in another prism. It just stayed yellow. That's called monochromatic light, light of one color. So I'm going to discuss all my phenomena for a while with light of one color because it's simpler. The first thing, Newton believed that light was a corpuscular thing and turned out to have very strange properties from that point of view. And it was then explained that many of these strange properties was because, in fact, it was a wave, which was wrong. It turned out he was right. It was a particle. It is corpuscular. The reason that he said it was corpuscular was based on an incorrect guess as to the behavior of waves. And his argument was wrong, logically. But it turned out in the end that it was particles. Now, how I talk about how I know it's particles is this. If we make an instrument to detect light that's as sensitive as it can possibly be made, we make it more and more sensitive. In fact, this thing is called a photomultiplier. And that's not the only instrument. I just take one for an example. It doesn't make any difference how we do it. When we get to light that's sufficiently weak, an instrument to detect it hears clicks, pulses, as if it was rain falling on something. You get bang, 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 bang. When the light is bright, the rain goes bang, 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 bang. A lot of them. When the light is very dim, boom, 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 boom. Small. The particular boom, booms and the bang, bang, bangs and so forth are completely out of proportion. The actual rate is enormous, okay, and a little bit less when there's less light. It's very difficult to get it to a boom, boom, boom. It could so dark in here you wouldn't know what. But this device, to show you an example of how it works, just so you understand, what happens when we detect the weakest possible light is it works like this. There's a metal plate here made of cesium or something. When light shines on it, it knocks an electron out. Then you have another plate here with a voltage that attracts the electron, so the electron, so to speak, falls. It's attracted and speeds up and hits this plate. When it hits this plate, got about 100 volts of energy, it splatters. Other electrons get knocked out of the 2 or 3, 5, perhaps, on the average. Now, those are attracted to another plate. And they all go sailing down here with another 100 volts, 5 of them this time, and each one of those knocks out on the average 5 or 6 other electrons. Now I got 25, yeah. And that's attracted to another plate, and that hits those, and so on, and you have maybe 10 or a dozen plates. By the time you get out the other end, you got such a chunk of charge and electrons, so many of them, you multiply 5 times 5 times 5 times 5, you'll be a long time counting pins to discover how much that is. You get such a tremendous pulse that you can, the number of electrons high enough, you can go directly through circuits and so forth and turn on and off switches and do all kinds of things, make voltages to pin, make noises, do all these things. It's amplified. Now what happens when we have a device like this and we put it in the dark is it goes click, 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 click. Every once in a while, a light particle comes in, a photon. This is a particle in every sense. The experiments have all the right properties as follows. That if you have a very weak light, and you have 1 or 2, there's one of them every once in a while, if you put 2 cells out, and there's just a few of them coming, then it goes on one or the other. They don't go off together. They go off together, you got too many coming, and you can't resolve it. But if it's very weak, the particle is either here or there. And it comes in particles. I don't know how much I can emphasize this, especially to young students who have learned its waves. It is particles in every way whenever you can detect it. It's unfortunate for us that we can see the light. I mean, it's unfortunate for us. No, not quite, not quite. That if we were 10 times more sensitive to light, then in the dark, we would see that what we're seeing is little flashes, little tiny dips, dots of light. The nerve would go off, just like this photomultiplier, in spots. But the human eye is not quite that sensitive and takes 5 or 6 of these particles, photons, 5 or 6 photons to make one nerve fiber go off. So it isn't, so we cannot detect with the eye light quite low enough to notice the fact that it comes in the form of raindrops. All right? Got that? They're particles, right? And you can detect them with an instrument. You can count them, so and so many per second. Bright light, more per second. Dim light, less per second. Okay? Now we start to describe the properties of light a little further. Next property I want to talk about is reflection from a glass surface or a water surface. I believe everybody knows that you can see the sun or the moon, let's say, in the sea as it settles, of course. Reflections are a happy thing in art pictures. There's moonlight reflected from the water. You have a window. When you look through a window, there must be millions of examples. Right back there's one. You look at a window, you can see through it, but also some reflection. Now already there's a problem, because the light that's reflected is not as intense as the light that's shining. Some of the light goes through the window, say, or through the water down in. Only some of the light comes back. If the light is headed for water, for example, straight down, only about 2% reflects. What does that mean, only 2% reflects? That means that if we had a photon counter here, let's say, draw the experiment so you know what I'm talking about. It's hard to make a water surface that's vertical. Yes, so we'll make the water surface horizontal. And light's coming down, and some of it's reflected, and we put a counter here to see one of those photomultiplier things, and we count the count. And we know how much we should have got, and we find what. How can it be partly reflected? When, I forgot to say when I was talking about the particles, when you have light of a definite color, the energy that the first one knocks out is always the same. Each particle is the same strength. There's not half particles. It's a full photon. What you get is full photons, which only if the light is dimmer. What does that mean? There are fewer of them, right? Simple. So, of 100 that come down here, perhaps 4. Now, this way and 96 go through. What determines which 4? How does it, which one that's coming down of the 100 knows what to come back up? All right? So the situation is that the phenomena is probabilistic. It takes odds. It comes down here and has a 4% chance. 1 out of 25 trials. Huh? I think you know what odds are. If you have, for instance, a die, and you want to get a 1 and you roll it, well, it doesn't come out so often, but it comes out sometimes, 1 out of 6. And what that means, if you roll die 100 times, let's make it 600 times, a little easier. If you roll a die 600 times, you might get 105 1s, or maybe 92 1s, or something like that, right? You get about 100. And if the numbers were bigger, the accuracy in percentage is bigger, not accurate. So if you have 6 billion, no, not 6, because I got 125, 25 billion of these coming down, about 1 billion will come off. Okay? Now, let's see if the next feature is how can it be probabilistic? Suppose that I had a light so weak that I had only 1 photon coming every few minutes. Will this counter go off, or will the one down here go off? 1 out of 25 times this one goes off. Which time? What determines that? Possible theories. Nothing. Pure chance. The world is made of chance. That would mean that the physicists can't predict the future. It would mean that if you set up an experiment with exact conditions, you cannot predict what happens in the future, because you can't predict whether it's going to go up or going to go down. You just got 4% odds. Your whole beautiful structure of science is reduced to computing odds. Nature, instead of being definite, does everything by chance. Not so good. Other possibilities, there are little spots on here. And the photon has to hit a spot on the surface. And Newton had several things. You'll find out later when I give you more phenomena, how these various explanations, which way it's going to go, and why the spot one doesn't work. But I'll give an argument that Newton made about that. He said it can't be that, because, he said, you can polish glass. It's wonderful. I love to read these old guys. You know, they knew you could polish glass, but they had the intelligence to deduce from the fact that you can polish glass that there's no spots on it. Like, why? What's polishing? See, he polished it. He carved his own lenses. He ground his own lenses, so he knew what it was doing. He takes a coarse-grained, sand-like stuff, what do they call it, the polishing powder, the grinding powder, and that shapes it. But it cuts fairly obvious grooves. And you take a finer one with finer particles, and you cut the grooves of finer, and you make the fluids finer and finer and finer. And after they're fine enough, suddenly it's smooth, and the light comes right through. When it's coarse, it's bounced around. And so he concluded that light cannot see the grooves, that when I polish it, it's not that it's smooth, it's still bumpy, but on a small scale, whereas when I have the big grains, it's on a big scale. It can't be any different. When I polish with the small grains, it's just a small scale irregularity. But somehow light doesn't see anything on a small scale. Correct. All experiments have shown that this is absolutely not the right explanation. If it was, there'd be all kinds of ways of testing that. I told you we can measure down to 10 to the minus 15 centimeters and so forth, and that what would happen would be you'd be able to find some area to focus very carefully the light so that the reflection coefficient would be higher than 1 in 25 because you happen to be near a place where there was a spot. Can't do it. No matter what you do, it's 1 in 25. Other possibility, the light that's coming down here, the photons are doing, like footballs. And they spin. And depending upon whether they hit with the nose point or with the flat point, depends on whether they bounce back. In other words, something inside the photon is determining which way it goes. Again, no. Because if that were the case, the light that went through would be all of a certain kind of football. And if you try the reflection again, you'd expect a different number than 4% because of the fact that they're all lined up, and you can't line light up. You can't fiddle around up here by any kind of filtering that'll change that percentage. All the lights, photons, are identical if they're the same color, as in one color. They're all identical, and they behave with 4%. Are we therefore reduced to this horror that physics has got reduced not to these wonderful predictions, but to probabilities? Yes, we have. That's the situation today. In spite of the fact that philosophers have said it is a necessary requirement for science that setting up an experiment exactly similar will produce results exactly the same the second time. Not at all. 1 out of 25, it goes up, and sometimes it goes down. Unpredictable, completely by chance. All right, I really see you turning off. I can see you say you don't understand me. You can't understand that it could be chance. I don't like it. Tough. I don't like it either, but that's the way it is, okay? I don't understand it either. I don't understand it. It must be that nature knows whether it's going to go up or down. No, it does not be that nature knows. We are not to tell nature what she's got to be. That's what we found out. Every time we take a guess as how she's got to be and go and measure, she's clever. She's always got better imagination than we have, and she finds a cleverer way to do it than we have thought of. And in this particular case, the clever way to do it is by probability, by odds. And so the first aspect I have to tell you about then is that light works by probability. All right? By the way, just incidentally, the wave theory had no difficulty with this at all. Because what happened would be like the waves of something are coming down here, and they shake and they just keep going, but some of them bounce back. Something like a sandbar sometimes partially reflects the waves in the sea. So some of the energy went back. But the waves don't operate this thing. By the way, when you turn the light on, this might go off at any moment. You don't have to wait for a certain length of time. Of course, there's odds that it goes off at any instant, but it could accidentally go off the moment you open the slit. So it's not a question of waiting for the energy of the wave to pile up or anything. It's hopeless. I have to start with light as particles. Waves explain many things, but not right. It's particles, okay? Okay. It's photons. The problem is they're reflected with probability. Now the next feature, having to do with reflection again, that I would like to describe is something that you're also familiar with, perhaps not so directly, but perhaps you've seen the colors in soap bubbles. It's made out of soap water, which has no color. No color, I've seen the colors. Mix it together, get a lot of soap water together and look at it. No color. You take oil, which is a sort of a yellow fluid, you know, and it drips with blackish yellow junk. It drips out of an automobile on a rainy day. You must have experience here with that. And you look at the puddle, to your delight, there are colors. Colors. These colors are produced by reflections from two surfaces near each other, very close together. If the surfaces are far apart, we'll discuss it later, the same phenomenon really occurs, but it's much harder to see under normal circumstances. What happens there is that in a soap bubble, for example, there's a layer of water. And so we have two surfaces at some distance from one another, so. And then the photon can either come down here and reflect right away, or it can come down this way and reflect from back there. Okay? Now, as it turns out, it's about the same percent. If it's just water between air and air, it's about the same 1 in 25 both times. What's the colors? If I'm going to do it with monochromatic light, that light of one color, what can you see in colors? What you see on an oil film, on a mud puddle, or in a soap bubble, when you use light of exactly one color, is not colors, but bands, bright and dark bands. Places where the light is reflected very well, and places where it's not reflected at all across the bubble. Now, the position of those bands, if you first looked at a bubble with red light, you see bands, black and red bands all over. If you look at it with blue light, you also see blue and white, blue and black bands. But the pattern is not the same. They're displaced from where the red ones were. And so when you have both red and blue, you get purple and red and black and purple and so on. Now, if you add to that yellow with its pattern and so forth, you get all these colors from mixing, okay? So we're going to simplify experimentally, as Newton did, and look at these, this reflection. What Newton, most of his experiments, he did this clever way. He had a beautiful curved piece of glass, which was a lens, and a flat piece, and put them next to each other. And then this was only a very slight curvature. And so he had this gap between the two. And when he shone light this way and looked at reflected light, which, depending on where you looked, see, this is a cross-section of the lens, which is more completely like that. There is some reflection in here, which is irrelevant at the moment. There's another glass plate down here. When he looked in different places, the light came down all over, and he looked in different places. He was looking at cases that corresponded to reflection with one gap or another gap between the sides. And when he looked at this with monochromatic light, looked down on it, since it was a spherical lens, he saw in what I call bands in the soap bubble, but more organized, he saw rings, called Newton's rings, with a black area starting and then red, if it was red light he was using, and black, red, and so forth. These looked like they were coming closer and closer together, but he was a clever man and understood immediately what it meant. If he measured the distance from here to here and plotted the answer for whether it's red or dark against this distance, not against this, instead of measuring away from the center, he measured how far apart these plates were. Then he found, like our friends the Mayans, every time you had 365 points, they got black. In other words, if this was black and this was red, then double that distance was black again, and triple the distance was red, and 4 times the distance was black, and 5 times the distance was red, and so on, nice and even. In other words, instead of measuring by this distance, by measuring the thickness, you find the following experimental result. Reflection coefficient against thickness between the two layers. Okay? The spacing between, in this case, if it's an oil film bubble, with that's the distance. In this case, it's the spacing between the lens and the plate. And if you could change it, it's harder to change in a soap bubble under control, but it changes automatically as it dries out. You get the following. You get no reflection if the thickness is 0, then you get a strong reflection for a certain thickness, and then if you make it thick, you get no reflection, you get no thickness. Reflection, then you get no reflection, you get no reflection, and so on and so on. And now it's getting thicker and thicker. Does this go on forever? Yep. If you got good enough monochromatic light and get the experiment under control, you can make it go almost indefinitely. You can make this work for distances of 1 meter or more. Still, keeping track whether it's even, odd, bump, bump, bump. Okay? There's nothing. That's interesting. Very interesting. But you know, that's damning. Why? Because what theory were you figuring for the reflection from that? That made the reflection be 4%. The odds, 4%, whatever. You put another layer down here at the right thickness, expecting to get 8%, and you get nothing. How does a layer down here turn off the reflection from the layer up here. Or, if you figure that out, and you make the layer just a little thicker, it doesn't turn it off, but in fact the reflection is more than twice. On this scale here, this line would have been what you would have expected if you expected it always to be 4% plus 4% or 8% from the two surfaces. This is what you would have got if you disregarded all this nonsense that actually happened. By common sense, it reflects with a certain odds, and it reflects from the other surface with a certain odds, and so altogether you get twice as many coming back. This is the twice as many. But for some, if the thickness is 0, you don't get anything. If the thickness, hey, that's not such a bad idea, is it? If you don't have any water there at all, you wouldn't get any reflection. Starts out right anyway. Well, that theory was kind of dumb now that I come to think of it. And that helps to explain Newton's observation: when the distance is too small, the light doesn't know anything about it. If the thickness is sufficiently small, it doesn't reflect. It does exactly the same as if there's nothing there. But the horror of it is, it's all right that it increases as the thickness goes up, but it overshoots, you see. And then it comes back to 0 again when the thickness is just right. It's very difficult to invent a probability thing. If I had these spots on this surface, it's very hard to see how you're going to have spots on this surface, which turns the spots on that surface off when they're the right distance away. And so Newton went a little bit nutty. And he talked about fits of reflection and transmission and so forth. And I would like to now just finish this by telling you what is the answer. Now here's the answer. This is the way we figure this out. It goes as follows. What we're going to calculate is a probability. The probability of a particular question. And then a probability that this counter goes off. The probability that if I had one photon coming down, it'll come back to this counter. The probability, which is measured by this curve. And here's the way that the rule is for finding the probability. Now listen, hold your seats now, hold on. Don't be afraid, just go along, all right? Never mind it, don't like it, huh? Just hold on. It works like this. What you do is you take a piece of paper has nothing to do with the original thing. The piece of paper is only to make marks on. It's got nothing to do with the light. Right? And I have your following rules. That you make an arrow to represent, well, for each reflection, you make an arrow. This arrow, for example, is for the reflection from the front surface, and this arrow might be the reflection from the back surface. And I'll tell you in a minute how to make those arrows. And then what you do is you tie the arrows together this way. You make one and then the other. All right? That means you make this arrow, and then you put the tail of the other one on the head of that one. There's the first arrow is a reflecting arrow from the first surface. And this is the second arrow is the reflecting arrow for the second surface. And you put these two arrows together by this rule. And then look at how far off you've come to the end, yes? Yes? You count the pins in the hole. You count the number of beans you put in the barrel. I mean, you make these pictures. And then you ask, how big is the circle? An area. That area represents the probability that you get the thing back. If the circle area is big, then you get a high probability. If the circle area is small, you get a small probability. And I just have to say one more thing of how to make the arrows. Answer. Well, the size of the arrow depends upon the particular materials. I won't come into that right now. The absolute size of 4% is another matter. What you do is you make an arrow, and depending upon the time it takes for the light to get from the source where it started to the place where you want to count it, you turn that arrow like a clock, depending on how much time. So if it takes a long time, you see, you start out at the source. There's the arrow for the source, but that's not the arrow you're going to draw. This is just a thinking arrow. And then you say, turn over, ding, 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 round, 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 depending on how much time it takes. At a certain rate, every second it goes around 75,000, goes around a hell of a lot of times. It goes around 1 followed by 15 zeros times in 1 second. But it doesn't take light very long to get from the source to it. So it still turns around a lot of times. You turn it around, okay? It's like the roulette wheel, and just at the moment it hits the counter, it happens to be sitting at some angle. All right? That's for the reflecting from the first surface. Now, what about, that was supposed to be this one. I've gotten too many arrows on here. What happened is you take the first surface reflection, turn it through at this angle depending upon the time, and it ends up here. You say, that's not a very big angle. You said it was a big angle. It is a big angle. You know, if you keep on turning, it can look like a small angle when you're done, but you had to turn around and around and around and around and around, right? You know what I mean. It goes around like a clock hand. After 25 years, it's still saying 2. It can start at 2 and end up at 2:15. Yes, 25 years it went around. So here it is, having been turned around a lot of time. Okay, this is from the first surface, I should say. That's the arrow for the first surface. Now the arrow for the second surface, rule. Same as the arrow for the first surface, but in the other direction. It's just an accident. It happens to be the opposite direction it starts because, well, not because. The rule will turn out later. When you go from air to glass, it's one way. From going glass to air, you change it around. Anyway, you start this way for the second surface, and you turn this one. No, which way did I turn? Yes. For the time. And when you get finished with this roulette wheel on the second one, it comes out so. And then you add them together the way I said. You tie one on the other end and make the circle. And that's the laws of light. And that'll tell you whether it reflects or it doesn't reflect. And what difference does it make? Why do I get these ups and downs? Well, sure, if you move this, kept that the same and moved that, what is that going to do to my exercise over here? Answer. The first arrow, the time doesn't depend upon where the other surface is, so it does exactly as I did before. I'm doing the same experiment with the bottom surface a little further along, okay? Top's the same place. Now the second one, however, when I went to turn it, it's a little bit further. It takes a little longer to get there, and therefore it's turned to a new position. So this second time, the picture would look, if the thing was thicker, the picture might look like this. Instead of being here, since it had to turn further, perhaps it's turned to here the second time. And then when I add these two things together and tie one on the end of the other, and I'll just do that again here, you see that this line is now a long line, whereas before it was a relatively short line. This, remember, was the answer line. The answer line is a longer line, and the area here is much bigger of this circle, and the probability is larger. And this upping and downing, zoom, 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 and the answer comes out exactly predictable just by this little game. All right? Now, that's a shock, huh? You say, yeah, he's going to explain why it's like that. That's exactly what I'm not going to explain. I don't understand it. That's the way it works. What I'm going to do in the next lectures is to tell you sort of the generalization of this. This is a special example for reflection. I'm going to tell you how the rules go about turning arrows. It's in fact somewhat simpler than this example. It's not bad at all. It's easy. It's not hard, but much more generally. And what I've done is this is a prototype of the general result. There is no secret behind it that we can do any better than give you that result. All I'm going to do is generalize it. It's going to sound something like this. This part you needn't understand right away. It's what I'm going to elucidate in the next lecture. The idea goes as follows, in general. It's just a statement, and I'll come back and do it again, so don't worry. To calculate the probability of an event, which can happen in a number of different ways, the probability of an event is always what we call the square of an amplitude. In this model, it means the size of a circle corresponding to an arrow. An arrow is called an amplitude. For every event, you calculate an amplitude, which is an arrow on a plane. The probability is the area corresponding to that arrow. All right? That's the first bit. Second, how do we calculate the amplitude for an event? If the event is simply a photon going from one point to another of a definite color, then it's simply an arrow which turns depending on the time. And that's the amplitude. Notice, by the way, if there's no reflections and no trouble, it just turns, the area stays the same, the probability of finding a photon is not altered. Okay, even though the arrow alters, its area is the same. It's when we get in trouble when we have more than one way to occur, then the rule goes as follows. If the thing can happen in more than one way, then you find the amplitude. What that was, the arrow, for each way. See, if it could happen in two ways, you got the arrow one way and the arrow the other way. And if it could happen three ways, if it was a double layer of stuff and so on, then you put another arrow for the third way. Maybe that one's a short one. And if there's a fourth way, you put another arrow. And when you're all finished, you put them tail to tail, all the possibilities, and find the total, what we call the total, or the net result of making all these little arrow steps. And that final arrow is the total amplitude, we say, for the event to occur. The probability is, as always, the area corresponding to that arrow. That's kind of stinky, right? Well, it's fun, and it's strange that nature is like that. And I hope you come back to hear how it works in general, a little bit better statement of this to review it. And one other thing, I am going to try to explain to you how this rule explains several of the ordinary phenomena that you're used to in light, such as angle of incidence equals angle of reflection. On reflection, that light bends as it goes from air to water, and it travels in straight lines from point to point, and so on. It's all hidden in that one rule. And how that one rule carries all this information is part of the next lecture, as well as I would tell you right away one more thing, that this rule, that to figure out what happens in nature, you have to calculate an amplitude, is not just for light. It doesn't make any difference what happens. An electron does something. A nucleus explodes. Doesn't make any difference. How do you find it? You can only calculate the probability it's going to happen. And how do you do that? You can guess. You calculate an amplitude. That's a lousy little arrow. And the probability is the square of the amplitude, we call it. That's really, we should call it in our case, the circle of the amplitude. The circle that represents the amplitude measures the probability. And that's true not just of light, but of the whole structure of nature as far as we can tell. And although quantum electrodynamics is only about electrons in light, we discovered that part of the rule, at least, is valid also for nuclei, nuclear particles, quarks, and everything else. The thing that is special about electrodynamics is our complete knowledge of exactly what the rules are for drawing the arrows. But the fact that you have to draw arrows and end up calculating probabilities like that, which is such a shocking and horrible form for nature, is something that I will talk about next time in further detail. Thank you very much.
These rotating arrows are all very well, but is there another model?
The question is there another model? Naturally, we struggle to find it. I'll tell you the answer of what's going to be in the fourth lecture. Nobody can find one. It's worse. We're not so dumb. We're pretty advanced compared to the Mayans. We've analyzed it very carefully. We almost prove it's impossible to find one over a wide class of ordinary possibilities. If it's going to be any kind of a model, it's going to be at least as weird as this thing. The reason is that the answers from this are so simple. That is, it looks a little complicated, you're not used to it. But mathematically, those forms and those curves are mathematically so simple, and the rules are so simple, it's hard to make any mechanism at all that can reproduce such simplicity. The Mayan thing was really fairly complicated. The numbers were peculiar. There's no explanation of them. This analogy, our numbers are not peculiar. Those, they have an explanation for. It's a different situation. One more thing about gravity, I would just remind you, we don't really have a good model because what comes to why is it that there's a force inversely as the square of the distance? And what do you mean inversely as the square of the distance? That's mathematical. And Newton was the one who taught us that we can make progress if you stop arguing about that. He said, I make no hypotheses. I don't explain the gravity law. I tell you what the law is. That tells you how the things look, and you can predict where the stars are going to be, and that's the pattern. But I don't, at the moment, know. But he left open the question, just like you asked. Maybe tomorrow somebody will figure it out. On your particular question, it's always possible that tomorrow somebody will figure it out, but it's going to be very difficult and very strange.
Do you like the idea that our picture of the world has to be based on a calculation which involves probability?
Not really, if I get right down to it. I don't say I like it, and I don't say I don't like it. I am very highly trained over the years to be a scientist, and there's a certain way I have to look at things. When I give a talk, I simplify it a little bit, I cheat a little bit to make it sound like I don't like it. What I mean is it's peculiar. But I never think this is what I like, this is what I don't like. I think this is what it is, and this is what it isn't, okay? And whether I like it or I don't like it is really irrelevant. And believe it or not, I have extracted it out of my mind. I do not even ask myself whether I like it or I don't like it, because it's a complete irrelevancy. It's a kind of a dumb answer, but it's true. And when I'm lecturing, I shouldn't have said I don't like it. What I was trying to say is you probably don't like it. There's nothing I think we can do about it. It might have been something else. I don't know how else to express it. It's not really personally a dislike.
Have you left out anything in this lecture which you need to add later?
It's very difficult, and I worked very hard on the lecture to try to use as my examples things that I didn't have to change later, the interpretation slightly. You know, I couldn't get an elementary enough process that I didn't have. Later on, I have to make a little change. You see, we talk and we see as though it's reflected at the surface. Actually, what's really happening, I want a deeper understanding, which I should do later on in the lecture, but I might forget, is that it's reflected because it affects electrons in here, which re-emit light here, or here, or here, or here, or here, or here. And what really is the things that we have to add is not the arrow from here and the arrow from here, but a whole lot of little ones from all the distances from there to there. But believe it or not, you get the same answer. Okay? So what I really ought to do, and I would do if I were doing it correctly, would be to talk about the reflections from every interior part and adding arrows. But I would rather add just 2 arrows the first time than an infinity of them. So I didn't cheat a little bit, but I got myself in a slight hole, which you picked up. The actual reflection is from the material, the electrons in the material. In the case of Newton's thing, it's because the electrons which are reflecting from the glass here and here are interrupted in their pattern, and when you add the arrows, it comes out to be, believe it or not, the same as if you just take a one from here and one from there. Perhaps just for those who can, I don't want to make it too hard, but just to give you a clue of the marvelous way it works. If you added tiny arrows to represent reflections from everywhere, instead of just talking about it reflected from here to here, which is a good equivalent way. But if you took a whole lot of little baby arrows, each one a very, very tiny angle from the other, all the same length, which is the reflections from all these places, you see you generate a circle. And what I was using instead of the circle were the 2 arrows, which were the beginning arrow and the end arrow of the circle. And what you told me is I shouldn't talk about the reflection from the front surface and the reflection from the back surface. I should talk about the reflection of all the stuff in between, but it's equivalent. The net result of going around here is the same as going up here and back on that one. It even accounts for the minus sign, at least. That is, the distance from here to here is what you get by putting onto this arrow this one backwards. Well, the distance is the same, see? So I got it upside down in my book. But this line is the same line as you would get by going in a circle. So it's really reflected from the interior. But in the first lecture, I thought I'd just get 2 arrows instead of an infinite number.
Does your picture apply to anything besides electrons and light?
This aspect is universal over the whole of the world's phenomena, as far as we can tell, not just light and electricity. This phenomenon of drawing arrows and making areas for probabilities. The probability amplitudes, we call them. The amplitude and the probabilities are the squares of these amplitudes or the circles of them. That's universal. The next problem is a rule for how to draw arrows under different circumstances. What kind of arrows do you draw under different circumstances? What are the rules? One of the rules I told you is it turns at a certain rate for light and so on. Those are the rules that we do not know well in the case of the nuclear phenomena. But we know virtually exactly, or at least as far as we can tell experimentally. I lost my numbers. For electrons and light, the rule for how to make the arrows is apparently completely known. Nothing is ever complete. But within the accuracy and so on, it's known. What's not known is the rules for making the arrows when it's protons that are moving around and so on. Okay?
When you are looking at something, do you see only light, or do you see the object?
The question of whether or not when you see something, you see only the light or you see the thing you're looking at is one of those dopey philosophical things that an ordinary person has no difficulty with. Even the most profound philosopher, in sitting eating his dinner, has any difficulty in making out that what he looks at perhaps might be only the light from the steak, but it still implies the existence of the steak, which he's able to lift by the fork to his mouth. The philosophers that were unable to make that analysis and that idea have fallen by the wayside through hunger.
Can you tell us whether in the future your theory will be found to be wrong, or is it complete?
No, of course not. How can we know what the final thing is? I tell you only what we know today. Can I tell you more? Do you want me to tell you more? Would you like me to tell you what we know tomorrow? I'm sorry. I have the Nobel Prize from the past, not from the future. I do not know the future. And I answer in a similar way to your likes and dislikes. If you ask me what I think will happen in the future, I'll tell you I do not think. I do my best to understand what supposed to understand what we know so far. I do not know what you're going to discover next, okay? I can't. I know only as you're talking about the edge of the discovery business. And it's impossible to say what's beyond the edge. So I can't answer you, all right? Except to say that the history of physics has been that the things that looked like they were nicely set aside it turned out to be erroneous upon further discovery. And since society continues to be vigorous enough in its endeavors to investigate nature, it's almost sure, from a social point of view, not from a theory of physics, that new things will be found out which will not fit in, and we have no way to tell whether some young man, perhaps from New Zealand or somewhere, will find another way or more about this stuff, so it'll have a different picture in the future. Obviously, I can't say. I tell you what it looks like today. You call it my theory. It's not my theory. It's the theory everybody uses. I'm going to make it a little tougher this time than I did last time. The phenomenon I'm talking about now is the theory of the electricity, light, and so forth, and we're concentrating on, first tonight, light, and next Tuesday, it'll be about electricity, and finally we're putting the two of them together. And the next lecture after that, we'll talk about what's wrong with the theory and what's in the world besides electricity and light, what else there is in physics, and what new questions are up. But in the meantime, I'd like to talk about light. Newton started by many experiments and observations which began this subject. He found there are phenomena that are so very, very common, but are absolutely sensational, ununderstandable, and almost impossible, supposing that light is made out of corpuscles or particles. Newton assumed that light was made out of corpuscles or particles because he made a mistake in reasoning. He said that he thought that the shadow edges were very sharp, and that meant that it must be particles, because if it were waves that went past the shadow, they would spread into the shadow. This is a misunderstanding of exactly how waves do in fact behave. They do spread a little tiny bit into the shadow, and the shadow spreads into the light of it, but not very seriously. And in fact, the wave theory of light is much easier. It finds the phenomena that Newton discovered much easier to explain. But I want to start by taking the view that light is corpuscular, that Newton had, and remind you of what these phenomena are, and then go back over Newton's attempt to explain them and see how pitiful it is. So we start with the reflection of light from a surface of glass. Last time I used water, and I said it was 2% reflecting, and somewhere along the line I changed it to 1/4, and that was a mistake. It's glass that's a quarter, and water that's a 50th. 2% is not a quarter. I mean 1/25th. It's 2% is 1/50th, and for glass it's 4% or 1/25th. So we'll talk about glass. The first feature that's interesting is that from glass the light is reflected only partially, and if it's particles it means some of them come back, 1 out of 25, and some go forward. 24 out of 25. There is nothing too hard about that. If you would suppose something is different from one particle to the other, even in their arrangement or something like that, but further experiments have all shown that all light photons are exactly the same and in the same condition, and there's nothing we can do to preset the photon to make it more likely to come back from the surface, a single surface of water, than to go forward. There's no way. And we have, well, I'll keep on going from a simpler point of view, and we'll discuss other models in a minute. But the really interesting feature is that the reflection of light from a glass surface is affected if there's another glass surface below it. For example, if you have a soap bubble, which is the surface between air and water and air, then the two layers make colors in the bubble, which aren't in the water, but is produced by the effect of the reflection from the two surfaces. And if I choose light of a particular color, say if I looked at the bubble with purely yellow light, then I would see rings or areas that are black and areas that are bright yellow, relatively. In other words, areas that reflect well and areas that do not reflect at all. In other words, the reflection from a surface, which you would expect from a single surface, can be reduced to 0 by putting another surface here, which common sense would imply would increase the reflection, when it could in fact make the total reflection 0. And the actual reflection probability, chance that the photon or corpuscle gets reflected, varies with the thickness of the layer this way. If the thickness of the layer is 0, it doesn't get reflected at all. That's nice. No glass, no reflection. If the glass gets thicker, the reflection increases to a certain peak. But if the glass is still thicker, the reflection falls again to 0, as I said, and rises and falls and so forth in a repetitious fashion. Newton, believe it or not, only working with very thin layers first, discovered this with 3 or 4 at 10 repetitions, and then was able by a clever experiment to demonstrate that it happened after 34,458 reflections. Repetitions. In other words, with 1/4 of an inch of thickness, this bumpy thing was still going. Nowadays, we can do this experiment in which these two reflections are separated by so far, 1 meter or more, and if the conditions are just right, you get monochromatic light of exactly one color from a laser, you can still see as you move this thing, reflection strong, weak, strong, weak, strong, weak from the two surfaces. So it goes on forever. Now, how can we explain such a thing from the point of view of corpuscles? I do this to show you what a fix Newton was in, to explain it, because he thought it must be corpuscles. First, the reflection must depend on both surfaces, because it depends on the distance between them. Exactly. Also, he knows the wet one or the other surface to change the reflection. So they're both involved. Yet it can't be that the particle is reflected from the first surface, because if it were reflected from the first surface, it would never know where the second surface is, and that reflection depends upon the position of the second surface. For example, if it was reflected from the first surface, how could it be not reflected at all if there's a second surface at just the right distance? And therefore, it must be entirely reflected from the second surface. But the reflection from the second surface is affected by the position of the first one, and therefore it must be as follows. The first one generates an influence which generates some kind of a wave in a medium or something of a kind that follows the particle along and changes its disposition to be reflected or not reflected. That is, it gets the particle of light as it comes through, can be in different conditions, either a condition of easy reflection or easy transmission, the opposite, no reflection. And whether it's easy reflection or easy transmission is determined by some kind of an influence which propagates along from the front surface and overtakes the light particle and adjusts it, so to speak, to make sure which way it's going. Now, this had a lot of difficulties with it. It was called a theory of fits of reflection and transmission. It's not good for the following reason. You can't get along very well with the idea that it's not reflected at all from the front surface. Because suppose you had very deep water, just a little dirt in it, then you still see the reflection just as well. And if it's not reflected on the first surface, it's impossible to explain, because that stuff which is coming, looking for the bottom surface never gets there, and yet some light is reflected. Second, if it's all the decision about reflection is made at the second surface, then it should not be expected that it would be possible to alter that decision by putting in a third surface. Now, Newton did not have available the experiment in which he used more than two surfaces. But had he done that, he would have found that the amount of reflection is altered again by the presence of third and fourth surfaces. And even though with two surfaces one might get a very strong reflection, by putting more surfaces underneath, you can reduce that again to zero. So that the decision is not being made on the second surface. The decision is made on the last surface. Then how does it know as it's going along whether there's going to be a last surface or not? Now, Newton is, I would say, is a genius about something. Actually, he's a teacher of something. He's the man who taught us how to do or how to think about science in a modern way so that we can make some progress. He's the one who distinguished very carefully between the facts that he would develop and experimentally determine this really happened. That is to say, what really happens is that the amount of light or brightness does go up and down depending on the thickness. And that is to be distinguished from a theory to explain why it's so. He hasn't got a satisfactory theory. He did his best. I'm sure, I can tell from reading it, that in the back of his mind he knows there's something the matter with it. He knows the explanation is going to get him into trouble for somewhere. He can feel it. Because he puts that part in the form of queries or questions of how does it work. Can it not be that there's an influence which propagates along and overtakes the light and so forth? He doesn't say there is. He's going to get into difficulty. Now, you're all happily laughing at poor Newton, but you have to laugh at yourself, because you live in the world, and this happens, and you have these very good ideas about how things happen, and you can't figure out how such a thing can happen from common sense ideas. Save one possibility. It's not particles. All right? And so it turned out that people proposed that instead light is waves which come down, and like waves in the sea, and parts of them bounce back here and they bounce back here, and the crests come together under some circumstances of timing, and the crest or troughs come together under other circumstances. You get strong or weak waves going out, and that's what you see in brightness is the strength of waves. So that for many years it was all these wonderful phenomena were happily explained by the wave theory of light. The difficulty there, the idea there was that if you had a very dim light, the wave, that would represent waves hardly moving at all. There's a little motion, carrying very little energy. So when they went to investigate dim light with the most sensitive instruments to see what it looked like, you found that the dim light wouldn't make an instrument like a photomultiplier or any other device that was very sensitive go off, said there's a certain amount of energy here. No, there's nothing. There's a bump of energy. The energy came in lumps. It wasn't a tiny little bit dribbling in all the time. And so the experiments with photomultipliers, which I unfortunately don't have a direct experience with, but the characteristics of them are that light is made like a corpuscle, so that although Newton's logic as to why they have to be corpuscles was wrong, it turned out he was right about there having to be corpuscles. And his paroxysms of reasoning that were produced by this thing, the torture of the mind that's produced by this phenomena, plus the fact that light is corpuscle, was returned to the physicist as a real problem. And it has never been solved in a completely, well, it's solved in a way, in a description method by which we can predict what happens here. What happens here is that this is not the intensity of a wave, that is the amount of wiggling of the wave of some kind, but it's instead the chance that a particle comes as being counted by a photomultiplier. When I have the thickness so big, so and so many particles, if I sent a light so weak there was only one particle, I send only one corpuscle, one particle of energy, one photon, to the system. And sometimes it bounces back, and sometimes it goes forward, and this gives you the odds that it bounces back and goes forward. For a single layer, the odds would be 4%. This maximum height here is 8%, and 4% around here, and it can go down to 0. Now, we have not been able to find any system of logic that's consonant with ordinary ideas of causality and ordinary ideas about what things go. How can it not know when it's at the front surface, it's in the back surface, all that stuff that'll explain this or describe this. And so in order to keep going, in order to describe nature, we've had to generate a set of ideas which are empty of a set of rules, rather, which describe how to figure out these probabilities, which are empty of models. That is to say, empty of a model of the type you're expecting. Particle is like a billiard ball that bounces against a wall and so forth. It doesn't work. Or that it's like waves. And what I would describe last time to you was this picture. I would say that it was in about the beginnings of the 1900s that it was discovered that light, as a matter of fact, behaved like particles, which was the terrible shock after the great success of the wave theory. And then the problem of trying to see how particles could make these wave-like phenomena that are so easily explained by waves became known as the wave-particle duality. Things would be said like light behaves as particles on Thursdays and on waves on Tuesdays, and that, of course, is not a satisfactory theory. The quantum mechanical, it turned out as a quantum mechanically studied further that light is not unique in this connection, that things that were supposed to be honest, proper particles like electrons behave sometimes, produced effects like this, exactly analogous. So things that start out as waves behave like particles, and things that start out as particles behave like waves, until both was clear, behave the same way. They behaved in their own inimitable quantum mechanical way. It worked out in 1926. At first, the equations were discovered, and then it was, in fact, a man you don't hear of very much when they talk about quantum mechanics, a man named Max Born, who proposed. Somebody's blowing their nose. Max Born, who proposed the interpretation of the equation in terms of this idea that we're calculating probabilities of events, that it's a statistical matter, and that it's not possible to predict exactly what will happen in a given experiment. Now I want to repeat the rule that we have here, which looks completely artificial, and I prepared you last time, as you all knew. We had a similar difficulty last time. It's heavy. I'll take it out, okay? All right? Is that all right? Okay. Now, I predict that the probability that I'll have a microphone of that kind next time is very low. All right. Now, how do we describe this in modern physics? First, that we cannot predict what will happen. We can't tell you for a given particle whether it's going to be reflected or not. Horrors of horrors, but it's true. We give up. And second, in order to find the only thing we do calculate is the probability, let's say in this example, that it'll be reflected. More accurately, I should say better, this way, that if you have a source of light here and a photomultiplier here to look, the probability the photomultiplier goes off. That's what I'm calculating. I said the probability that a photon went down and bounced back. That's bad. Otherwise, I get back in the old problem again. Which surface did it bounce from? No. Just the probability that the photomultiplier goes off. All right? Now, how do you find the probability that the photomultiplier goes off? As follows. General. Not only about light, the whole of the world is built this way, according to these modern physicists. It's just an example. Photomultiplying goes off, electron counter goes off, things like that. Probability, you calculate probability of events this way. The probability of an event that comes out in the end is proportional to the size of a circle made by an arrow on a plane, a calculating plane over here. It's got nothing to do with the geometry of that. This arrow on the plane is called the amplitude, sometimes called the probability amplitude for the event. So everything that you want to calculate, the chance that the counter goes off, has a probability. No, it has a probability amplitude. There's an amplitude that it goes off. The square of that is the area, or proportional to the area. Somebody bothered me about a factor pi last time. Correctly, is the measure of the chance that the counter goes off. All right? Now, the theory, that's the framework of nature, and the rest of the theory of nature is to compute these probabilities, amplitudes. That is to tell the rule for finding the length of the arrow and where it's located. And that's what we talked about last time again, and I'm reminding you, in this particular case, it works as follows. For light that's monochromatic, of a single color, let's say red, it's the following is the rule. That you draw an arrow for the reflection. Let's say, for instance, that this is, say, a single surface. Reflects, let me suppose, 4%. That is, in fact, 1/25th of the light. So if the unit of light, if the light, 1 unit of probability is represented by that, and its size circle, when light is reflected, the length of the amplitude arrow is 1/5, because its square is 1/25th. So here's the amplitude arrow for reflection from the front surface. Should be 1/5 the other one. Incidentally, the same manner, the reflection from the back surface produces an amplitude arrow for, this is the amplitude rule 1/5. That's the rule for reflection. And this, from the top surface, this is the corresponding rule from the bottom surface, is to make the 1/5 in the opposite direction. And finally, one more rule, that you have to figure the time to go from the source all the way back to the photomultiplier, if it was going at the speed of light, and the proportional to that time, you move this around like a clock. So the effect of the reflection from the first surface is in fact an amplitude which is 1/5 long, but is tilted at an angle, which is what would result from a very rapidly moving, rotating clock hand going along, as if you wish, for the length of time that you would calculate ordinarily for the light to come to the first surface and bounce back. It goes around like a son of a gun. 1 followed by 15 zeros a second. Going around. And then when it finally reaches the photomultiplier, it's in some position. Likewise, the second one, this is the first one. Let's say this is the first surface, the second surface, but more correct when you put the timing in. That's the contribution of the first surface. Now, for the other way that the thing can happen, we have the second arrow turned also around a great deal, but not by the same angle. Let's just for a moment suppose that the two surfaces were exactly on top of each other, then the times would be exactly the same, and the angles would be the same, and in that case, the other one would come out this way. But if it's further down, it in general will come out at some other angle, because the time is not the same, so let's draw it at another angle. Now the rule is this, that if the general rule starts something like this. Probability is equal to the square of an amplitude. Amplitude for an event that can happen in more than one way is the sum of the amplitudes for each way. Now what do I mean by sum? How do you add two funny arrows? Rule for adding arrows, you put one on the tail of the other. So if this was number 1 and this is number 2, you draw them like that and see what you get left. So in this particular case, we have only 2 ways. We have only 2 arrows, and I've added them together by making one chase the tail of the other. This is the arrow representing the contribution from the first surface, and that's from the second surface, and you're all bored because I told you all that last time. But hoping that there's a few more, some people, I cannot believe that everybody who was here before came again, and there's the same number of people as there was before, so I deduce that there are some people who weren't here before. Now, this then produces these effects in the following manner. That if the thickness is 0, the first arrow points this way for the case of 0 thickness, say, and for 0 thickness, the second arrow points that way, and if you put this tail on the head of the other one, you go up and back, and the net result is nothing, whose circle is 0, and there's no probability. On the other hand, if you have a thickness, a little bitsy thickness, you got just a little bit more turn, and you get something. That's somewhere up, climbing up here. The best you can do is if you get the thickness just right, so that this one is turned around so it's exactly lined up this way. So with a certain thickness that's just right, the first one is turned a certain angle, and the second one, which would be out here, is turned more by another half turn, and therefore the second one is this way also. And when you put the tails together, you get it twice as long, right? And then you would have had it by one alone. And therefore, what is the probability? 4 times what it would have been for one alone. Because the probability is the size of the area of the circle, and for one alone, if there were only one surface, the circle is only so big, and there's twice the radius is 4 times the area of the circle. So therefore, the height of this is 4 times, the probability here should be 4 times as much as it is from one surface. And since from one surface it's 4%, and 4 times 4 is 16, this has to have been 16. And it is. Now in this manner, of course, if we take greater thickness, the thing turns around further and further, and it goes down again, gets back into the same condition in a repetitious fashion when the timings are so. And so we understand why this keeps on going up and down, up and down, up and down. No, I'm sorry, we don't understand a damn thing, but we have described how it behaves. You'll notice that the average here, if you had some circumstance in which you average this and didn't look too close to it, the thicknesses, you had an irregular plate or something like that, or for any other reason you want to average it, the average is about halfway up. In fact, it turns out, because of the symmetry of the curve, to be exactly halfway up, and the average is 8%, which is the amount of light that you would get expected to have gotten if 4% came from the front and 4% came from the back, and our life was easy. If it weren't for these bumps, there'd be nothing to that. We could understand 8% childishly, 4% from coming from the first surface and 4% coming from the second surface, but it doesn't do it that way. It sometimes gives us, instead of 8%, nothing, and other times it gives us 16%, which is more than we want, and it ends up, on the average, giving us 8%. And it gives a clue of how the old theories, the simple-minded views of what was happening, what happens in the world, why you can bounce balls and count things and do things as you expect them to do, works. It happens that these irregularities involve this distance of thickness is something like thickness of glass of the general nature of 10 1/millionths of an inch. And therefore, for ordinary pieces of stuff with reasonable dimensions in which you're not so accurate as 10 1/millionths of an inch, you're doing a lot of averaging, and then common sense dumb stuff like, look, it reflects 4% from the front surface and 4% from the back surface. It's got to reflect 8, come out right. But that's because you're averaging all this fancy business with these arrows. Now, what I would like to do in this lecture is to show you, to start you off in a certain direction and to show how it is that although this model of the world is so thoroughly and utterly different than anything you've ever seen before, or expect and hope never to see again, it will explain the simple properties of light that you know. And properties such as angle of incidence equals angle of reflection, that's in there. That light goes in straight lines, that's in there. That light, when it goes from air to water, it deflects. The light goes in a certain line, you know, and when it goes, light goes from air to water, It changes direction. Yes, all that's in there. That if you have a lens, you can focus light to a point, and things like that. All of that's contained in this thing, plus many other phenomena. And the great difficulty I had with this lecture was this. It's so easy to derive all these phenomena that you take so long to learn about in school that I did one after the other until I found I was doing too many. And then I realized I'm doing it to people who know that. For example, what is the exact behavior? How much does light go into a shadow? I wanted to explain. It's easy, but I'm not. But since not many people know how much it really, how it looks, they haven't seen diffraction anywhere, I won't bother with that phenomenon. So what I had to do is to control myself and not produce a large number of examples, but only a few to show you how it starts. But I can guarantee you, of course, because otherwise it would be illegitimate what I've been saying, that all this agrees exactly with every phenomenon that everybody has ever observed with light, every detailed phenomenon. So I'm just going to start with the simplest possible ones that are common. All right? We start with a mirror. We start with the problem of determining how light is reflected from a mirror. And we have here a source of light, and here the photoelectric cell, which is, a photo multiplier that's going to measure very low intensity light. We have one photon at a time go here through here, and we would like to know what the chance is that this thing gives a count. It's also possible if the light goes straight across. To avoid that, we put a black box in here. So we have to think, and we would expect that what we'd have is that the light would reflect from the mirror like so, and that's what we usually say, and that all you need is this piece of the mirror here. This got nothing to do with the price of cheese under these circumstances, right? And that, in fact, the place where it reflects is where the angles are equal. That might be obvious to you because it's so darn symmetrical, but if I put this thing further down, you can still prove the angles are equal, and I'll show why it is. By this rule. Yes, sir. As follows. Rule. Probability that a thing occurs is a square of an amplitude. Amplitude is the sum of the amplitude for every way that the thing can happen. In that experiment, there were two ways it could happen. In this experiment, there's virtually an infinite number of ways it can happen. To make it easier to understand, suppose that this mirror surface was temporarily divided into little squares. It's best if the mind forgets for a while that there's another dimension to this mirror this way. This is a cross-section of the mirror. And just for the hell of it, I can forget that, but we can do it the other way too. Now what happens is that there's several ways in which the photon could have gone to the photomultiplier. It could have come down to this part of the mirror and bounced off and went to here. You're crazy. The angle ain't equal. I'm not crazy. That's what happened. Another possibility is it could come here and go. Or it could come here and go. Or it could come where you'd like it to come and go. And it can go over here and go, and so on, and so on. And these are all possibilities. And the idea is that there's a certain amplitude that it does it this way, an amplitude that it does it that way, and so on. And now we have to figure out the total probability that it does it at all. Naturally, instinctively, I'm going to tell you the rule that the amplitude is biggest for the one where the angles are equal. No. The amplitudes there's slight variations, which we're not going to worry about them. It's almost the same for this one as for that one. Let us take it easy. We make approximations here to make it easy to do, and I'm not going to absolutely exactly mathematical. I just want to explain the idea. I'm going to suppose it's exactly the same amplitude for every one of these things. But the timing is different. That is, let's suppose that the rule of that your chance that you get the amplitude to be reflected in a little square here, there's some little arrow. Very small, I draw it. But because I have to count the total time to go from here to here to here, this arrow, the contribution of this one, gets rotated, zing, depends upon this time. And the one to go from here to here is also rotated, but not by the same amount. Because I think you can almost see that the distance from here to here is certainly not the same as the total distance from there to there. There's a time it would take. It's not obvious? All right, then let's take a place way over here. The time it would take to go over here and then go rushing off to here is certainly longer than it would take to go the easy way. And in fact, if you were in a hurry and you had to run over to this wall and run back, you'd know more or less that the best way to do it is somewhere in the middle there. And it isn't a good idea to run to the wall here and then have to go back. So what we're going to do here is to figure this out by a series of drawings to help us calculate. The second drawing underneath here is a kind of a graph. Let's see if I can do this with colors by some. I don't know how to do it with colors. I didn't figure it out ahead of time. But this is a graph in which I measure this way. Yeah, let's do it this way. The time that it would take to go from here to the mirror and over here, and I'm plotting it this way, directly under the place where I want it to go in the mirror, see? Now, the time it takes to go here, we just found out was pretty large, and going down, more or less, as we got near the center, and of course it's a kind of a symmetric curve, and it goes up here. What do I mean by this? Is this, let's make it very definite. If you're going to reflect from this point here, this particular route, then this is the amount of time. This height is a graph of the amount of time. There's a lot of time. If, on the other hand, colors. If, on the other hand, you were to go somewhere nearer the middle and come down this way and go so, then the time it would take is less. And it's plotted on this scale as this height from here to here. You don't have to worry about the plot if you understand the idea. The time is big, comes down, and goes back up again. That's all, depending on where you are. And now what does that mean for our arrows? It means this. That the contribution from this one corresponds to an arrow like this, a little baby arrow. Baby because I make these things very tiny in the end. I told you in the last lecture that we have learned that students take 4 years of undergraduate work plus 4 years of graduate work to learn how to add these arrows cleverly and quickly. And we'll just do some simple examples. So I tell you what, we'll have to just work it out ourselves for 1 or 2 examples. But that's all they learn is how to add the arrows. Now this, what you do here is you take this arrow and you turn it around a lot, that's I call a lot, from here to here, and you come out with the arrow in some direction. Because it's spun around at so much time. Now, on the next point here, which I didn't draw in a color, but just let's talk about it, is less time. It doesn't turn around as much. It's more like that, okay? The next one is less time. It doesn't turn around as much. I should be coming toward the green one in case. In this time, it's not, well, let's say this one's around here, and this one, you see, what I want to point out, well, I didn't do it too well, but that the change is less each time as I go along. That this one is, I don't mean that it's an accident that it comes out nearly horizontal. I don't care where it came out, but unfortunately it's nearly horizontal. Let's say that the next one is hardly any change from this and corresponds perhaps to that direction. There's no meaning to the absolute fact that it happened to come out that way. But it's important to point out that as I go on to the other side, the timing is increasing again. And so the contribution, the arrow I would have to draw to correspond to the contribution from this would be again slightly inclined. As I went further over, the inclination would increase again, further and further. If I do it very carefully, I should have at corresponding places out this side the same kind of arrows as on this side. In other words, the contribution that's made according to this dopey rule, that to get the total amplitude, that the thing arrives over there, where is the probability? We have to add an amplitude for each root, and each amplitude is the same, except that turns in different degrees depending on the time. And now I have to add all these things together. Of course, it goes on both sides of the mirror, way out. And it's hard to get started because they're way over here. But let me just start over here, or further back. What happens is, I'm going to put the arrows on each other's tail. This one represents the first one here. And now this one comes. You see, I put the arrows on each other's tail. And then the next one, it isn't working out too clear. It's hard to make the drawing clear, but maybe you'll believe me when I tell you what happens if you do it very carefully. And then it comes an arrow this way, and then the green one, which is hardly any difference in direction. And then the next pink one, that's just tilted up there a little bit again, and then tilted up some more, and then tilted up some more, and then tilted way back. And now let's, for the fun of it, keep on going. Yeah? But what will happen is the things get turned more and more and turns more and more. So the next one's this way, and 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 the next one's this way. Okay, boom. And in the same way, the stuff that I hadn't drawn yet over there correspond to an arrow tilted still further cockeyed and still further cockeyed until so on, all knotted up in little things. Now that from one edge of the mirror, which is the 74th arrow over there that I have, to the other edge of the mirror, which is a 7 millionth actually arrow, because it's usually with a reasonably sized mirror, since these angles involve turns, involve millionths of an inch, there are millions of turns. So that this got down to really down in the middle here, and it goes to the middle here. And so that the total amplitude, which is the sum of all these arrows added together, of which last time I added 2, I now add 3, no, I add 5, no, I add millions of them. I get a line for the net result of the whole thing, the total amplitude to arrive, which is this tremendous line from here to here, as the result of all those little arrows. Okay? Now, let's investigate. What determines how long that line is? The size of that square determines the probability. Now we notice a number of things. First, that the edges of the mirror are not important. That were I to have chopped a piece of the mirror off over here, a piece that you had intuition know that I was wasting my time piddling around with, it wouldn't make any difference. Because that part in there, the arrows are going, I throw it all away. I know you said it doesn't make any difference because, so I start a little bit off here, a shade. It doesn't hardly make any difference. Therefore, I can really chop this mirror down a bit. Where is the part of the mirror that makes the real difference, that makes this get a real length, that makes it likely to be big? It's the place where the arrows are all pointing nearly in the same direction for a while. Think a while. It means it's the place where the curve stops changing for a while. And after much mental effort, you'll discover that's always the place where the time is least, or possibly other way sometimes, most. Most often in practice it's least, but it can happen most. Anytime the time curve stops changing, it's a place where the time is least. And so it turns out that the ray that's most important, the thing that determines the probability, is the part of the physical world which is close to the place where the time is least. And that's why you don't have to worry about the other part of the mirror. And that's why, crudely speaking, you say, hell with the rest of the mirror, I can just use a little piece. You're wrong if the piece gets too short. If it gets too short, you don't get much of these. You get a few of them and not enough. You get different answers. But that's a few, maybe thousandths of an inch, and you're not used to experiments with thousandths of an inch mirrors, although in the laboratory we have many such experiments, and I am strongly tempted to tell you what happens with such things and so on, but that's not everybody's experience, and so I have to stop myself somewhere. And so I stop here. I say, what I've done is I've pointed out that only part that really counts and give you the answer there is what happens in the center of the mirror, that the other parts cancel themselves out in their effects. They're just as strong, there's just as big an arrow from here as there was from here, but just move a little shade over and there's another big one trying to undo it, because it's twisted. And in the middle, where the time is least, the arrows for a while point in the same direction. That's why in approximation we say you can get away with a crude picture of the world by saying the light just comes to the middle part where the time is least. And it's mathematically easy to prove that in any circumstance when the time is least, it turns out it means those angles are equal. And I attempted to prove that, but I won't bother you in straining your geometric imagination. Now, it perhaps bothers you a little bit to have to say that the reflection, that all this is happening, that there's reflections from all this part of the mirror when all it does is cancel out. And so let's discuss this a little bit. Let's do an experiment to find out how much light is reflected under similar circumstances. And I guess since I have one more color, and I don't want to erase everything I've got there, let us just imagine, for definiteness, that only this, well, here, let's say this piece of the mirror. I just used a piece of mirror so big. No bigger. I just used a little piece. It's a big piece, but it's in the wrong place. And I expect to see the light reflected from here to there. Not very likely, huh? But this dopey physics says that, yes, you have to calculate all the arrows from all this stuff from here to here, and they're all changing. It corresponds to the arrows up to there from the beginning. So it's just a bunch of arrows that go just for a while, and I stop, okay? You know, that line means these arrows are not in the picture anymore because that part of the mirror isn't there. And so you see that the distance from where I started to where I finished is very small. Not zero, but very small. And it's true. Experimentally, with a finite piece of mirror, you get a tiny amount of light reflected in an odd manner. It's called diffraction from the edges, but I don't want to go into that. It's very tiny, so let's say it's zero. This idea that the whole thing can be there and doing nothing seems like a kind of a waste of time and a mathematician's thing only. It's not real physics to have something that's not doing anything. But watch this. They're going to prove that it's right by the following dirty trick. I perhaps should expand this side a little bit. I'm getting pushed off the side of the board there by the way I've drawn it. This is the way the time was going, and the arrows were pointing in a sequence of directions which were very different from one another. And now I'm going to do a more fine calculation, which I cut it even finer, and you would find, if it's fine enough, that I haven't got much difference in time, but I find a bunch of arrows essentially going around in a circle, very close to a circle, getting nowhere, going around and around in a circle, because some of them are pointing forward and some of them are pointing backward virtually. It's continuous, but for some contribute this way and some contribute that way. Now let's have some fun. Let's see if it's really true. What we're going to do is we're going to make the mirror less effective by painting it black in the right place. We're going to paint the mirror black in just those places in which the arrows are pointing the wrong way. For arrows, if it turns out that the timing is such that the arrow points this way, don't use that part. Paint that part of the mirror black. Don't use it. Make it not reflect. I don't painted the wrong curve. I should have painted. My drawing is unfortunately way over here. The idea is, if the arrow is this way, I take it. But any time the arrow comes out that way, if that's the time between here and here, then I paint that part of the mirror black so that those arrows don't operate. In other words, in order to test this idea that everything's canceling out, I take the parts of the mirror for which the timing is just right to make arrows that point this way, or more or less that way, or at least have a bias in that direction. And the parts of the mirror that were contributing arrows whose bias was in this direction, I paint out. Or, if you don't like this idea of painting out, and you have enough patience, you simply cut the silver away. There's nothing. The light goes through. Worse, it can't reflect. It didn't reflect before. You got less mirror. It's going to reflect less. No, it reflects perfectly well. Because according to this picture, if I add a sequence of arrows, which are turning rapidly, and then as soon as they're supposed to come on, oh, here's the circle. Here it is, down here. Excuse me, and it's also in yellow. I add the arrows this way. They're going along all right, and as soon as they start to turn back, I don't let it go. I don't add anymore. I've cut the silver away. And now it gets around and starts to go in the forward direction again. So I let them come. I don't paint that silver away until it starts to back up, and then I paint the silver away. I get it out. And what I end up, of course, is a lot of little strips of silver separated by clear glass. And each time the thing does this, bloop, bloop, yeah, bloop, 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 over this whole distance. And wow, what a net arrow I've got for the final result. Lots of light. And so it's possible to take an ordinary mirror, flat, and cut away strips correctly in the right places, just right, strip after strip, very fine, it turns out, thousandths of an inch, so that when you shine light down on it this way, it bounces it off that way. This thing would only work with one color. If I've designed this it's called a grating. It's a line of lines, and it works like a charm. It's beautiful. If I use red light, and I've got that thing exactly right, it'll go right. If I use blue light, it won't work. What I have forgotten to tell you in the beginning, and I don't know whether I said it last time, is this is what happens with red light. With blue light, you get the same result, except the thicknesses are shorter. All the timing is quicker. And what the rule is for blue light is the same as it is for red light, except the speed at which you turn that for time is faster. You turn it more. Now you'll notice that the place that we put those cuts was especially designed just for this rate of turning. If it turned a little more, because it's blue, and I had the cuts in the same place as I made for my theoretical red one, it turns out it all gets kinked up and it doesn't work very well. But as a matter of accident, it happens to be so that if I make two changes, first I use blue light, and then I put the photomultiplier at a somewhat different angle, in fact less angle, it works again with the same lines that I used for red. It's an accident. I cut it carefully for red, put that photomultiplier over there. It also happens, luckily, that if I change the color, it doesn't work. But if I move the photomultiplier and change the color, it's cut again about the same place. It comes out, just geometry. And therefore, what happens is actually that if you shine light down here, blue light will come over here and red light will come over there, and it's a beautiful thing to see. Because if you take this thing and turn it, when the light is fixed, you'll see colors, red and blue. I don't know whether it's come down in New Zealand or must have. We have them in the United States now on automobiles. People have these wonderful colored signs that you wonder whether the colors come from. They're so bright, and as the car moves, it changes from red to green to blue, and all they are is mirrors with lots of lines on them instead of, and so they're not reflecting in a normal manner. All right, so that shows really that we cannot get rid of the area which gives zero, that it really is canceling out, and if we do torturous and clever things to it, we can demonstrate the reality of the reflections from this part of the mirror and produce some striking optical phenomena. It depends on how much of your experience is, whether this appealed to you or not, if you knew about grading. So you didn't. That's the problem with this lecture. I can go on like this explaining holograms and lasers and everything else easy, except you don't know anything about them. There's no use, but never mind. I try something else. This time I'm going to talk about light going from air to water. We would like to put the photomultiplier under water. We'll suppose the experiment, they're going to arrange that. This is water. Maybe it's easier to put the source under water. And here's the source of light that we would like to know. Photons, have a small number of photons. We want to know if they're going to get there. And we have, again, the same situation, that the light can go this way to the water surface, and then that way to the photomultiplier, or it can go this way to the water surface, and that way to the photomultiplier, and it can go all possible, different possible angles. And every one of them contributes an amplitude, and it makes a bunch of arrows at all different kinds of angles, and what's going to be the result? Same picture as we made up there. The only part that really gives a result is when the time is changing slowly. In other words, it's a minimum or a maximum. Minimum. Now, in this particular case, in water, I didn't tell you about this, but in water, when you're finding the amplitude, the rate at which the thing goes around in water is slower than in air. Or better, maybe it's a better way, excuse me, better. I made an error. What I said was wrong. Light travels slower in water than it does in air. So that the time, when you calculate for a length in water, is not the same as in air because the light goes slower. So that these lengths are more important, so to speak, than in here. What you need to do to find out what's the most important of these pairs. Remember, as before in the case of the mirror, many of them all canceled out and didn't make any difference, but there were some that were important when the arrows were always the same, when the time was minimum. So what we have to do is we have to figure out, to go in here and to come down here, where the time is minimum. The idea is, suppose that you were really in water, and you went in a boat, you could only go slowly, and then you could run quickly on land. Well, the beautiful girl is drowning here, and you're the lifeguard, and you can swim slower in water than you can run on land. Where do you hit the water? You rush this way to the water and swim like hell. No. Actually, there is a place that's the minimum, which it would be foolish of a lifeguard to analyze and calculate under the circumstances. But the fact is, there is a computable position at which the time is minimum, and it's some kind of a thing that looks like that. The idea is, it is not the straight line, because the straight line has too much water in it. so to speak, water path. And by moving for less water path and more land path, one makes a compromise and comes out so. And that is the reason why light is bent into water. And as a matter of fact, if you follow this thing all the way through, you can prove that the ratio of the sines of the angles of the this and the that is the ratio of the speeds in the air and the water. But the reason that it's a minimum time is the same reason as it was for a mirror. Okay? In the same way, we can understand why light goes in a straight line. It's used, if we had a source here and a photomultiplier here, there are many ways the light could go. We could say a photon can go from here to here, a certain amount of time, phase. That's the way I've been doing it before anyway. But I'm going to be more accurate this time and tell you that the story that I said it went in a straight line before in calculating things was only an approximation. If I didn't do that, I get the same answer as if I do the following. I say, not only does it go in a straight line, it could also go this way to here. It could go this way to here. Really? Really? It can really do, yes. It can go any way it wants. But almost always, the contributions from these different ways cancel out with each other completely because there's a nearby way that's got the arrow the other way. But if you can find a way where if you change the paths a little bit, nearby paths, don't make any difference to the time, then you've got the place where most of the contribution is coming from. And the story is as follows, that if you have a path like this, a nearby path can be made that's shorter. That is, has a different time. Distinctly shorter. A lot shorter by moving it in. And so you can get a very different time. But that the minimum time comes for the path that's a straight line. And so the most important contribution is from the straight line. Remember that in the case of the mirror, I say the most important part of the contribution is near the place that is the minimum. It isn't exactly that one arrow that does it. No, it's the contribution over quite a range. And so it turns out that a light does not really go in a straight line, but it smells the neighboring lines and it uses area around it, just like a section of mirror is necessary to get the full reflection. A section of space is necessary. If you were to put blocks in here so as to not allow the path to wander too far away, and made these very tight so that it was try to go in a straight line, you would discover that the light from this source, if you put the photomultiplier here, for instance, and didn't have these blocks, no, if you put these blocks in like this and had the photomultiplier here, let's say the blocks are pretty far apart, and put the multiplier in such a way that that line is not allowed, that corresponds to using a piece of the mirror that's in the wrong place. But if this thing squeezes tighter and tighter, after a while light begins to come here. The reason it comes is that you've only got a few of the arrows. It's just as if you used I didn't show you in this case. It's the same idea. If you did have the mirror in the wrong place but used a very short mirror, then there's not enough range for the arrows to cancel each other. Just a few that go one way and it stops. And so what happens is that there's a little, if you cut this very fine, the light spreads, that it doesn't go in a straight line. And if you try, therefore, to squeeze light into a small hole to make sure it's going in a straight line, you discover that it no longer goes in a straight line. This is a few examples of how the theory of thing is worked out. Let me just do one more, which is interesting. Instead of dealing with all the net result of adding all these, in empty space, of adding all these different possible paths, is in fact turns out to be the same as if you just took this one path. Very closely, as for approximately, well, essentially that. I mean by that, there's just another factor, the angles are the same. If we think about this in a special case, let's draw an artificial line here that means nothing. It's just like the equator of the Earth, it's just a line. And then consider paths which are straight in two sections and ask, what about light going this way, and this way? So you don't have too many different paths to add. We restrict them to be double straight line sections. Then by exactly, the answer is exactly the same as for the case of the mirror. The time to go this way is a big time, and this changes and changes, and it changes rapidly. And if I plot it this way, the time for these different things, this is a long one, that's a short one, that's a long one. This time you can figure the time immediately in your head because the time is just the length of that line, and you can see that that's long and that that's short. Now, let's have a different kind of a game. Let's do something to make this one longer so that it's the same as that one. Let's fool the light so that all the paths are the same length of time. How can we? I told you it went slower in glass than in air. So let's put a piece of glass in here to slow it up so as to take a little longer. Let's say we're not going to do anything to the path out here. That's going to be the key time that we're going to make everything equal to. Now, the one that would go through here straight would have got there too fast. We slow it up for a while, and by slowing it up, we bring it so that the time it takes is the same. Now, there was a path that went like this, and that had a time so. It's also too short, not as much as the other one. We have to make it take a little longer, so we have to put a piece of glass in here. This glass is not as thick as this one because we don't have so much to offset. The nearer we get to the top, the less we have to use glass to slow it up, and the very last one needs no glass at all. If you put all these funny pieces of glass in there, the net result, of course, is that you're putting in a piece of glass shaped like so. The result of that is that the time, now, with the glass in, by careful design and the exactly right shape and right thickness, you just found out how to calculate the thickness exactly, just put the right thickness in to compensate the time, you will find that the times now are all the same, no matter which path it is of these straight line types. What happens then? Now, each one of them contributes its amplitude. Yes, amplitude, same time, same, whatever the angle of one of them is. The next one's the same, the next one's the same. You straightened out the arrows. What a dirty trick. You straightened out the arrows. And there's a lot of arrows. There's millions of arrows. And so the result of this is that they get, for the final result from the front to the tail, a sensationally large, unexpectedly enormous arrow, a high probability of going. Of course, you know what I'm describing. A focusing lens. If you have a source of light here, and it just sends light to here, it's kind of weak because it spreads. But if you put a lens here, it'll concentrate it right away again back to here. And that means concentrated light means high intensity, and really high intensity means lots of photons. Or if the light was weak, the chance of a photon arriving is very strong at this particular point and very small everywhere else. And so by the trick of arranging things so the times are equal, we focus light. And so by this, I use these examples to show you how what looks at first like an absurd rule with no causality and nothing like anything real produces effects that you're more used to. It also produces other effects that you may not have been used to, such as the grating and a number of other things. And so this is the success of this point of view, and it continues to be successful. And I would summarize it by saying what we know so far is that the probability is equal to the square of an amplitude, then they need a calculus of the amplitude, that amplitude for an event that can happen in several different ways. In different ways, I should have written this in the beginning, is the sum of an amplitude for each way. Now I have the rest of that should be really all that is really necessary to understand. But in order to get a full flavor of the theory, I would like to tell you a little bit more about how people calculate these amplitudes. And a little bit more about the law for the amplitude. For example, I kept bringing in funny things like when you have a reflection, you have a little arrow. When it's from the other surface, you make the arrow backward. When you go through glass, you have to use a faster timing, and so forth. All right? All these things should have to be explained, and they will be, not this lecture. However, the particular feature that I can describe a little better, a few things of how we analyze the amplitude. A particular problem, to show you the type of thing, is this. Suppose you had a surface here, and that we have a reflection. Suppose this was a 4% surface, so that the amplitude, the intensity that came out here was 1/25th, or that for that surface, the amplitude of reflection is a fifth. Now that, and I put the photocell here. Well, you could put a double surface. Well, I have it already drawn. I'll draw it again. I have a double surface, and a source, and the reflections, and all this stuff, and I computed the amplitude for the light to arrive here. Now I'm going to try another thing. Instead of putting the photomultiplier there, I make a little hole, I let the light keep going, and I let it bounce through a couple of other surfaces, 3 surfaces, whatever it is, all right? And come out over here and put the photomultiplier there. How do I figure out what happens, what the amplitude is? Now this amplitude in this particular thing can be thought of in, as so to speak, 2 problems. One, if light starts here, what's the amplitude to get here? The second, another problem that's interesting is if I put the source here directly, what would have the amplitude to have been got there been? It turns out from those 2 things you can figure out this combined problem by an operation you could call the rule for successive amplitudes. Right? The rule goes like this. Let us suppose that this section here, if you don't understand this too well, it doesn't make any difference. You get some, I'm trying to give you some flavor. If the flavor tastes bad, it is, just relax. Now here, some people like ginger snaps and some don't. Let's say in this problem, we've already worked out the amplitude for all the possibilities added together to arrive here. Let's call this point A, this point B, and this point C. So we have if, well, the amplitude to get to B from A, that is a source A of unit strength, 1 photon, has an amplitude to get to B that's been worked out. Let's suppose we start out, this is the source strength, 1 unit. We begin. And what do we get out is the result B, the amplitude comes out some crazy arrow. So let's say that that thing is this arrow. That's the amplitude that gets from B to A with the source. What is this thing? It's 1/5 as long. Let's say it was 1 surface. It's 1/5 as long and a certain timing. Let's suppose this surface over here ends up as a 4%, 1/16 reflector, or 11%, and 1/9 reflector. Makes it easy for me. The length of this thing is a 1/5, you see, so that the thing will be 25, 1/25, and you have to turn it to an angle. Now this next one, if it would work all by itself, if the amplitude to get to C from B alone is this. If at B there was a unit amplitude, if at B it really was 1, then there's a certain time delay and a reflection. There's some time delay corresponding to some angle, and there's a length of 1/3. This happens to do with the time delay. The time delay, I mean, from B to C. Now, what would the result be? Why do I say 1/3? Because the area of the square would be 1/9, which is what I said the reflection should be. Now, what will be the amplitude to go get to C from B, from A, all the way? It isn't hard to guess. First of all, the total time means that the angle, whatever it is, you go around and around and around, the sum of the amount you went around for the first part plus the second part, because the total time is the sum of the 2 times. So that you're going to draw something whose angle is the sum of this one and this one. It would have turned around while it was going to B. It goes around, 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 around. It goes to B, and it goes around, 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 around some more, and that's how much more. So the net result is an arrow sum like this at an angle, which is the sum of that angle and this one. You turn this, and then you turn it that much more, and you come to here. Here's where we start with the 1, and here's what we're coming out with. And how long should it be? Well, the chance that it gets, of all the light that comes down here, 1/25 is reflected here. And of all the light photons that come here, only 1/9 is reflected there. So it turns out that that means that the of the light, let's say I had 1,000, I have bad numbers. I should have taken better numbers. What you have when you finish is 1/25 times 1/9 of the light. 1 over 225 parts out of 225 photons, about, on the average, 1/25 or 9 photons get through here, and of those, 1 goes here. So 1 out of 225 come out, which is, by the way, 1/15 times 1/15. 15. So therefore, this size of this is 1/15. Now, the 1/15 can be, this composition, this is the rule of composition. Add the angles and multiply the lengths. So you have two events in succession, you combine them by this rule of composition, that you add the angles and multiply the lengths. Putting an arrow on the tail of another arrow to find a final arrow, we call adding the amplitudes. Composing them this way, multiplying their lengths and adding the angles, we call multiplying the amplitudes. The reason we call it multiplying is interesting, therefore, that arrows can be added, can be combined by two operations, putting them on each other's tail and multiplying them together like this, which we have called adding and multiplying. And the reason we call it adding and multiplying is it obeys all the right rules of arithmetic for addition and multiplication. All of the rules such as, I don't remember the rules. A times B is the same as B times A, for instance. A and B, these arrows, combining it this way and meaning by times this composition rule, then it continues to be right. Now, the rules of algebra are things that are studied by mathematicians, and mathematicians have tried to find all the objects that you could possibly find which obey those rules. The rules were originally made for counting apples. It was improved by using negative numbers. It was improved still further by inventing fractions. It's still true you can add and multiply fractions. You can use unending decimals to represent numbers and add them and multiply. We have today become very sophisticated. In the early days when mathematics was first developing, and it was said that a number is something like when you count the number of apples or people or something like that, then the whole idea of a half a person was a problem. But today there's no difficulty at all, and nobody has any moral or discomforting, gory feelings when they hear that there are 3.2 people per square mile in certain regions. It doesn't bother them. They don't try to imagine the 0.2 people. But what they do is they know what they mean, that if they multiply that by 5, it gets to be 16, and so forth. And so some things that can satisfy the rules of arithmetic can be interesting to mathematicians, even though they're not represented by numbers of apples, absolutely, and without having to picture exactly what it is. And these arrows on a plane, which can be combined by two operations, tying them on each other's tail and combining them by this multiplying and adding angle business, those two rules, adding and multiplying, obey the same rules as algebra, and these amplitudes are in fact called some kind of numbers by mathematicians, and to distinguish them from ordinary numbers, they call them complex numbers. Makes it hard, in other words. So if for those who have studied 4 years of university, or enough algebra to have come to complex numbers, I could have said all this by simply saying amplitude, the probability is a square of a absolute square of a complex number. The amplitude is a complex number, and the probability is its square, and that when the thing can happen in more than one way, you add the complex numbers, and when it happens in succession, you multiply the complex numbers. And have I said any more than I did before? No. It's just a different language, and it maybe sound better, and the only reason I use that different language is because some few of you may have heard of that language, and it would be nice to make sure, I just wanted to make sure to you that it was really the same thing. For those who have never heard of it before, the idea that that is multiplication may be disturbing, and I think I waste a little time on the side. It has nothing to do with, well, I think I'd waste time. I'm late, so I shouldn't waste time. I wanted to explain why it's reasonable. I can't resist. I want to explain why that is a reasonable way to define multiplication. This is a stupid thing. It has nothing to do with our lecture. I call it multiplication. That's enough, but I have to play anyway. What is multiplication? And the Greeks wanted to use numbers that were not necessarily integers, and they did it by talking about lines. If this is a unit, then the line, this length, represented the number 1. Whereas a number like 2 would be represented by a line which would be twice as long. That way you can represent fractions and so forth. The third is long, 2.5 times long, so forth. So here's 1. 2 is the relationship of this line to that. Now 3, you might get, is the relationship of this line to that. All right? I have to write the unit. In order to understand what this number is, I have to tell you how big 1 is. And what's 6? the product of 2 and 3. It's a line also. It's a line. It sticks way out. And it's like so. It's got 6 notches. Oh, it's 6 notches. And the way of looking at it is to say that the problem is this. I want to convert 3 to 6. I want to multiply by 2. The idea is that the 3 line that I had before bears the same relationship to the answer that I'm trying to get, the 6 line, as the 2 bears to the 1. 6 is twice 3 in the sense that this, relative to that, is the same as the 2 to 1. Right? The idea is then that the answer should bear, of multiplication, should bear the same relationship to one of the things you're trying to multiply as the other thing does to the unit. Voila. Let's see. I want to multiply this by that. And what I have to do then is to create a line which bears the same relationship to this line as this one does to that. Yes? I have to, just like I did over there, I have to find a new answer. It has to have the same relationship to this line as this has to that. Now let us draw the answer that I drew over here, so you can see its relationship to that line. What's the relation of this and this? The relation of this and this is a certain proportion in size and a certain angle. Can you imagine that thing turned so it's in this, and you see that it's the same angle and the same proportion as the original 1/5 to 1. In other words, the relation of this line to that is the same geometrically. And so that's why it's multiplicative, because it has the same geometrical property, a property, though, that fits on lines which are tilted, not just lines which are horizontal. It's interesting, the mathematicians developed all this mathematics for these crazy numbers without having anything to apply it to directly in physics, and that it should turn out to be so fundamental to the bottom laws of physics to be using such funny numbers or complex numbers. So that's the other feature. And I'll just say one more thing to finish this. That means that we can understand what happens in a given situation by a sequence of, as if it's a sequence of events. Instead of, you see, when I was talking before, I would say a thing comes from the source and goes to the photomultiplier, and I gave you the answer for one operation. You turned it and you made a little line. But I can talk about it in several operations. I could say it goes from here to here. You start with an arrow. When it goes from one point to the other, just turn it around according to the time. Reflection. Reflection is a little 1/5 arrow. Multiply by that. That means shrink it down. Next, go from here to here. That means take the result and do again the same next thing, which is rotate. Now, finally, I would like to say, what I'm going about to say is to show you that we have still simpler laws than the ones that I talked about. We have been talking only about one color light and talked about the amplitude depending on the time in that fashion. What is the difference between one color light and another color light? The speed at which that goes around. But in space, light is light is light is light and doesn't know where it came from. And what another picture is, different picture is this. Now, light, if you want to know the amplitude that it arrives at a certain time, I'm going to put time into this argument now. It arrives at a certain time in the photomultiplier. We suppose, well, I think, since I haven't figured out, I'm sorry, this is very amateurish, isn't it? I haven't figured out what I'm going to talk about completely next lecture, and I haven't got quite enough stuff to fill it up. And therefore, I'm going to leave this little thing in the next lecture so I can fill it up. I will tell you what the idea is, that the time has to do with the, well, I'll discuss that the next time. The other thing is, I have tried, and in the case of monochromatic light, I have completely described the rules for the amplitude. If I add one more thing, which I haven't, that is, I have to talk about what happens in a vacuum first. And when a light goes a certain distance, it's true that the angle turns, but there's another rule which I have not discussed because it's not very interesting relatively, and that is that the amplitude to go a certain distance, besides turning, shrinks. If you go far, it gets smaller. Everybody knows that the chance of finding a particle far away from the source goes down as a square of the distance. And that means that the amplitude goes down as the distance. In other words, when I was drawing these arrows, as I made them go further, I should have shortened them a little bit. Those are kind of approximations. They have nothing to do with the excitement of how it works, and I didn't want to bother you with such accurate detail. But if I once tell you that the thing turns at a certain rate and goes down in length proportional to the distance that it went, I have completely defined exactly the properties of the propagation of light of one color, except for one other technical thing. Light, as it turns out, even if you specify the color, I have to say this in order to tell you exactly, how much you know and how much I haven't mentioned. Even if you specify the color of the light, there's one other feature that light can have. There are two kinds of photons with the same color. We say they're polarized. If you use Polaroid, for example, you let through light that has only one kind of axis. And another piece of Polaroid lets through the same kind of photon. But if you set that other piece of Polaroid for its axis the other way, so that it'll pass light with the other kind, then no light will get through, where the first one only passes one kind and the second the other. All these effects of Polaroid and polarization have been entirely left out of this discussion. Why? Because my purpose is to give you a complete feeling of the difficulty of the subject, of the interesting philosophical problems about probability, the succession of amplitudes, how little we really understand, and so on. And the fact that there's two different kinds of photons is not qualitatively different. It just means a little bit more calculation, but of the same style. It doesn't change the style of the analysis. And therefore, in spite of the fact that I've left out a number of things, such as how the amplitude changes with distance, and the fact that there's polarization, makes my lecture incomplete in the sense that I therefore have not given you the exact law for the propagation of light. Not quite, but damn close. So close that it contains all the mysteries, all the peculiarities, and so forth in a perfectly satisfactory way. And I hope then that you're satisfied and you're confident that I haven't left any essential difficulty out. The things I've left out are not difficult. They take just another lecture of technical points rather than any new difficulty. One thing, though, I must say, and that is this. We've been talking about light going through a vacuum, and then I had a rule about it's reflected by a certain amount when it goes. It has a certain shrinkage when it comes off a surface. When it goes through a medium, it gets slowed up, and so on. These, it turns out, are not really the properties of light. They have to do with the properties of matter. You can't get reflection without having a piece of glass. It doesn't go slower unless it's in the glass. It really, as it turns out, is not going slower. It's curious, and we're going to find out exactly what it does. In order to explain it, we have to know what the electrons in the glass are doing and how they interact with the light. And I'll summarize the most wonderful fact is that light never does anything, really, when you get down to it, except to go in a vacuum from one place to the other. It's emitted by one atom or particle and absorbed by another. And it never goes and gets slowed down or gets reflected. What reflection really is the light goes down, is absorbed by something, which shakes it, and that emits a new light, which comes back. Reflected light is really not the same photon coming back as went in. The photon from the source went into the glass, and from the glass comes out a new photon. This is an interesting thing that makes light in the end simpler and simpler and simpler. And what I was trying to get to in the last steps was to show you how ultimately simple it is when it's only in a vacuum. And the complications of funny laws for reflection and funny laws for going through glass are really the result of the interaction of light and electrons. And that's why this subject of discussing physics can't go on any further until I can discuss matter. And the next lecture will be about matter. All right? Thank you.
I put together a theory about photons and electrons, and I took it to my physics teacher, who said it's not right.
Now, since he didn't describe the theory with great detail, I cannot answer, but I will say something that I forgot to say in the lecture. One has the advantage of using questions to finish the lecture. I really had, I must emphasize something that is a very great danger of talking about what happens in an experiment with one photon. Because after a while, you get the idea that these arrows are somehow associated with a single photon. It's a mistake, and I should have not permitted that mistake to be generated by mentioning as early as possible that it's not right, and that one of these amplitudes are not the amplitude to find a photon riding around somewhere, but the amplitude that an event occurs. And I give an example why your professor probably said no, by giving you a problem, so to speak, of the kind that we answer with these amplitudes, which is of a different style than the ones I've been mentioning, and requires more thought. And I would just at least, as I say, I don't know exactly what your theory is, and maybe it's okay to satisfy this example, but nevertheless, let me know next time. The idea is, suppose that we have a problem with two photons. Suppose that we would like to know, just to take a definite example, that we have two sources of light. Each one has been arranged to two sources A and B, and it's been arranged that both A and B emit one photon under some circumstance, and you have two counters down here, two photomultipliers, and you would like to know what is the probability they both go off. All right? So the event whose probability you're computing is the probability they both go off at the same time. If this both emit, but there's a coincidence that they both go off at the same time. Now this has an amplitude, the amplitude for the two photons, so to speak. In one, there's only one amplitude, the amplitude that both go off. And I should have emphasized that no matter what the event, no matter how many you're involved with and so on, we talk about the complete event and calculate the probability of it, not the probability for each photon. Now in this case, to compute the amplitude for a photon, to both counters to go off, supposing that one photon came from each of the sources, it has to be done as follows. One way it could happen would be that this A source gave a photon that went off, and the B one gave a photon that made the other counter go off. Let's say this counter is called X, and this one's called Y. X went off because it received a photon from A, and Y went off at the same time because it simultaneously received a photon from B. The net result of the experiment is that both A and B have lost some energy, and the two counters went off at the same time. How do I compute that amplitude? Answer. You compute the amplitude that A would reach X, some arrow. That's the amplitude A would reach X. You compute the amplitude that B would reach Y, another arrow. Actually very similar in this particular example because of the symmetry of the picture, but it's not relevant. What is the amplitude corresponding to the thing that both should happen? You can get a hint. Well, what the answer is the product of these two amplitudes in the same sense that I talked about before, multiplying. You're going to get an idea of why it's multiplied in this sense because of this. It helps a little bit. The time, if there's a certain chance that this reaches here, like 1/5 of them will reach here, and 1/9 of them will reach here, then the probability that they both reach is the product, and you've got to get that back into the amplitudes, and it's a clue. At any rate, you should multiply the amplitudes not only of things that happen in succession, but things that happen independently at the same time. This particular problem is especially interesting. Let's suppose when I multiplied these two, by the rules I'm talking about over there, I get add the angles and multiply the lengths. I get this answer. That's not the right answer for this problem, incidentally, and curiously, because there's another way it can happen. You're all sitting there saying, well, how the hell did I know that it wasn't A that went to Y and B that went to X? Well, if I say that this was, remember, this one was A to X, and that was B to Y. Now, if I say A to Y, that's a different arrow. Why? Because it's a longer and therefore different time, and therefore this particular arrow is turned more. And likewise, B to Y is turned more. I'm not drawing them correctly because there's a symmetry. There's a similar arrow. At any rate, the net result for that case is some other arrow for the other case. Now, what do you do when there's two possibilities? If a thing can happen more than one way, you add the amplitudes for the two ways. And the net result for this problem is to tie one of these arrows onto the other, and that's the answer, the length of that. And now what we have is something which is all the elementary textbooks say is impossible, interference between two photons. Or more correctly, you get pluses and minuses depending on the angle, strengthenings and weakenings, depending on the positions of these two counters relative to each other. This is used, as a matter of fact, and was invented, I think, locally. Perhaps not in New Zealand, but at least in Australia. To detect the diameter of stellar objects or quasars and things like that, by looking for radio waves received in two receivers and looking for correlations of strength, which just means a coincidence of photons. It's called the Brown twist effect. But it's a perfectly definite effect that's understandable and computable this way. Most people's theories, who have a theory about waves associated with photons, will not have a theory which is capable of dealing with situations where there's more than one photon. I do not know that your theory is incapable. I only suggest that as an interesting problem.
How old is this theory of quantum electrodynamics?
Present complete form is from 1948 or 78, 9, 78. Therefore, it's 30 years old. That's what the subject of these lectures is. As you see, the reason it's so difficult to filter down is the resistance of your mind to such models. People who hear that all I'm going to do is make a couple of arrows on a board to calculate the chance that something happens, says this guy doesn't know physics. But this is the guy who knows that that's what you have to do, and admits, therefore, that he doesn't know why he's doing what he does. And you can have the confidence that when I say I don't know what I'm doing, that probably nobody else does either.
In what way is your theory different from wave mechanics?
The question is whether how is this related to wave mechanics? Now, the reason I hesitate is there was a thing called wave mechanics, which is the quantum theory of wave theory. And there's also another sense in which we might be using the word the mechanics of waves, by that meaning water waves or sound waves or something like that. There's a special theory called wave mechanics, which is discovered and developed in 1926, which is just another name for quantum mechanics. And there was two things. First, there was an equation for these waves, these matter waves, made by Schrödinger. And then there was an interpretation of these equations by Max Born within the year, which was that the function that we're talking about is a complex number whose square is a probability. I am saying no more than that at all. That's exactly it. The only thing I can add that for the 20 years after is merely a refinement or an improvement in discovering exactly how to calculate the wave amplitudes, or these numbers, these arrow amplitudes, for photon phenomena and electrical phenomena of high energy and so on. The complete formulas for quantum electrodynamics took 20 years to get straightened out exactly, and that was why I said 1949. But 99%, well, 97% of the thing was worked out in 1929, and the interpretational scheme about probability amplitudes, and that you square them to get probabilities, which is so strange, is the resolution, shall we say, or a description, a precise description of what was, for a while, a confused wave-particle duality. You might say, but you still have a sort of a wave in the sense of something turning or oscillating, and the particle somehow in the sense of the particle going. So it's still a duality, but the words wave-particle duality is a description of a condition of the minds of physicists before 1926, in which it was best described as saying, it looks exactly like a wave, but that's on Thursdays. And it looks exactly like a particle, but that's on Tuesdays. But the answer is it does not look exactly like an ordinary particle bullet with normal probabilities. And it does not look exactly like ordinary waves, because it ends up that you measure it in particles. And how to put that together? Answer is the way it looks.
Then in your own mind, do you think you have resolved this peculiar duality?
Not at all. I haven't done anything, but the wave-particle duality represented a state of confusion. It was a word that there was a wave-particle duality. It was a phrase used to describe a state of confusion as to exactly what law to use to figure out what happened in each circumstance. Also a confusion of model, whether it's wave or particle. This thing, the final way out, worked out by Born, 1926, it's still got dual aspects of wave and particle, but it's precise in telling what to do and to predict the circumstances in any experiment. And there's an agreement with nature's experiment. And so it's a resolution of the confusion, but it is not a resolution in the sense of producing a model which is clear, physical, in the old-fashioned sense of waves or particles.
Other clicks from a photomultiplier caused by the photomultiplier and in no way related to light.
The question is, when a photomultiplier makes clicks, is it the photomultiplier itself that's making the clicks, or is it light? And the answer is, it's light, in the sense. And insofar as it's actually quite true that photomultipliers make clicks all by themselves in circumstances in which we've done everything we can to make it as dark as possible. In other words, it's dark, and there is no light. Various things this because it's so extremely sensitive, and one can do things to the photomultiplier to improve it, such as cooling the cesium surfaces so they don't emit spontaneous electrons and so on, until we get an instrument, the idealized photomultiplier, which is better and better in the sense that it has less and less counting in the dark. But whether it has counting in the dark or not, when you change the circumstances, that in normal parlance, in ordinary language, we'd say light is coming in the sense that the sun was shining, but we put a whole lot of black paper around it, and we got a lowest count. Make a hole in the paper, and all of a sudden the counts go up. In all those circumstances in which we would expect in ordinary language to say light is going in, and in all those circumstances the counts on the photomultiplier are increased. And the increase is by an amount that depends upon how much light is let in. The increase. If you improve the photomultiplier so the dark current is much less, you get the same number of excess counts due to making holes in the black paper. Because the circumstances in which the photomultiplier increases its count are those which are commonly associated with circumstances in which the common English use of the word light is used, we use the same word and say, when you have a situation that you would say light's going in, I'll guarantee you the photomultiplier will go off.
Is light then wave-like?
No, it's discrete. It always works discretely. Ah, yes, discrete. Because no other instrument has ever been designed or can be designed, as people have tried and they've argued about it and discussed it, whether I build a photomultiplier or any other instrument for the detection of light of low intensity, it always ultimately behaves in this pulse-like manner. I only use one example, but every instrument that detects light at sufficiently low intensity always ends up discovering that light comes in these lumps. Also, the behavior of light in many other circumstances, like in in hot regions and so on, Planck discovered that he could not understand that many of the properties of the distribution of light from furnaces and so forth and other technical situations unless the energy of the light could not come in arbitrary amounts, small amounts like the wave theory expected, but had to come in definite lumps of a certain amount of energy depending on the color. And so it's all this, not just a photomultiplier, but all the other experimental situations and so forth, which it's impossible in a popular lecture without 4 years of study to produce and to demonstrate again and again all these experiments to produce the kind of conviction which one would get from a long experience. It's unfair of me to say you've got to believe me because there are all these experiments, but the best I can do then is to refer you to other books and stuff where experiments are reported of all kinds, which will show you that that's the way it looks. That's the best I can do.
Can your theory explain the redshift or blue shift of light from stars?
Yes. Yes, and that was a point that I was coming to, but I'll try to, because of the time, I guarantee you, if you promise to come next time, which is next Tuesday, I will contain it. I had intended to put it in this lecture, but I saw that was one of the things I was coming to. The idea is relatively simple, and I'll try to explain it. The color of light has to do with the speed at which that amplitude turns around. I never talked about how the detector would look, where the photomultiplier would see if it was moving toward the source. But what happens is that the time that we're talking about to get the amplitude is always shorter as it approaches the source. And because of this changing timing from the motion on top of the rotating, it appears as if the arrow effectively at this multiplier is turning at a different rate. And that is equivalent to what would have happened to the multiplier if it's standing still, but the light source had a different color. And therefore, the behavior of an instrument which is moving toward a source is to react as though the source was standing still, or the object was standing still, but the color were bluer. All right? It's not very clear, but I'll perhaps make it better next time.
Right, well, we must make a break there. I'm sure Professor Feynman needs all the time he can to get his next lecture.
I guess I'm not used to the kind of politeness you have in New Zealand, because in America, the audience is decreased each time, so let's end up just going to 4 or 5 people. But I'll try to make it not so painful. We've been talking about or what we're aiming to talk about is the theory that works the best, that we know the physicists like the best, and that deals with a part of nature, and that's quantum electrodynamics, and deals with photons and electrons. Most of the time we've been talking about photons. What we've discussed is that mainly the main idea of the talk is to give you some idea of the kind of framework of ideas which theoretical physics needs in order to describe results of experiments. And I think by this time you'll agree, after 2 lectures, that they're very weird indeed, and quite peculiar and difficult to believe. But I'll just remind you or review for one more time a little bit about what happens with photons. And as we've said many times, 2 times before, we have a source here, and the photomultiplier, which makes counts of photons, even if we have only 1 photon at a time, and if we have more than one way that a thing can happen. And the example I've been making several times is that the light the photon we could imagine could be reflected from 2 different surfaces. If there's more than one possible way that something can happen, the whole structure works as this way. In any situation where you have experiment looking at something microscopic, which of course you have in the end to look at something macroscopic that is large, and the photomultiplier amplifies up. When you have a system like that, you can't predict exactly what will happen, but only the chance that the system operates, that you find something happen here. And this probability is always given as the square, or the circle to it, of a thing called an amplitude. And this amplitude is a kind of absolute square. It's a special kind of it's the square of the length. And the amplitude is nothing but an arrow drawn on a plane. Now, when something can happen in more than one way, the amplitude that it happens is calculated by adding the amplitude for it happening one way plus the amplitude that it happens the other way. And when you square that, you get the probability. In a problem like this, we have found that the circumstances or the probability for this event might depend upon how far apart you put the plates, and you get reflection from a pair of plates which varies with the thickness in that manner. And so, this, in our particular example, I finally found out that that was 16% and that was 8%. From each surface, there was 4%. Now, if this were a more ordinary thing, like you would expect, an ordinary type of reasoning instead of this esoteric subject of microscopic physics, you would expect that the chance to arrive here could be analyzed by saying, of all of the ones that come down, some bounce from here with a certain probability, and some bounce from here with a certain probability. Let's say 1/5 bounce here, or what do we say, 1/25. And 1/25 here would be 2/25 of them. What we would do would be to add the probabilities. We find out that instead of adding probabilities in such logical circumstances, we add amplitude. In other words, we can sit around and talk about it this way. You say, well, there's a certain, it can go either this way or it can go that way. And we just add the amplitude before we split. But that means that the logic that we can say that it really goes either this way or that way is false. You can't really say that in the common language way, or you're meant to add the probabilities. Because if you were to say it can either go this way, some of them come this way, and some of them come that way, you're at a total loss to understand why, when the thickness is just right, there are none of them come at all. Because if some of them come one way and some of them come in the other way, the fact that they can go both ways surely isn't going to make it that they don't come at all. But that's exactly what does happen. And so the idea to be able to say that it comes either one way or another, it requires that you know what you're talking about. You're not talking about ordinary either one or the other, but either one or the other in the sense of adding amplitude. So it's a crazy game. I still find myself saying, well, it comes either one way or the other. But it is not really true that for a given particle which arrives here, you can say that it either came this way or that way. You get the sensible physical idea out of that. As a matter of fact, it's entertaining. The following thing is very interesting. It is possible to put some kind of atoms on the surface here, such that when light bounces off it, they leave some trace, that the atom is left in some other state than it was before. So that if it bounced the light from the surface, an atom on that surface would be left in a different state. Likewise, we can put atoms of this kind. It's rather technically difficult with light, but you can do it in many, many analogous experiments in similar situations. Well, imagine we can do that with this. And then we could say, let us bounce the light, and then afterwards look at the atoms and see which ones are excited. What you discover is, if you have enough here, that you don't miss them. But you forget the cases where you miss. That it's either excited here or it is excited there, yes. In other words, it does look like the photon either goes this way or that way. And when you have the atoms here and you count just those cases in which you can find, you see, I'm worried about the cases where you miss them. Forget the cases that you miss them. And take only the cases where either one or the other atom is excited on one or the other sheet, and ask for the probability of arriving here. And you know what you get as a result of the function of thickness? A completely different result. If you have atoms there that can leave a trail as to whether light was there or not, you get 8% reflection no matter what thickness. In other words, it tricks you. You're going to be clever. You know that if you have no way to tell from which one it comes, if the light after it bounces off leaves everything the way it was before, then you get this funny interference effect. If, however, you put something here to see if the light bounced here or here, you can tell it bounced one or the other. It tells you, it leaves the atoms excited. But lo, there's no more interference effect. Why? How do we describe that? It's not hard. It's that we changed the problem. The first problem was, given a source here and material here, what is the probability that for the following event, that the photomultiplier goes off and that the system is left exactly as it was before, that nothing is changed in the glass? That's that curve, the first one. But in the second experiment, we're asking for a different final problem. We're asking a different problem. The problem is, what is the chance, if we have a source here and these layers here, that the photomultiplier goes off and one of these atoms on this layer here, say, is excited? That's a different problem, has a different amplitude. And that has nothing to do with what happens down here. And that amplitude is 4%, or 0.2 rather. Squared is 4%. It has some darn angle, I don't understand angle. Squared is 4%, and the probability that it's reflected from the front surface as detected by an atom there is 4%. Likewise, if you ask for the following situation, that the photomultiplier should go off and the bottom one should have an atom excited, you get also 4%. So you see, if we try to test whether or not it's going one way or the other, then the results of the experiment are changed, or another way, we have to ask about a different experiment. The case of interference is this, that it is such a situation that the rest of the system, the glass, is exactly the same before and after, and there's no way to tell where the light bounced. Otherwise, if you had some way to tell, you'd ask for a different physical result, have a different amplitude and different results. Which means these things I point out because as you've gone along, you've probably struggled to find some kind of a simple-minded explanation of these things. But when you see how annoyingly complicated it gets, I mean not complicated, but curious it gets harder and harder to make a simple model. So we've given up on that. I also emphasized last time that you can get some that one of the things I wanted to emphasize is that things that are very common and observed all the time and which are perfectly obvious are quite different in this world. It turns out that what we thought was obvious is quite wrong and it's much more complicated. Or not more complicated, but just different. In fact, it's sometimes simpler and more beautiful. A particular example we had was that light was reflected by a mirror at equal angles, or that light went in a straight line, and we demonstrated that mysteriously enough, was the consequence of light going every which way, and not necessarily in a straight line. In particular, I pointed out that if we had a mirror which was made of little pieces of the right spacing, and had light coming down this way, it's reflected back that way sometimes, but it has a good probability to be reflected at a special angle. That's crazy. That depends on the spacing here. I have been using light, and we've been using red and blue light. When we change the color of the light, the distance changes, but I have explained in the first lecture that the range of conditions is enormous, and that we can have distances corresponding to hundreds of meters for radio waves, and distances corresponding to spacing between atoms, or even much smaller for other rays. In fact, if these little spots were instead of mirror pieces, just atoms, which are much closer together, very close together, then it's possible to find photons of such short wavelengths, much smaller than light. This distance is about 10,000 atoms, the thickness there, but here one atom. And when you have light of the wavelength of one atom, it's called X-rays. And when you shine X-rays on a crystal, which is where all the atoms organize this nice pattern, say a crystal of nickel or some other metal, you'll find X-rays coming off at special angles. That was discovered in 1914 and was the proof, they said, that X-rays were waves, but at the time, all the other evidence indicated X-rays were particles, and we now know, you all know about this puzzle. At the same time, this was very exciting because it not only determined the wavelength, so to speak, for X-rays, it showed they were the same as light, but much smaller wavelengths, but also much quicker variation in time of the amplitude. The amplitude changes slowly with red, faster with blue, super fast with X-rays, super fast with gamma rays, and so on. And not only did that, but by the way, incidentally, by measuring these angles, you could determine the spacing and arrangement of the atoms in crystals, and that's how we've gotten to understand how the atoms are packed in various kinds of substances and so on, which is exciting and interesting all by itself. But I'm wasting time because the lecture's on electrons, and I've been talking about photons. But what I wanted to emphasize was the structure. The structure is amplitudes. We get to talk about them all the time. Only later at the end we square them to find probabilities. Amplitudes add when you have different possibilities. We also taught that amplitudes will multiply when the things happen in succession. In fact, amplitudes multiply just like probabilities multiply, and under the same circumstances. If you had, we could analyze this another way. We can say there's a certain, if this were really a chance thing, we say there's a chance it gets from here to here, and a chance it bounces off, and a chance it gets from here to here. It turns out that that's right. You can analyze the amplitudes the same way. There's an amplitude to go from here to here, an amplitude to be reflected, and an amplitude to go from there to there, and you multiply them all together, just like you multiply probabilities. Multiplying, I explained last time, multiplying two arrows is done in the following magical way. You have two arrows, and you make a new arrow whose length is the product of the lengths of these two, and whose angle from horizontal is the sum of these two angles. So in this case, the product, I don't know what the unit, let's say the unit is this big. The product is a small arrow at an angle something like this, which is the sum of the two. Anyway, we find we can add and multiply arrows. The mathematicians call them amplitudes, and mathematicians call them complex numbers, and that's the structure of the world. Electrons were discovered in about 1895 or so as particles, and they were studied and believed to be particles. They behave very much like particles. You could count them. You could put one of them on an oil drop and measure the electrical charge. Electrons responded to the presence of other electrons. If you had a metal plate here and a metal plate here and had an excess of electrons here and a defect so that what's left over is protons here, then an electron sailing through between the plates would be repelled from the other electrons and attracted to the protons and move in a curve something like this. Millions of electrons moving through a wire represent an electric current, and so on, and so on. And the entire picture of electrons as particles going around in matter explained many phenomena, and everything was going along all right. There were some puzzles about how they behaved in an atom. If you've heard about the atom as being a little solar system with a nucleus in the center like the sun and the planets going around like electrons, then you're back in 1900 and something, 1910 or so, because it's quantum mechanical, as it turned out. By 1923, de Broglie suggested that this business about mixture, this wave and particle properties like light, was probably also true of electrons. You know, historically, the wave part, aside from Newton's era, the wave aspect of light was most obvious, and the particle aspect was discovered afterwards. In the case of electrons, the particle aspect was most obvious, and the wave aspect was discovered afterwards. By almost in 1924, only a short time after de Broglie's suggestion, Davison and Germer were doing some experiments bouncing electrons off of nickel, expecting them to bounce back this way, which they did. But they also discovered that some of the electrons went off on a crazy angle. And when they read de Broglie's paper, I can't pronounce it. Sometimes they call it de Broglie, and sometimes de Broglie, and sometimes de Broglie. It's a French name, so it's hopeless. And they found that these electrons came off at an angle, and that they calculated the angle, what the wavelength had to be, because you know the spacing of that from the experiments with X-rays. They found out that that was exactly right, according to de Broglie's theory, and that electrons, in fact, did the same thing as light in the same kind of dual hocus-pocus. In translating the words dual hocus-pocus into better English or better physics, it's this: that even an experiment involving electrons going from one source, say a tungsten filament, to a counter of some kind, is exactly analogous to the situation with light. In fact, all of physics, as it turns out, as far as we can tell, is all the same framework. There's a probability for an event, and the probability is the square of an amplitude. And there's an amplitude that an electron goes from place to place. The amplitudes can be compounded by addition when there's more than one way to happen, and by multiplication when you can think of things happening in succession. That means that all the possible events in the world might be analyzable into separate, simple events of which everything is a compound. For instance, is it possible to describe, like, everything that happens as a series of events? For instance, it jumps, it goes from here to here, it bounces off, it goes from here to here, and so on. I'll give a specific instance in a minute. What does turn out to be true, and this is what the content of the present lecture, is I want to start all over again and tell you, now that I've introduced and I've convinced you about the framework of probability amplitudes, I must give you the laws for the probability amplitudes, and that way give you the complete theory of quantum electrodynamics. it turns out there are only 3 laws, okay? But they have to do with the idea an amplitude that an photon goes from place to place, an amplitude that an electron goes from place to place, and an amplitude that an electron emits a photon. I'll describe them in detail now. Now I would like to give a more complete description of the way the laws of physics look, at least in this partial realm involving only electrons and photons. In order to give this description, I have to include something which I didn't include before. For simplicity, I include now the time. In the experiment which, here it is. In the experiment which I thought I had just erased but didn't, we can ask another question. We can ask if the source is made to emit a photon at a given moment, what is the probability that the counter receives a count or goes off at a given moment? This adds the idea of time to the things that we've been doing before. We can ask a question that's, in other words, more complete, not only where the thing is and at what time it arrives. And so we have the following world. We have an amplitude inside of space-time, space and time. Things move around in space, and they take time to do so. They don't really move. They have amplitudes for doing their thing, okay? But their thing is done in space and time. You can ask for the amplitude that a photon arrives here at a certain time and an electron is somewhere else at another time, and so forth. Now, in order to describe both the space and the time pictures, I'm going to make a kind of graph which we call, which is very handy. If I call it by its name, you'll be frightened. So I'm not going to call it by its name. I plot the position in space sideways here and the time this way. And I'm going to explain what such a diagram is by taking the old-fashioned world first, not the quantum world, and see what happens. So we take a baseball. It's standing still here. What does it look like on this picture? The space is supposed to be represented this way. Of course, we know space has more dimensions, but I don't have to draw them. I draw one out this way for the other dimension space, and a third one at right angles to both of these and this for the third direction of space. Now, if I represent the baseball by a little plot here, at a given moment, there's the baseball. Later on, the baseball is in the same place. So later on means go along this way. Then later on, the baseball is here. That's the width of the baseball, okay? And later on, the baseball here and so forth. Why did I bother to make it a wide baseball? I don't know. And so here, I could have made it a point baseball and made it easier to draw. The baseball, as a function of time on this diagram, will be represented by that band, all right? Now, if a baseball is moving, okay, it's drifting across the room, what does it look like? This time, I'm going to make a very much smaller baseball, okay? Or you're so far away you can't see the sizes. Let's say it's here now. Later on, it's in another place here, and later on, it's another place here, another place here. So in this world, it'll go so. If it's coasting at a uniform speed, it'll be a straight line. If the baseball goes for a while, hits something and comes back, then it'll go something like this. There was something standing here, right? And it bounces back. Let's say this was a brick which was standing still. And that would be a picture of a ball hitting a wall. It goes boink, boink. And I stretch that out this way. Another way to, well, that's, I think, a pretty clear picture. And this we represent situations in space-time. So if I would do in space and time, which I've inadvertently called space-time, which is what everybody calls it. Now, we could say, for instance, that at this particular place, we had a source which emitted a photon at a certain time. This is the time, and this is the place. Then later we can ask if at this place, a detector at that time would discover a photon. Now, if photons were baseballs, we could say, well, maybe the photon went straight along here, or what have you. But we don't have to say we don't know anything about how it goes, but you know what the answer is going to be. There's going to be an amplitude, that a photon let out of here arrives here. And that amplitude will depend upon the time of this one and the position, and the time of this one and the position. And I'll call this point for just a moment number 1 point, and this a number 2 point. And then we have a thing which is called the amplitude for a photon to go from, well, 2 from 1. And that's one of the great fundamental laws of nature, what that formula is for that. It's a little mathematical formula, and it's very simple. I do not want to bother you with exact mathematical expressions because it won't mean anything. It's easy to describe for those who are more sophisticated. Of course, you realize immediately that this formula for this is going to depend only on the difference of the time and on how far you had to move, the difference of the distances. So it's not so complicated. If the difference of the time is t and the difference of the distances is x, then the answer for this thing is this function, but I don't want to bother you with the mathematical thing. Only know that I can write it down in 1 second, and people who know this magic, this mysterious language, know what that means. So that this formula is extremely simple. It's as elementary as it can be. Oh, it really is as elementary as it can be, as it turns out. If we added a couple of principles, then you can deduce what it has to be, knowing nothing except those principles. The principles are as follows. There's a knowledge of the relation of space and time. The way things depend on time and the way things depend on space are interconnected by a law, which is the principle of relativity. And that tells us a great deal, limits the functions a great deal. The second proposition is that the probabilities that you get from this must have the property that if you add up the probability of every possible event, you get 100%. And if you make a wrong formula here, it doesn't check. You know, the probability of everything all added together has to be every possibility, which is 100%. Something's got to happen, in other words. And if you get the wrong formula, it doesn't come out right. You find out that the probability of something happens is 1.5, or -2, or something. So adding relativity and that principle determines this almost completely. Not quite completely. I'll tell you a little more about it in a minute. This function, this depends on these two things. Just for the sake of this discussion, I'll call it D, say. Why D? P, for photon. P is for photon. Between 2 and 1. It's an amplitude of a certain size that depends on the distance between the two. You might at first be surprised because when we were dealing with photons over there, we said that the amplitude was rotating and depended on the time by going around proportional to the time, depending on the color of the photon. Nothing has been said about the color of the photon over there. Something's wrong. No, it turns out as follows. I will explain it better later. The color of a photon is a result of the source. The source emitting has an amplitude to emit the photon, which is a function of time which is going around. When an amplitude for an event changes with time by simply rotating, not changing its length, but by changing its angle, it corresponds in the real world, I mean the world you're used to, the ordinary world, to be a situation in which the energy of the system is definite. And what we've been talking about before were situations in which the color of the photon, the energy of the photon, was definite. And in those situations, the amplitude is turning around in time. This is, in fact, a result of the source. When we go back to discuss things as a function of time, and all photons are exactly the same, there's only one kind. If the amplitude varies slowly, it appears to his eyes a red photon. If the amplitude varies very rapidly, it's an X-ray. It's all the same. It's just one thing. There's only one kind of a photon when you cut the time. So you see, when you discuss it in time also. So you see that things are getting simpler. To represent that a photon has gone from 1 to 2, we represent that by a wiggly line for no good reason. To represent a photon going from 1 to 2. Now the next thing we have to do, that's the first law of physics. The second law of physics, that's all about optics. That's the entire theory of light. It is. It really is. The part that's not in it is how the light interacts with matter, and I'm coming to that. Next law. That has to do with electrons. Oh, I did cheat a little bit. Yes, wait. I told you about polarization of photons, which I've left out here. It also turns out that electron has two states of polarization too, which is sometimes called spin states. And again, I'm going to leave them out because they don't add anything to the ideas. They just add a little complication to the formulas, which you're not going to work with right now anyway. So if you want them, I'll tell you the exact laws, but this is very close. With electrons, we have a similar situation. I just draw the same diagram because I used up my paper and I rolled it away. But if this was time and this was space, we can ask the following thing. If the electron is known to be started here at a position in time which I call 1, it has a certain amplitude to arrive at another position in time, 2. It then will go from 1 to 2, which I'll draw with a straight line to distinguish it from the photon case. And we need a formula for the amplitude for an electron to go to 2 from 1. And that's a different function of the 2. That is a number that depends on the 2. And I'm going to write it down here. No, it turns out a little harder to write that one. It turns out that that one involves not only the time and the x, but also another number in this formula. It's more complicated than this. And that other number is a characteristic of the electron. It's called its mass. And I'll tell you in a moment a little more about it. In other words, this thing really depends on the position 2, the position 1, and the number m, e, the mass of an electron at rest. Mass of an electron. If you put the right number in for that, then that's this thing for electrons. If you put 0 in for that, that's a photon. That's this one. That's D. And as we'll see, for every known particle that we hope in the end, for every point-like particle that behaves like a point, it's got to be this way with some m. You can deduce that alone, this formula for this thing, from relativity and this business about the probabilities adding to 1. The only possible function is a particular one here, which I haven't written down, but I write it symbolically. It's an arrow, which is the amplitude, a complex number, which depends upon the 2 positions, and on some number. In the case of an electron, that's a particular numerical value. Now, it would be nice for me to finish the job and write down the formula for that thing, but I can't make it understandable to you, because unless you have some more enough mathematical background to appreciate Bessel functions. So, but I will tell you a little bit about the function. A special example. A special example, in fact, of the use of such a thing. Suppose that we have a situation where we know at the present moment, time is this way as usual, and space is that way. We know at the given instant that the electron is equal amplitude, exactly the same amplitude, to be everywhere in space. Then the question is, with what amplitude will I find it at this particular place later? Answer. It might have been here, and then it would go to there. Or it might have been here, and then it would go to there. Or it might have been here, and then so on and so on. So what you do is you take for each one of these places, for these 2 points, the value of this E, and then for these 2 points, the value of E, and you add them all together, because those are all alternatives. It might be here, and so on. I could write it this way. The amplitude to arrive at point 2 from places 1, which are all different values of x at a particular time t1, we'll call this t1. This is mathematically complicated and frightening. But all I'm saying here is exactly, perhaps I better not say it this way. What you do is you take the amplitude to go from every one of these points to here and calculate it. Add it together. In other words, you add this thing for a given time, but all different places. And then the answer is very simple. The answer is simply an amplitude of a certain of a unit length whose phase, whose angle here, goes around depending on how much time it's been from here to here. Sounds familiar, but it's not a photon. And the rate at which it goes around is very high. It's something like 1 point some odd times 10 to the 20th. That's 130 million oscillations a second. All right? But that time, the speed at which this is going around, if you change this time, is characteristic of the electron and measures its mass. Furthermore, it's pretty obvious that the amplitude to arrive at any other point is exactly the same, because it had all the same amplitudes back here, and if I started with another point here and drew all those arrows and everything, it would be the same picture. So the amplitude to arrive everywhere is again the same, but has a different angle. So if the amplitude to be everywhere in space is exactly constant, the amplitude to be everywhere in space stays constant, but changes its angle only. At a rate depends on the mass. A particle whose amplitude is the same to be everywhere in space, it corresponds to a particle at rest, stationary, in the normal parlance. Also, I told you, when an amplitude is such that all it does, it doesn't change anything except in time by changing the angle, it's a state of constant and fixed energy. An electron at rest has a definite energy, which is called its mc square, I think. It's mass times the speed of light. I've taken the speed of light to be 1 in the units I'm using, so that this just goes around depending on the mass. If I had had a heavier particle, the situation would be the same. I put a different number in here, but it'd just be that this amplitude would rotate faster in that case. Anyway, there's a simple example of one of the properties of this function, which is very, very simple. As a matter of fact, if you're clever enough, you can deduce from this, plus the principle of relativity, what that function was, but you're not that clever, so we'll let it go. But I'm just trying to emphasize that the particular function, although I haven't written it down exactly, is as simple almost as it can be. Finally, there's one more rule, and that is that if an electron comes to a point at the same with a photon, they come together at a point, an electron and a photon, that an electron can go off from there. It's possible to have a junction. And there's an amplitude that there's a junction. The amplitude that a photon is absorbed by the electron, let's say. Or whatever kind of a junction is that. We can talk about what the junctions mean. But every time you see a junction, you get an amplitude. That amplitude is given by a formula. C is equal to 0.08542, and so on. A number, just a number. 1 times it. Physicists like to remember this number in the form 1 over c squared. And they write c squared is 137.03599 plus or minus 3, and that's the result of an experiment. That's a magical number, a mysterious number. Good theoretical physicists put that at the top of their bed at night and dream if they can figure out why that's the right number. The fact that we have no idea where that number comes from, and it's one of the mysteries and incompletenesses of the theory, because it would be nice to get that number out of something. It's done by experiment. I'll discuss that problem in much more detail in the next lecture when I talk about the limitations or the incompletenesses of the theory, and also other particles in nature and all the other problems of physics more complete, not just electrodynamics. Well, now let's see. We have just these parts, and I would like to discuss calculating the amplitude for a number of different events so that you can see what's involved. So the first example will be this. Suppose that I have 2 electrons, again time this way, space this way, and so on. I have an electron, I know its state at position 1, and time, the position time 1, Mach 1 here, and another one at 2. And I would like to know whether at a later time I will find one electron here, well, let's not put it in the same place, and another electron, say, there. All right? So one electron should be at 3, and the other at 4. Now, to find out how to do it, the first thing I do is I suppose that the electron number 1 went to 3, and the electron number 2 went to 4. So I draw a picture like that. And I read the picture mathematically as follows, that amplitude for this event is the product, as we talked, because these are two independent things. There's one factor, which is the amplitude that this gets from here to here, which is just that E thing, which is some arrow. And there's an amplitude to get from here to here. If I were writing it mathematically, I'd write E31 times E42. But what I would mean is, I get from the formula the size of the arrow here, and then I'd multiply it by the size of this arrow, and that would be the answer. But that's not the complete and exact answer, because there's another possibility. So I must consider other possibilities that can occur. Another possibility is that it was this electron that went to there. I'm just drawing the same picture over again, but making a recombination. This is 1, this is 2, this is 3 and 4, and the amplitude for this one would be E3 from 2, E4 from 1. And from what you've learned last time about photons, if it can happen in two different ways, you add the amplitude. But for electrons, there's a different rule. When it can happen in two different ways for electrons, you subtract the amplitude. This subtraction has a very profound and remarkable influence on the behavior of electrons, and is the reason why electrons behave more like particles experimentally than like waves when they were first found. I'll come back to that in a little while. Let's forget this for a while and let's talk about just situations like this, that somehow you know it's the same electron going here. This subtraction is extremely interesting. But I'm going to come back to that because I want to concentrate on something else. Well, there's another way that the first thing can happen beside that exchange, and that's this. It could be, here's the particle at 1, and here's the particle at 2, and the particle that goes to 3, and the other one's going to go to 4. Now, I had them going directly. That was the first thing. But you must add an amplitude for every possibility, so we have to keep on going and adding something. It could be this. Number 1 could go to some place in time and space, which I'll call position time 5. The electron can go to here. Yeah. And then go from 5 to 3 and make a junction here by emitting a photon, and the other one go to the other point where the other end of the photon is 6 and goes to 4. Now, if you're brave enough, I'm going to write the amplitude for this thing in a high-class mathematical fashion, and you'll be able to follow it. The answer to this amplitude for this contribution here is the following. E35, E51 times E46 times E462 times, anybody got another guess? What else is in it? D56. That's a P, photon, 5 to 6. And forgot something, C times C. How's it work? If I haven't made a mistake here, there's the amplitude of the electron goes from 1 to 5, and then an amplitude the electron goes from 5 to 3, times an amplitude that's a junction, that's a C. Likewise here. In addition, there must be some amplitude that the photon that's been liberated at this junction has gone from 5 to 6. You put that in too. You multiply all these together by those rules. I know it's getting complicated, we're piling a lot of stuff together, but it's like playing checkers. There's a few rules, and you just have to use them a lot. You got triple jumps, but they're nothing but single jumps repeated. So it's like each of the thing is simple. It's just repeated and repeated. So we calculate this thing and add it, that amplitude with all its arrows, and multiply to that one up there. Let's forget the other case for a minute. Add it to that and be improved accuracy. It's not quite finished yet. Why? Because, of course, you could have something like this, and so on. I mean, there's all kinds of wonderful things. We'll come to all kinds of wonderful things in a minute. You got two of them going across, and so on. Well, this is a hopeless task. And you got to keep adding and adding and adding and never get finished. But we're going to get a good luck. Good luck. You see, this amplitude has a number of factors in it, but it also has C times C. And C times C is a relatively small number of the order of 1%. And as it turns out, the contributions from a picture like this under ordinary circumstances is about 1% of the contribution of this. The reason I say that under ordinary circumstances, it can happen that you've got a situation where this one is adding a lot of cases and a particular picture cancels out by interference, and then something that's 1% smaller is the whole thing, and so on. Forgetting all about that, each time you add an extra photon, you add a C square, it makes it 1%. So therefore, if I make a picture like that, it's 1% of this one, which is 1% of that one. So by the time I got down to this one, I got things correct to 1 in 10,000. And if I would get to the putting 3 of these darn things across, well, then I got to 1 part in a million, and that's why we can calculate so accurately, because we can do 1, 2, 3. Never can get to 4. It's too complicated. And there's another thing I forgot to say, and that is that where's 5 and where's 6, you're sitting there asking. Anywhere. Yes, anywhere. Those are all possibilities, and those are alternatives. 5 might be here and 6 here, and you have to take that, then you have to put them somewhere else and add them and add it and add it for all different places that 5 and 6 can be. All right? So what I mean to do is to add this together for all places that 5 can be and all places that 6 can be. I mean by its places, positions in space and in time. If 6 is later than 5, you're inclined to say the photon went from 5 to 6. If 5 is later than 6, that is, if I got this around that way, you would say the photon went from 6 to 5. In other words, in one case, this emitted a photon which the other one absorbed, or vice versa, this can emit a photon that absorbs. But it's a funny thing in relativity, it's very difficult to say when two things are nearly at the same time, which is ahead. And this whole business of trying to decide when they're nearly at the same time, which one is emitting the photon and which one is absorbing the photon is in irrelevancy. This function for photons is large when the distance is big, only when these two are at such an angle that you usually can get there at the speed of light. You usually think light goes at the speed of light. You used to think light went in a straight line. Light goes on many different lines, and the result is it looks like a straight line to a gross sense. Light goes at different possible speeds, at different kinds of angles here, and the superposition when the distances are big is that it gives only a result when the speed is at the speed c. So I have now finished telling you, one thing I cheated a little bit in the fact that I left out the polarization. And this junction thing has a whole lot of different numbers, depending upon different polarization cases. It could be one kind, another kind, another kind, different combinations of polarization cases here. And those numbers are those are a little 1, aside from this factor. There's either a 1 or a -1, or sometimes a pure vertical thing like that, or sometimes a pure thing like that. Very, very, very simple. So if I'm going to leave out polarization altogether, I'm not giving you a wrong impression that the junction is just C, this number, times 1. It's not exactly 1. Sometimes it's -1. It's a little different, but that's for different polarization cases. But I don't want to deal with that any further. From that, all the phenomena of nature result. For instance, you know that the light can be scattered. It comes from the sun and is scattered by atoms in the sky, so you see blue sky. How does it work? If we have an electron, well, excuse me, let me go in a slightly different order. I'm going to come back to that case. I stepped on my own cord that time and it choked me. I have now recovered enough to continue. In order to understand the behavior of electrons in atoms, we have to add one other feature, and that is the nucleus. The nucleus is not completely understood. And I will not give you the correct laws for the behavior of nuclei if I could. I wouldn't waste any more time lecturing here, but I would publish it immediately as it is unknown. These functions that we know so well must be the right functions when things behave like points and have no internal structure. And it has turned out experimentally that the electron and the photon have no internal structure to as small as we've been able to look so far experimentally, and that is to distances which is 10 to the minus 15 centimeters, approximately 10 million, 1/10 millionth of the size of an atom. Small enough. So it looks like a point. But the nucleus doesn't look like a point. But for many, many phenomena in atoms, you can approximate by supposing the nucleus is a point. And insofar as you can approximate the nucleus as a point, you can do the same trick with a nucleus, but put the mass of the nucleus there. That is only approximate. For the electron, this is right. For the nucleus, it's approximate. So if I want to describe a hydrogen atom, I have to represent the nucleus, so I'm going to represent nuclei by lines, thicker lines, double lines, like this. This is an electron, that's a photon, and this is a nucleus. A nucleus, let's say to take a hydrogen atom, the nucleus is just a plain proton. And it looks fat because we don't understand it inside here. But the electron is nice and thin, and it goes along, and nucleus might emit a photon which interacts with the electron. It could be that over 1 million years, or 2 millionths of a second in the practice, that you're going to emit several times photons back and forth, and the electron in general does some sort of a dance like so around the proton. Calculate the total amplitude, an electron and the proton down here. Still looks like an electron and the proton after a long time. You have to add the possibility that the electron and proton just went directly with ease, or that the electron went for a while and there was an exchange and another one of photons. Both of these things happen, and the interference between them has an effect on the motion of the electron. In the presence of a proton, an electron does not move the same way as it does when it's in empty space or free of a proton. When it's free of a proton, the amplitude to find an electron at a certain point is given by this function. As a matter of fact, you can show, in a manner similar to the case of light, that if there's nothing but an electron in the space, it appears to go at a uniform speed in a straight line. That is through the interference, of course. The same way with light. But when there's a proton in the neighborhood, or any other source of photons, but let's take the case of a proton. As the electron is moving, its amplitude keeps changing because the amplitude of the situation keeps changing because of the exchange of the photons. And the result of that is that the amplitude to find an electron anywhere is altered by the possibility of exchange of photons with the proton. And that is all computable and quite complicated. That's the theory of atoms. But if we have a very large-scale event in which things are far apart, and I drew it somewhere, but it's long lost. If I had some metal plates with an excess of protons here and some extra electrons sitting here, then an electron going along here, and mind you, this is on a very large scale compared to my other drawings where atoms were big there. Now they're tiny. There could be a photon go across here, another photon, another photon. These billions of photons going across are all very long wavelengths, 2 centimeters, half a centimeter, contain very low energy and hardly disturb the system. The thing that's emitting them can emit them without any change. It's such a small energy. At any rate, the main point is that the electron going along in this space here is not going along the same way as it would if there were no plates. And when you calculate the chance of finding an electron to go from here to here, you'll discover also, just like we did with light, that in this approximation of large scale, the only path which is important is a special curved path. Not straight, because the photons are altering the amplitude. Actually, yes, that's right. The interference, I got the curvature in the right direction. That's what was worrying me. In the case of light, you remember that there was an angle at which the amplitudes came in, and if we added all these amplitudes together at slightly different angles, the only path that was important was one in which the angles are not changing. In the case of light, the angle depended only on the time. And so it was time should be not changing, or least. In this particular case, the quantity which is not changing is more complicated than the time. It's a more complicated thing. It happens to have a different name. It's called the action. And the pairs of particles can be calculated by computing a certain quantity on a path called the action. And the path takes the curve, which looks like the curve of least action. This way of putting the laws of mechanics was discovered many, many years ago as what we call classical mechanics. The relationship of quantum mechanics, quantum mechanics is exactly right, and the classical mechanics is an approximation. The behavior of light jumping all around as before is right, but the idea that it goes in a straight line is an approximation. The idea that an electron goes in a curve is an approximation. It's really amplitude jumping about. This example, however, shows something interesting. In many circumstances, it's true that we have long wavelength photons which can be emitted because they contain so much little energy without disturbing the source. And whether or not they're absorbed by an electron is a matter that doesn't make much difference to the energy of the electron. And so we can find an electron moving in a region in which there are available many photons, enormous numbers. The wavelengths are so long, the energy is so low, the numbers are very large. But they're all about the same. Then we can describe this electron by saying it goes in a straight line except it's disturbed. It's disturbed by the possible presence of photons. We say, in an old-fashioned language, that there's a field in the neighborhood, an electric and magnetic field, which alters the motion of the electrons. But what this electric and magnetic field is amplitudes to find photons in very large numbers under circumstances where their energy is so low that it's easy to emit them. And that's the earliest ideas then about the motion of electrons was that they were particles being bent by forces generated by fields. This is now all passé. Instead of that, it's just the exchange of photons between the electrons or between the nucleus and the electron, the amplitudes for which are all given by this little constant, and the amplitude for the photon to move is given by a known function, and the electron likewise. And that's all there is to it, and from it all the rest of the laws of physics come out. Another example is the scattering of light. Light, according to that view, would always go in a vacuum in a straight line, or however it goes in a vacuum. And if the distances are big, it would look like a straight line. But we know that we've talked many times about light being bounced and reflected from the surface, or light going slower in materials and so on. I have to explain that. What's involved there is that in matter there are electrons, and if this is a typical electron moving along, again, time is this way, unlike this diagram. This is an ordinary diagram moving through a piece of material. We're moving through some place. But here's time again in space. We can have a photon coming in from the outside, hitting an electron in an atom, say, or anywhere. And after that, a photon is emitted by the system. So a photon comes in and a photon goes out, and it's even possible that the electron's condition that was before is restored again, although temporarily it's been changed. Of course, if you like this game, you can imagine another diagram. Let's see. Another possibility. Crazy idea, isn't it? That it's emitted before it's absorbed. Yes, you add that too, both together, and it comes out right. Don't worry about anything. Just add everything. It's only the sum of these two which is the right answer for the scattering of light. So you see that when we have electrons present, a photon can come in and come out in some other direction. That is the basis of the rules that we made before. And I should, for completeness, repeat these rules and explain them all over again, because in this system I had a different rule. I talked about photons having an angle dependent on time, and everything was kind of funny, and it doesn't look like it here. So I have to explain that just a little bit. It works more detailed. Now, this is a more detailed description of what happens in here. First, we were supposing that we had monochromatic light, that is, light of one color. That means that the source was emitting light of only one color. How does it do that? The way it does that, what that corresponds to, a source emitting light of one color, is this. The source, this is time again, and this is space. And let's say the source is standing here. It's like this. It might have emitted the photon then. It might have emitted it later. It might have emitted it later. It might have emitted it later. The amplitude to emit it at each time is different. So the amplitude to emit the photon at different times from the source is changing. Going around backwards. Yes, backwards. Like so. Now, to make a quick idea of it, let us suppose, for simplicity, that this function for the photon, just for simplicity, only, but it's right at long distances, only connects 2 points which are going at the speed of light. It's a simple model. It's a simple approximation. So if I were to come over here and get the if I would get the photon to get to here by one route and compare it to another route, when the time is longer, it must have been emitted earlier. If I asked for it to arrive here at a certain time, if it came this way, it was emitted at one time. If it came this way, it was emitted at another time. The amplitude to be emitted earlier. It's going around backwards with time. Yes, so the amplitude to be emitted earlier has a bigger angle. That's why the one that takes longer has the bigger angle. It's not really a property of the photon in the space, like I cheated you in making believe it was. It's really the amplitude of emitting. If you get the photon at a certain time here, it means that it left here earlier. If it went this long route, it left even further earlier. And if this source was emitting with an amplitude which is changing in time, then the amplitude to arrive here by this route and by the long route are different because the source was different. So it's really due to the source that there's a difference in the phase, or the angle, rather, of arrival of the light. In addition, there's one other thing wrong. I talk about light being reflected from a surface, and that's just nonsense. It's not reflected from the surface at all. What it really is, it's scattered by the electrons in the material. So the correct picture of this thing is this. I'll draw a better picture. What really happens is that the light comes down and hits the first piece of matter and then is scattered back by that kind of a picture on the last board over there, down here, in microscopic view. Or it comes down here and is scattered there. Or down here and scattered there. And that's all it does. It's really scattered in the inside, not on the surface. And so we have to add together a whole lot of amplitudes, each of which takes a little longer and have come from the source at a different time. And so it ends up adding a whole lot of little arrows. Each one is a little turned relative to the other by about the same amount. And if you add arrows, each one of which is the same length, and they're turned relative to one another, you go around on a polygon, or if the arrows are very small, a circle. And so you see that the net result, for example, of a certain thickness is to have an arrow, a net arrow, from this end to here. By the way, if this is the center of the circle, that could be represented as the resultant from these two, as this and this together. But that's the way I cheated last time. I just drew these two. But what really was happening was the circle. Let me explain it again. It goes, each little contribution in the interior goes around in a circle, and if I have the thickness just right, exactly right, the circle is complete, and the net result is 0. That's the first minimum. If I go a little thicker, it goes around again and comes back to 0. If I used half its thickness, it would go around halfway and stop. And in that case, I get the biggest possible amplitude, and so on. So those fluctuations were really not from the surfaces, but from the interior. At least we have the glass where the matter is doing the scattering of the light, and not some imaginary stuff like the surface. I cannot resist. One of my problems is, the problem is with this is that I can make it more interesting by showing you how more and more of the phenomena that you ordinarily see work out this way. And at the same time, I have a desire to tell you about all of the phenomena which are quite unlike what you see, which are quite unexpected and exciting. And I don't know which to do, either to convince you that it's interesting because it's something you didn't understand before, or it's exciting, and the thing to do would have been to give 8 lectures. But I didn't. I only contracted for 4 lectures. So what I've decided to do this time is to tell you about something unbelievable but still true, which is very interesting. So it doesn't explain a phenomenon you know about, but it explains something you don't know about. And that's this. Let's take the simple situation. Well, there's many possibilities. I'll say it very neatly. In that we would talk about a photon going from a place to place, and that we could also have it this way or turn it around. We could have the points 5 and 6, 6 being definitely later than 5, 6 being nearly the same time as 5, or 6 being earlier than 5. And when 6 was earlier than 5, it was just a photon going the other way, if you'd like. Now, as it turns out, the same thing, mathematical form of these functions is very closely related. I think I already told you, if I didn't, I meant to, that d of 2 and 1, if I put 0 in for the mass, that f of 2 and 1, if I put 0 in the mass, is the same as this d. So all the functions are exactly the same, with just one number in them, 0 for the case of the photon. And their properties are very similar. So at first you thought everything was understandable when I drew a picture like that. For example, the electron's coming along, the photon comes, electron goes to another place, and the photon comes out. I did shock you by having the photons come in the wrong order, but it's still all right. But this is a real good one, isn't it? Suppose this point here gets earlier than this point, and I start to draw something like that. Never mind about all the photons, they're in there too, but the point I'm trying to emphasize is the motion of the electron. This is time, and this is space. Question: if this point is called 5 and this point is called 6, and 6 is earlier than 5, I hope to goodness this f is 0, huh? Because I don't want things to go backwards. But it isn't 0. What it says is that this is perfectly possible. And what can it be that's going backwards here? Oh, you say that's easy. It's just an electron going from here to here. Almost. Almost. It's this way, though. The electron carries a charge, and it's good to put an arrow on to remember which way it goes. In this particular case, the arrow is going the wrong way. And it turns out that this section going backwards has many properties exactly the same as an electron, but it's not exactly the same as an electron. It is possible, by getting enough energy, so on, to get an isolated long piece of this backward moving section. See, it goes on for a long way. Maybe it's connected to an electron this way, an electron that way, but it's got a lot of things happening, photons coming in and photons going out and so on, except it's going backwards. You can take a piece of that line and put it between those metal plates that we were talking about, and it curves the wrong way. If you figure out which way the amplitudes are coming and they're changing, it'll turn out that it'll bend the other way. It moves toward electrons. In fact, it's just like an electron, except it's positively charged. It's called a positron, and it really exists. It's easy to make. If you get enough energy with some photons in the fields and stuff, you can produce this kind of a situation. For instance, you can take this and have the following physical possibility. I need more blackboard all the time. Let's see what happens. Yeah, I want that one for later, so I have to have this one. Good. For example, if I drew some terrifying thing like this, with 2 photons, this represents the possibility that an electron and a positron initially in space come together, disappear. No more electrons. Time is this way. Time is this way. Yeah, I know. It looked like I drew the diagram sideways. I didn't do it. They get 2 photons out. An electron and a positron can annihilate and emit 2 photons. It's directly observed easily in the laboratory. Or photons can come, I can draw it the other way. Photons can come together and produce that. Produce an electron and a positron pair. So that it turns out, because of this mathematical business, that every particle can go backwards as well as forwards in time if you want. And so for every particle in nature, there's another particle that goes with it, matched, which is called its antiparticle, and which has many of the properties of the original particle, with some of them with the sign reversed. In the case of the positron, for example, its mass is exactly equal to that of an electron. It comes from the same function. And its electric charge is opposite in sign. That you can find out by checking some numbers in here. It's all the consequence of these rules. In the same way, there are antiprotons and so forth. And a proton and antiproton can come together and annihilate each other, producing a lot of other particles. For instance, they could produce 2 gamma rays, but it's rare. But it can happen. The other particles I don't want to mention because they come next time. And so we have the possibility of having any kind of combination of these things in space and time, sometimes going forwards and sometimes going backwards. The backwards one's a positron. When a positron is actually made, the way I described there, in the laboratory on the Earth, it doesn't go very far before it disappears because it finds an electron, and the 2 combine, like the first picture, and 2 photons come out. But you can make them, see them go, deflect them with plates the wrong way, and they annihilate again. They were predicted by Dirac from the theory he had, which was really a calculation of this function for the first time, and discovered very soon afterwards by Anderson in the laboratory. This also permits, well, let me now finish. Well, I don't know if I finish. Yes, not finish. One thing I can't resist. This minus sign is so interesting. It means that when you cross up which is which, you have to subtract the amplitude. And that has an interesting consequence. Suppose the 2 points 1 and 2 are very close together, that you want to emit 2 electrons in the same condition at virtually the same position at the same time. So if 1 and 2 are the same, put 1 here and 1 here, and 1 here and 1 here, because 1 and 2 are the same place and same time. Now you see that this expression differs in no way from this, and therefore the difference between them is 0. That means you can't make 2 electrons, or you can't expect to find 2 electrons any time where they're made at the same point in the same place, same time at the same place. Or if you try to put 3 and 4 at the same point, you see if point 3 and point 4 are the same, these cancel. That would mean that 2 electrons can never be found at the same place at the same time. It turns out what it means is that they try to stay away from each other. Not just because of the exchange of photons, which is one influence which does make them stay away from each other, but by a completely different thing, which is this interference of the amplitude. Actually, because of the fact that there are polarization cases, it turns out what I said is right, but if you take into account the polarizations also, then you can make 2 electrons at the same point, but they must be in different conditions. One must be polarized one way, and one polarized the other, so that you can still keep track of which was which. So as a matter of fact, you can get 2 electrons into the same condition of, not just, you can put 2 electrons into the same condition of motion, one polarized one way and one polarized the other way, but that's all. You can't put any more. It is on this fact, with its consequences, which is one of the other things I'm unable to show you because of lack of time, the very beautiful fact that all of the chemical properties of substances can be worked out. If we start with a nucleus which has some protons in which are attracting electrons, we start with one proton and it puts one electron around it. If you start with a nucleus which has two protons in it, it's called a helium nucleus, then you can put one electron around and put another electron nice and close in the same place. They try to get as close as they can. The other one can be in the same place because of the two possible directions of polarization. Now when you take next nucleus, number 3, and you want to put 3 electrons around it, one goes in nice and close, the other one goes in nearly the same place but polarized the other way, and the third one, because there's only 2 ways of polarizing an electron, can't be in the same condition as the other 2 and has to be wander around out here waiting to get in. It's not repelled by any electrical force. It's just repelled by canceling amplitude, by interference. It has to stay out there. It's easy, since it's far away, the photons which it exchanges with the nucleus have small effects. It's easy to remove it. The last electron, in other words, is easy to get off. And that represents an atom which is chemically much more active than helium because it's easy to remove an electron. It gives an electron up easily. Such a thing is called a metal. In fact, when you compress a whole lot of these atoms together, the electrons are so easily outside ones. They're so easily removed that they just swim around in a kind of sea around the nucleus. They don't even stick on one. They wander off to another one and wander off. They wander all around inside, but 2 of them on each nucleus is still there. Boom, 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 but one extra ones are wandering around. Such a material, with very little electric forces, you can make all those electrons shift one way or the other. There's electrical conductor. And that metal I'm describing is lithium. It's this first metal. The element before is helium, and it's hard to get its electrons from the inside. Helium is chemically almost inactive, and lithium is chemically quite active and makes a metal, and so on and so on. I am very sorry to have such a brief time to explain phenomena that you know about in terms of these ideas, as the ideas are by themselves are rather difficult to get at, and I wanted to be complete in telling you about the most mysterious aspects rather than cheat by leaving out something important. I guarantee you, aside from the polarization, which is not important, I have now left out nothing, and the whole theory of electricity, electrodynamics, our understanding of the world comes from just these pictures. Each picture is interpreted this way. When you draw a picture, you write an amplitude for this, and this, and multiply it together, wait, and 2c to cut it down. Finally, I would like to describe the motion of an electron in going along. Here's an electron all by itself going from point to point. All right, nothing to that. But it has to be corrected. It's also possible that as the electron was, instead of just going directly from point to point, goes along for a while, decides to emit a photon, and then horrors, it absorbs its own photon. There's something perhaps immoral about it. But it does it. All right, it might not be the nicest thing to do. It does this. And just, you understand what this symbol represents now. If you put some points in here and label these, there's an E for this, an amplitude for that, an amplitude for that, an amplitude for that, all multiplied, for the amplitude for this electron to go from here to here, times the amplitude for the electron to go from here to here, times the amplitude for the electron to go from here to here, times the amplitude for the photon to go from here to here, times C, times C. Those are the couplings for the junctions. And that bunch of junk all multiplied together has to be added for every place that this can be and time, and every place in time that that can be. And when that's all done, you've got this piece, which is supposed to be added to that piece. Now when you add this piece to that piece, you find that the motion of this is slightly altered. its behavior in particular in a magnetic field is changed. In a magnetic field, if the thing was as simple as this, it turns out its polarization changes at a certain rate, or its spin changes, at a rate that can be measured, and which we'll call 1. 1 is the result you would get for this alone. If you add this to this and figure out how the thing moves, it behaves in a magnetic field slightly differently. And if you just add this, you get 00116, or 8, or something like that. If you're this time, for the fun of it, I'm going to write the formula. It turns out that this term is proportional. The contribution in the magnetic field of this is proportional to 2 C's. C squared is 1 over 137.0360. Sorry. Well, I did the error. I'm within the error. Over 2 pi. This time it's easy. Our students learn how to do this calculation in their elementary course in quantum electrodynamics, which is a 3rd-year graduate course. All right? This was worked out by Schwinger for the first time in 1948. The next case is to take diagrams corresponding to 2 of these things, something like this. There are other possibilities. Let me erase here and write the other possibilities of this. I'm just continuing. There are other possibilities, all of which involve 4 C's, C4 sometimes. And there are other things that can involve 4 C's, are something like this. Okay, there's a different kind of connection timing. And finally, there's nothing significant about that being straight. These points, it should be, you know, and stuff like that, but I'm too lazy to draw it cockeyed. Here's an interesting possibility. Photon is emitted, makes a pair, electron and positron, and again, if you'll just hold your moral criticism, the electron and the positron annihilate again. So there's an electron going this way and a positron going that way, and they annihilate again into a photon, and that comes back. It's called a closed loop. It comes and it goes. This involves 4 C's, 1, 2, 3, 4 also. And this, and this, which involve 4 C's, can all be added together, and you get something proportional to C4, which, by the way, is fairly small, being the square of 1%, which is 100, 1 in 10,000 or so. And the coefficient, this time it's not so easy to write down. It's 0.03 something something. All right. At any rate, this took 2 years to calculate after this was worked out. And it took 1 year to find a mistake in that calculation. It's true. It's true. It was very exciting because it was calculated very carefully by 2 different people. They thought they were independent, but they compared a little bit or something. They both had the answer was wrong, and it disagreed a little bit with experiment. And they improved the experiment, and it disagreed, and it showed that quantum electrodynamics was wrong. No, it was an error in arithmetic. So everything was all right. And now, that was 2 years later. That brings us up to about 1950, 51. And now we go on and we try to do 3. Oh. Well, you see, when you have to add all these possibilities, you get lots of pictures, of which I'll draw one more, but you can keep on going and draw a lot more. You make a pair, they interact by exchanging a photon and so on. And each one of these diagrams represents a definite formula, and we use the diagram to represent the formula. And we just make these pictures, write down what they correspond to, and add the amplitude. A straightforward cookbook process. All you got to do is write the picture and translate things and write the factors and add everything together. Therefore, it can be done by machinery. Now that we have super-duper computers, we've got so we can compute this one, C6, and by that time it's down to the millionth part. And altogether, so far up till today, as I told you in the very first lecture, this number comes out to be, when you add all this stuff together, don't stop here, but keep on going, 596523 plus or minus 3. Calculated and experimental is 24 plus or minus 2 at the present time. What do we got to do to make it better? Some of this error is that the computer who did this calculation only did it approximately, and we can do it more exactly by using more time on the computer with a little more money. That'll improve the error for that. However, it's no use doing that until we look at number 4. That is C8 with 4 of these extra 8 couplings in it. And people are just beginning to see if they can estimate how big the C8 term will be, because that will be of the same order as this error. In addition, there's an error that comes from the fact that when we go to calculate it, we've got to put a number in for C squared, and this is as accurately as it's been measured up till now, and a part of this error is due to that. So I have to wait to give this lecture again, perhaps in a year or two, in which case I'm sure I could write one more figure here, and the error will be smaller. But the question I am not sure of course, is whether it will still agree with experiment. That one never can tell until one makes the calculation more elaborately. I think then that describes the framework of the world as we see it. In the first place, amplitudes for every event that we add together when we expect to add probabilities, and we multiply when we expect to multiply probabilities, but we're not doing it with probabilities, we're doing it with amplitudes. This makes us philosophic difficulties, if you wish, but after a while one gets used to it. One can think about these amplitudes, one can think about adding them, one can consider these as alternatives, which you simply add as amplitudes. And after a while, one gets to be quite familiar with this strange language. The ordinary experiences of nature, such as light going in a straight line, the conservation of energy, and so on, are all very easily deduced from these principles, and all there really is that we can find to all the phenomena that you see every day, with the exception of radioactivity and gravitation, is just the 2-3 rules. That a photon has an amplitude to go from one point to another in space given by a special function p. An electron has an amplitude to go from one place to another by another function e. And that there's a junction possible between a photon and 2 electrons, which has a coefficient which is a certain number. This slightly modified by the couple of cases for polarization, but no more really complicated than that, represents the whole sum of a knowledge, a summary, a most marvelously unified theory of almost all of common experience. But not all. And therein lies the puzzle. There is much more in the world than just electrons and photons. There are the nuclei, protons and neutrons, and so forth. And the theory is therefore not a complete theory of the world, although it is, as far as we know today, a very complete theory of common phenomena. Colors, light, X-rays, positrons, electric currents, electric and magnetic fields, X-rays, radio waves, and so on, substances, hard and soft, chemical interchanges. Some atoms are easy to combine with others and some are inert. All of this is a consequence as a result of this analysis of first finding the right framework, which is the most exciting part of it because it's so utterly strange. But after finding the framework in which to describe things, namely amplitudes, to discover in the end only 3 amplitudes that you need to discuss. One is a simple junction number, and 2 functions, both of which, by the way, are really the same function. In one you put one value of m, and the other put the value 0. So next time I'll discuss the rest of physics and also all the puzzles which are still left in this theory if you thought that was absolutely complete. We still have a question or two to ask about it, and I'd like to describe that and other things in physics for the next lecture on Thursday. Thank you.
Where does coherent light, the light from lasers, fit into your calculations?
The laser has to do with the fact that we spoke about this situation and this situation, only this time I'm going to call it photons. Suppose you have two sources, or two atoms, 1 and 2, which can emit a pair of photons, and you want to know, do you get a photon in two different counters, 3 and 4? There's two ways that can happen. But this time, because it's photons, we're supposed to add these two. Now, if these atoms are in the same condition, or very close, then the amplitudes that we're adding are virtually equal. So the amplitude for the event that the two atoms which are ready to emit produce two photons is twice as big as you would have guessed. If the two photons were different, you would just get this one term because you could distinguish this case from this one. But the two photons are very much the same. You have to add this other amplitude, which is the same thing except that instead of E's, they're P's. And if 0.1 and 0.2 are close together, or in the same condition, you have to add two numbers which are the same, and therefore double the amplitude, and multiply the rate by 4. So therefore, the rate at which two atoms will emit light, if they emit the same light, is higher than if they emit different and independently. So when there's a large number of atoms, the same thing happens. You have to add all the combinations. And when you have a whole lot of atoms which are all set to emit, that can possibly emit the same, exactly the same kind of photon, they emit much more with a greater enhancement. They all cooperate to emit. They emit with a much higher probability than you would otherwise expect. A laser is a device for producing a large number of atoms in a corresponding physical state, which are all capable of emitting a photon in a particular direction, one kind of photon. It corresponds to all the 3s and 4s being on top of each other. And it has, therefore, when they're all in the right condition to emit, a whole bunch of them discharge the energy into the same photon, and that's what you call the coherent light of a laser. It's a very intense light of a single frequency in a single direction. The reason it works has to do with this interference. It's not a very good answer, but it might give you a clue.
Does the amplitude of a photon coming out have any effect on the one going in?
Yes. What we have to do is we have to work out. You remember when I cheated in the beginning, when I was doing this easy, I said all you do is you take the time it took the light to get from here to here. But you see, that really is the sum of two times. I could analyze it in two steps. I could say there's a certain amount of, there's an amplitude that you come out, amplitude that you reach here, amplitude that you reflected times amplitude that you get here. Now, in multiplying the amplitude to go from here to here by the amplitude to go from there to there, I add those two angles. So I add the angle for this time to the angle for that time. It's just the angle for the total time. So that I can analyze this either way. I can either think of it as one photon doing that and consider the total time it went, or I get the same answer if I think of a photon went from here to here, a certain change in amplitude, angle. Then a photon, new one, goes from here to here. That would contribute an angle too. But I say to multiply them in succession. And when you multiply, you add the angles, and that's equivalent to the total time. So it comes to the same answer.
Does the existence of a positron involve some sort of violation of causality?
No. The question was that my description of the positron here involved apparently some sort of interaction, and yet an electron can be all by itself. That was a completely unnecessary difference. There's not an essential difference. I explained the need for the positron by a kind of continuity from this diagram here to this case here, in which the timing is changed, and told you that this function, mathematical function, had to be, this E function, has to be of a certain form where it's completely smooth between here and here. In fact, the mathematical properties are that the behavior when 6 is later than 5 and 6 before 5 are very closely interconnected. One can deduce one from the other. That's all I wanted to say about that. There's no reason why this backwards moving section cannot be a long section, either interacting with photons or not. I gave you an illustration of one where it was a long time going, interacting. But it could be that this positron was made on some star 10 light years away. and it's been going this way in empty space, unperturbed by any photons in the neighborhood, disturbing it or be picking them up or not, for like it was an electron alone in space for 10 years. Okay? So there's no reason why positrons, in fact they do, they last, they behave exactly the same as electrons. But for the accident of the fact that the world has so many electrons, the matter in the world has so many electrons in it, so our laboratory walls are full of electrons, and we can't make the positron not hit a wall. If it's left alone, it coasts into the wall. And when it coasts into the wall, it annihilates. So in practice, the positrons don't last very long. But if you get them in a circumstance where there's no matter, we have done so. It's not left alone because of the wall. But you can make them go in a circle by using a magnetic field. And then you can keep them going for days, going around in a circle, untouched by human hands, not touching any electrons, and they stay, and they stay, and they stay. In fact, we do experiments by making speeding up positrons going around in a circle to a very high energy, and making electrons go in the circle in the opposite direction, and looking at what happens when the electron and the positrons collide with each other. Then we have a diagram that starts out like this. Electron coming in, positron coming in. Time is this way. And then things happen. Photon comes, and then one thing might happen is a pair of new particles might come out. If you want to know what kinds of new, could be an electron and positron, it's uninteresting, in coming out in a new direction. You would think that just means a collision. But really what it was an annihilation followed by a recreation. But even more interesting, and I will advertise the next lecture, there are other particles in the world, and this is one way to make them. We can make particles called muons by hitting electrons and positrons together and producing a pair of something else. Mu plus and mu minus. So there's nothing different about a positron than an electron. They're all very symmetrical, except history, except the characteristic of our laboratory, that we have a superfluity of electrons. We have an excess of electrons.
Is the direction of time in your laboratory reversible, then?
It's a very interesting subject and requires a lot of more serious discussion. His question was, what about the time in your laboratory? Is it reversed? The order of time, and that is to say the order of events like this, if you put hot and cold things together, then it gets lukewarm. But if you take two lukewarm things and put them together, one doesn't get hot and the other doesn't get cold all by itself. The explanation of that direction of time, has to do with the confusion of things. If you would take a lot of black things and white and black objects and then just jiggle them, they get mixed up into gray. If you start with gray and just jiggle them, they never get black and white. But each jiggle could be perfectly reversible. For instance, your rule could be just take a pair and flip them over. Take a pair and flip them over. You can't tell whether I'm going forwards or backwards in time. If I take a pair and flip them, that is, reverse them, it looks exactly the same. If I ran the moving picture backwards, I took a pair and reversed it. So therefore, what is interesting is, it turns out that on the microscopic scale, all the laws of physics are exactly reversible. Forwards in time, backwards in time look the same. But all those phenomena, and there are many, of course, life and frying eggs are two examples, which go in one direction only in time, have to be interpreted by the complexity of the circumstances, that there are so many particles getting mixed up, plus some assumption or understanding about the fact that in the past, the matter in the universe is at a higher density than in the future. This is a property of the universe at large and is not reflected in the microscopic laws. So it does not, it turns out, in spite of the fact that I draw my arrows upside down, end up violating any causal principle. Strangely, it is very interesting.
Whenever you have shown an electron changing direction in your space-time diagram, it has coincided with a junction. Why?
I did that because what I really know, and only thing I do know, is that there's an amplitude to go from 0.5 to 0.6 as a free particle without disturbance. And then there's junctions, and then it goes to another point as a free particle without disturbance. And so I just wanted to represent the functions which I've erased here. By this line, I mean that in the final expression, you will find a factor E56. The line is only meant to indicate that fact, the fact that it's straight is a convention. All right? It doesn't mean that the electron has to go exactly along here or anything like that. All I know is it's generated at 5 and disappears at 6. And it has amplitude E56. Okay? I don't worry about where it actually went.
A disturbance has to travel from 5 to 6 then.
Well, 5 and 6 are the places in which the photon, in this particular case, is coupled. I have only 3 things. It goes from one point to another in a leap, a pure leap without disturbance. The amplitude to do that is that E. Photon goes from one place to another without disturbance. The amplitude to do that is the D. Then there's an amplitude that an electron and a photon and another electron come together at a point. That's C. The 3 rules of nature, or of quantum electrodynamics. If all of nature is that would be all there was to it, but that's all there is to the part that we need to do quantum electrodynamics. So what I'm going to talk about in this lecture is really all of physics, actually, all of the known physics at the moment, plus a lot that's guessed. And so the lecture is going to be even more extensive than the ones before, because there I was only dealing with 2 particles, and now I have to deal with, I guess it's 24 particles. But first, I'm going to divide this talk into 2 parts. First, I'm going to talk about questions that are directly related to quantum electrodynamics of itself, supposing that that was all there was in a system, electrons and photons, what problems are associated with that theory alone. And the second set of questions has to do with what is the relation of this stuff to the rest of physics, to nuclear physics, gravitation, and so on. So start with problems of quantum electrodynamics, which I suppose now that the theory is completely understood and you know what I'm talking about because you were here at the other 3 lectures. Most shocking characteristic is this crazy framework of amplitudes, and if you would think about there being problems, you're sure that problems must be associated with that. But the physicists have been fiddling around with this now for 50 years, and we've gotten very used to it. A. B. All the new particles, all the new phenomena having to do with nuclei and higher energies, etc., always turn out to fit perfectly with everything that you can deduce from supposing it's a framework of amplitudes whose squares, probabilities, and interferences, and so on, all appear. So that the model structure of the world, the framework of the world which I described, has no experimental doubt about it. You can have all the philosophical worries you want, but there we are. Because it's an experimental science, we have no other way to go. There's another set of problems, which are technical problems, having to do with improving the method of calculating the sum of all the amplitudes. You make all these pictures, and you have to add all these numbers, and you have different kinds of techniques that are available in different circumstances. And, of course, that is what the graduate student learns how to handle and what takes so long to learn. And, of course, since it's so technical, I'm not going to discuss it. That's just a continuously improving techniques for analyzing what quantum electrodynamics really says in different circumstances. But we have one additional problem that's characteristic of the theory itself, we have a particular problem, a characteristic of the theory itself, which as a matter of fact was the reason why it took 20 years from the time it was first invented in 1929 till the time it was first satisfactorily used in 1949. And that has to do with this problem. We have in our theory, for example, if we start with an electron here, we have a certain amplitude that it gets to here, which we can supposedly calculate first by supposing it goes directly, and that amplitude is a direct function, a very precise function that comes from relativity that contains a particular number in it, which I wrote last time as ME.
And I'd like to write this time as m sub in. Now that we put in to the theory. We have to just put it in and then find out what results we get and find out what number we have to put in there to agree with experiment. This is the amplitude that a particle starting at 1 will get to 2. I think I wrote it this way last time. And depends on the mass of the object. However, the real amplitude to go a long time from position 1 to 2. Oh, I also told you last time that the amplitude was constant in space, and you added this all together, then you'd find that the amplitude to find it at a time 2 simply rotated at a certain angular rate. The angle would keep turning at a rate depending on the mass, m. But in fact, there is the total amplitude to get from point 1 to point 2 also contains other possibilities, of which this is one, that the electron could have emitted a photon and reabsorbed it. And the electron could have emitted 2 photons, or a photon twice and reabsorbed it, and a whole lot of other diagrams that you keep on going. Contribution from these various diagrams, if this one, for example, is of order c squared, where c is a number that goes every time there's a junction, or called a coupling, and c squared was equal to 1 over 137.03599 and so on. We haven't done it experimentally. We're not sure of this within a 3, plus or minus 50. But that's determined also experimentally so that the predictions of the theory agree with experiment. Now, the thing that's I'd like to emphasize is that because of the other amplitudes, the real total amplitude to arrive at the time 2, supposing, let's say, that initially it was equal amplitude to be everywhere in space, does not revolve, the phase does not turn at exactly the original value, but turns at a different value because of the contributions of these other values. This one would go around at this rate. The angle, the amplitude to arrive is a complex number, which with time t2 changing, goes around. After you've added these, it's again a complex number, but it goes around faster or slower, different rate. Now what we measure when we measure the mass of an electron in an experimental world is the rate that it goes around. The mass of an electron is its energy. The mass and energy are equivalent, as Einstein showed, and energy is equivalent to frequency, as I guess it was de Broglie showed. And so I keep saying mass and energy and frequency interchangeably because I'm so used to that. At any rate, the frequency or the mass or the energy of the electron, the one that we're going to measure experimentally is not the one we put into the theory. So we have another mass, which is the mass experimental, which we could see would be expected to come out something like this. If the c square was small, very small, and you want to forget it to 1%, forget that 1%. This term is of order C4. You would say first approximation comes from this amplitude, you'd get something like that. And then you'd have a correction because of this thing, which would have a c squared times it. In other words, some correction with 101%, something like that. A correction that you'd compute by adding these diagrams together, and then maybe C4 times another correction from this and so on and so on. That's easy to understand. Now, when we make calculations of any other physical result, it's much more convenient to express the answer in terms of this m, which is a measured value, than it is in terms of that. So we have a habit of writing all the answers. Always imagine we might start with a number like this, calculate everything, and express everything in terms of the experimental mass that we measured, which is the sum of all these things. So all answers are calculated in terms of the experimental mass. Now, if you've understood me at all, you probably don't understand why we made such a big fuss of that, because that's just a matter of convenience. It's just a question of whether I put it in here and compute that, put it in here, or whether I put it in directly. The difficulty is, and the peculiarity, the thing that bothers us, is that this correction that you multiply c squared by is infinity. And the fact that it comes out infinity because this function and the one for this was the electron one, and for the amplitude that the photon gets from here is the same from here to here, this point to this point actually, not 2 to 1. I shouldn't have said that. In here, we're just going from here to here. That multiplied by the same function for zero mass and then added everywhere comes out infinity. And that caused a lot of trouble for the first people who invented this theory. They saw they were getting infinity for every answer. Because at every problem that they did, there was something like this in it somewhere. An electron going from one place to the other would always be possible to emit a photon and absorb it. Every answer to every problem was infinity. It was noticed by 1949. It was 20 years later. It was noticed by Beta and Weizsäcker that if the answers were put in terms of M experimental, it looked as if, in spite of this being infinity, when you wrote the answers in terms of that and computed them, there was no infinity. All the infinities canceled out. So that if you had expressed the answer in terms of the final M and not in terms of this one, then everything would be finite. It looked that way, and it was just a matter of checking out that, in fact, that was true. That's what was done by Schwinger and Tomonaga and myself. I got prizes for that. But one way you could say all this is that this number is unavailable experimentally. It doesn't mean anything. You put it into a theory. Let's, for a moment, imagine it, well, so that whatever this is, I can always adjust this number so this comes out finite. If this is infinity, I put minus infinity in for that. And that's one way of saying what we ultimately are doing. Although this looks like it comes out in infinity, we put minus in, this comes out, let's say, not infinity, 10 billion, right? Then we put in 9,999,999, only get 1. So if this, or whatever this is. So the idea is that this goes toward infinity in a calculation. We just say, well, just keep on adjusting the M so that it's to fix it back so that the M comes out finite. Now you laugh at that because you have some kind of a feeling that's a dippy way to do mathematics. And it is. And this dippy way to do mathematics is the way we do this theory because we never been able to straighten it out. But we do know that if we do this dippy way, we get results which agree with experiment. If it had been that this correction were finite, there would be no problem, of course, because the fact that this would be some number and there would be another number. But this fact that the correction is infinite is very annoying. And as a result of that, it has turned out it is not possible to prove at the present time that the entire theory of the quantum electrodynamics that we've written down is really self-consistent, that there's not some, if we calculate everything extremely accurately, we wouldn't get into some difficulty in itself, that the mathematical structure of the theory is self-consistent. There's a nervous condition that there's something wrong with the need that we start with a nice number and have to put minus infinity and play games like this. That annoys us, okay? So that there's one problem, what I have to say, is that in this, although this calculational scheme is quite definite and we know exactly what to do, this process, which is called renormalization, we are not satisfied that it's a mathematically legitimate process. But you notice that when we compute the 10 decimal places, it agrees with experiment. So it may be all right and may be a real theory. Another way to describe this business is the following. In making all these calculations and adding over all possible places for the, in this case, there's a 1 and 2 is here, but in our problem, where I'm having trouble, let's call this 3 and 4. Then we would have this at 4 and this at 3, multiplied by the photon going from 4 to 3, which is the same thing at 0, man. And when it turns out that when 4 and 3 are very close together, that these both things rise together as gets close together, but so much that when you add all the possibilities, you get infinity. So one way of saying this is, your whole idea that you can have 2 points infinitely close together is nonsense. Your whole thought that space can keep on going down to the last notch and you can use geometry to the very last infinitesimal distance is wrong. Suppose we stop these sums when 3 and 4 are closer than some very tiny distance. Let's say a distance that's shorter than any distance or any wavelength or anything we're able to get experimentally. Then this correction comes out quite small. Well, it depends. If you make the distance sufficiently small, then the correction gradually builds up. In order to make this correction term equal to this, so that this has to be 0, sort of, it turns out that the distances that you have to use are absolutely, well, I can't even, it's no use trying to describe them. They're like 10 to the 100 power or something like that, 10 to the minus 100 cm centimeters, whereas all we can do experimentally is 10 to minus 15. That means some, I don't know, 80, 90 decimal places further on than where we are. So it's always possible that nature's different 5 or 10 decimal places down. 20 decimal places down. You don't like it 30 decimal places down? It's all right. The trouble is that we cannot make a model of that, a real model. If we stop these things at some distance, then the theory that we write is mathematically inconsistent. It gives probabilities that don't add up to 100%, or it gives negative energies, or it gives something silly. Of course, it gives these things with infinitesimal amounts, but it's not a self-consistent theory. Therefore, we don't know. We do have this difficulty with this theory. We don't know whether if we stop the theory temporarily, it makes sense, or if we just go taking what we call the limit here, where we use everything and do the renormalization process, calculate everything in terms of the experimental mass, and then forget about the infinity, whether that's a mathematically sound thing. So I have to explain that in order to tell you the exact position of physics today. That's the problem. It turns out, in addition, there's the same kind of a problem about the sea. That also has a correction. If you were to have started out and imagine that 2 electrons were interacting via a photon, and they were at an effective coupling C0, C0. And now you'd have a correction, because the photon that goes along could make a pair, and then that could annihilate and make another photon. And that corrects this, and so on. And in exactly the same way, the effective coupling constant, which is measured experimentally, see, I cheated a little bit. I said it was that. It isn't. It comes out like this, that the experimental coupling constant is equal to C0 square plus corrections of the order C4. See, because you have 2 C's here and 4 C's here times a correction. Yes, you guessed it. That's right. This correction is also infinite and causes us the same nerve-wracking business. But this is measured experimentally. Make that 0, and it'll come out okay, because 0 times infinity is finite. Never mind all that. If we put the results in terms of the experimental constant, then there's no difficulty, and all the infinities disappear. So in other words, we have to use the renormalization trick twice, once for the masses and once for the charges. Once for the coupling constant, which is called electric charge, and the other for the mass of the electron. Okay? And when we're finished, we get a coupling constant, which we have to look to experiment to measure. So that is simply a technical difficulty, perhaps, and maybe a real difficulty. But anyway, that's the slightly discomforting condition in which the theory is. That's the first main problem. Now, with regard to questions about electrodynamics, if you say, I accept that, that probably is okay, or if it isn't okay, I'll wait for some mathematician to find out for me. We then have the following interesting physical problems I mentioned before. Where does this number come from? From experiment. I know, but a good theory would have that this thing is equal to 1 over 2 times pi times the cube root of 3 times 6 and so on, so that you know what it was, if you know what I mean. It's a number that has to be put in, that nature has, or so to speak, if you're religious, you would say God has created that number. But we would like to try to figure out, if we can, a little clue as to how he thinks to make a number like this. For example, maybe why isn't that a 4 there? You see? Okay. In the same way, by the way, you might ask, in the same way, what is the mass? That is also a number. Yes, that's also a number. If you write the mass of the electron, and I'm always going to put the experimental masses down, it comes out a number. There's so and so many grams. And why is it that many grams? You first have to tell me why a gram is as big as it is. It's because somebody chose a gram, I think during the French Revolution or something. They decided such and such is a gram, and then the electron is so many grams. That's therefore not a real problem. But nevertheless, I'll put it down here as a problem. I'm not going to use grams because there's too many zeros. We have a particular unit which doesn't make any difference what it is, but we'll call it the million electron volts. It's the energy, masses and energies equivalent, that you get when you have a million volts and have one electron fall through that much difference in voltage. And this mass is known many more decimal places, but I'm not going to bother you anymore with these long strings of numbers. So the mass of the electron is this, and of course we don't know why it's that particular number. That depends on why we chose the gram the size it is, or the electron, the volt the size it is. Okay? And that, so that is not by itself a serious problem. But the reason I write it down is that it's going to turn out that there's a large number of particles in physics, not just electrons. There's, as I mentioned, several dozen, and they all have masses, and they're all different. And they're all the same problem. Where did this one get its mass? You know, they're all relative to it. You can't play games with the grams anymore. One's a ratio. For example, you find one is 67 times this one. Why? So this is, the masses are in general a problem, to which we do not know the answer. So we have no way to determine this mass. Now, that summarizes all of the problems associated with quantum electrodynamics. The most beautiful one is the coupling constant 137 point and so on, and all good theoretical physicists put that up on their wall and worry about it. There is, at the present time, no idea of any utility for getting at that number. There have been from time to time suggestions, but they didn't turn out to be useful. They would predict that the number was exactly 137 when it looked, well, the first idea was by Eddington, and experiments were very crude in those days. The number looked very close to 136. So he proved by pure logic that it had to be 136. Then it turned out that the experiment showed that that was a little wrong. It was near 137. So he found a slight error in the logic and proved with the pure logic it had to be exactly the integer 137. It's not the integer. It's 137.0360. Every once in a while someone comes out and they find out that if they combine pi's and e's and 2's and 5's with the right powers and square roots, you can make that number. It seems to be a fact that's not fully appreciated by people who play with arithmetic. That you'd be surprised how many numbers you can make by playing with pi's and 2's and 5's and so on. And if you haven't got anything to guide you except the answer, you can always make it come out even to several decimal places by suitable jiggling about. It's surprising how close you can make an arbitrary number by playing around with nice numbers like pi. I mean, and therefore, throughout the history of physics, there paper after paper of people who have noticed that certain specific combinations give answers which are very close in several decimal places to experiment, except that the next decimal place of experiment disagrees with it. So it doesn't mean anything. Okay? Those are the problems of quantum electrodynamics. Now the next part is the connection of quantum electrodynamics to physics, to the rest of physics. And then we're going to have a good time now for the rest of the lecture because I'm going to tell you all about the rest of physics. And you can compare the laws of the rest of physics with the laws of quantum electrodynamics. But first I must say immediately that the rest of the laws of physics are not known as well as quantum electrodynamics, and therefore what I have to say is to a varying degrees uncertain. Nowhere near as certain as the electrodynamics. So first there must be a connection because we have to discuss one point. The photon, which couples to the electron, also couples to the nucleus. That's why the electron is attracted to the nucleus. So there's something inside the nucleus that couples with a photon. In other words, we sometimes say it's charged. To say a particle is charged or something is electrically charged is merely a statement that it couples to a photon. A photon is absorbed by it or emitted by it. That's what it means. Anyway, nuclear particles are charged. So in the beginning of the history of this thing, knowing about the nucleus and puddling around looking at them, it became pretty clear that it's easy to understand nuclei of the atom. They're a tiny little center where the electrons go around. They're different from atom to atom, and they can all be thought of as being made out of two particles, a number of particles of which, no, how do you say it in English? A group of particles which are either protons or neutrons. Like, for instance, a particular carbon, for example, is a nucleus that has 6 protons and 6 neutrons in it. Nuclei can have, uranium has 146 neutrons and 92 protons in it, and so on. Hydrogen, the simplest nucleus, has just 1 proton in it, and so it goes. So out of protons and neutrons, the nuclei can be made. But the protons and neutrons that are in the nuclei stick together quite tightly. The forces are very large. The energies that are released when you let them jiggle around are much greater. in proportion as the atomic bomb is more effective than dynamite, because the dynamite represents a rearrangement of the electron patterns, and the atomic bomb represents a rearrangement of the proton-neutron patterns, and the relative energies are very large. The particles that interact, when we tried to, at first, the first guess would be that the proton is simple also, and that the propagation of a proton, that we make diagrams for protons, same way, and all we have to do is put the mass of a proton in here. Problem, first. It must be that there's more than just photons involved, because the forces in nuclei are stronger than electrical forces by about 100 times. If we would invent some new force, we would have to have a kind of a c-square of the order 1 and not 137. Because the size of the forces needed are 100 times bigger than electric forces, we call those strong forces. Strong forces are those in which somewhere there's a constant of coupling closer to 1 than it is than electricity. I mean, it might be a quarter, it might be a fifth, it might be 2, but it's not 1%. In investigating this, at the beginning it was hoped that the proton was simple, but the proton kept on showing that it wasn't simple at all. For example, there's many properties that indicate that it's not simple, and the neutron is not simple. For example, the proton, the electron, we talked many times, has a magnetic moment which we can start expanding like this. But the proton has a magnetic moment 279, completely crazy. And the neutron, which is neutral and should have no magnetic moment, no magnetic interaction at all, if it were really neutral, is in fact has a magnetic interaction, which is some number. 3. That indicating that inside the neutron there were some charges that could interact magnetically. It might be neutral, but there are plus and minus or something going around in there, or something. So, to find out more about these particles, which look so much more complicated than the electron, we did many experiments bombarding protons onto nuclei and hitting them harder and harder, first to drive the parts out of the nucleus in order to see how the nuclei were constructed. But in the process, you discover, going higher and higher energies, that you created new particles. And the names of the new particles go, first they discovered pions, and then muons, and then lambdas, and kaons, and sigmas, and x's, and you ran out of the alphabet, so pretty soon it was the sigma 1190 and a sigma 1386 and a lambda 1190 and so on, because you just gave more numbers, and those numbers were the masses of the particles. And ultimately, it is clear that there's an unending number of particles, there being about 400 and some odd particles at the present time, but it's an open-ended thing. It depends on how carefully you measure. You can't go along with 400 some odd particles. Things get more and more complicated. And then it was realized that these particles can all be understood, cannot all really be understood. We don't know, because now we're moving into partly the unknown. We expect that they all can be understood as being made of others. Now I would like to discuss these others, the so-called, the present guess as to the fundamental particles. Most of the things that are made by bombarding protons and so forth together are supposed to be made of quarks, and I'll tell you about those soon. Those are the strongly interacting particles. But in the process of the experiments, some new particles were discovered which were not strongly interacting with nuclei. The electron, for instance, does not strongly interact with the nucleus. It only interacts through the photon. It's a charge. It's a small thing. It's always got the c-square. There are other particles which do not interact strongly with nuclei. So what I'm going to do is I'm going to divide all the particles up into two classes, those which do not interact strongly and those which do. All right? The ones which do not interact strongly happen to be called by a horrible name, leptons, and the ones which do interact strongly are called by an equally horrible name, baryons. So I start out by discussing the ones which do not interact strongly and which are called leptons. And I thought to tell you what they are. Well, the first one in the list is, let's put the name of the particle here, and here we can put the mass of the particle in these nutty units, MeVs, and then I'll put down an electric coupling, which we'll call charge. the strength of the coupling to the photon. This is the coupling to the photon, in another word. But the unit I'm going to use is 1 for the positron. So the first one is an electron. And its mass in MeV is 511. And its charge to the photon is -1 by definition. It's the scale in which I want to measure, and I use minus because of Benjamin Franklin, who chose to call the electron minus. Okay, so we're stuck with that since 1776. Now, and lots of other things we're stuck with since 1776. Which some of them are not so concerned as I am. At any rate, I now may continue this list of these particles. We have discovered another particle, which is called the muon, which has a mass of 105.6. It's 206 point, we know it very much more accurately than I'm writing it, times that of an electron, and its charge is -1. It does not have a strong interaction, and your first guess would be that it propagates like an electron, except that in this place where I put the mass, I'm sorry, after I renormalize the mass, this is a renormalized mass, it should just be a different number. And that's all the muon should be. And that's all the muon is. There's nothing different about a muon and an electron that we can find except its mass. It's different. It has a different mass. It's just as if God wanted to try out a different number for the mass. And, for example, the magnetic moment of a muon has been measured and is 0.01165.9. Well, first, we calculated theoretically because if there was had no strong interaction, no magic, it's just quantum. We use quantum electrodynamics, same kind of diagram, same game, and get this number 0 plus or minus 1. Well, let me get it just right. It's 3, I think, plus or minus 1. You don't really care, but the fun of it is to see how nice it works. This is only the 3 plus or minus 1. That's the calculated value. And the experimental value is blah, 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 blah. 90, blah is being exactly the same. Plus or minus 3. I don't want to write the 101. But this isn't quite as accurately calculated or measured as the electron, but within the calculations and measurements they agree. And this turns out to test the idea that there's nothing wrong at short distances more accurately than the other. Because due to the very much higher mass, that simply means that the amplitudes are changing much more rapidly, by 200 times or more rapidly. And therefore, if anything is wrong with the electrodynamics over a short distance, this is 200 times more sensitive to see that there's something wrong. Nothing seems to be wrong. So our space, that's how we know from this, in fact, that the space is as accurate down to distances or frequencies, rates corresponding to 20,000 in these scales. The electrodynamics would be right up to 20,000, as we now know, before there's a serious error. Well, that's kind of interesting, and that produces the problem. Where does it come from? You see, now, if you don't like trying to figure out where that mass comes from, your problem is what is the ratio? Why is this true? Is there another answer, so to speak, to some problem? It's as though you had a quadratic equation that got in a book, that has 2 solutions. Here it is with 2 solutions, and somehow or other there's one answer and another answer, but we don't know what the equation is that has those 2 answers. I know there's some of you clever kids in algebra can cook up an equation that has those 2 answers, but if you didn't know the answer, you wouldn't know how to write that equation. Now, very recently, within the last year or 2, I think, it sort of gradually became apparent, so it's not exactly a year or 2. First clues were a little older. We discovered there's another one. Mass is this time 1,860 approximately times in these units, which is something like 3,640 times as heavy as an electron. It's twice as heavy as a proton. Its charge is -1. And as far as we know, and we don't know much, first we know it doesn't interact strongly with doesn't interact strongly. Second, it behaves for the few experiments that it does behave. Everything can be understood so far by supposing it's another example of an object which obeys quantum electrodynamics perfectly like an electron with no error. But there is no, I can't write anything down. We haven't measured any magnetic moments or anything of any accuracy. It's just the beginning of understanding it. All right? Now, obviously, there's another one down here, huh? What you got to do is guess the rules to make these. This lecture is to try to tell you really what we don't understand about nature. We don't understand that at all. That makes it very interesting to be a theoretical physicist because you have these wonderful puzzles. Why does she repeat herself at that 206 times and then at 306.40 times or whatever it is? So, of course, you want me to write down the next one, but I have no more knowledge. At the present time, machines are being built to try to do experiments at higher energy. These are very high energies. And they are designed to look for another one, if there's another one down here, unless that's too far along. If it comes out that that one should be at 10,000, we're not going to find it. But if it's at 4,000, we might find it. Okay? All right, that's all. That's all I can say about those particles. Well, I say some more. The muon is in fact unstable. Otherwise, if it were stable, you would wonder why it isn't in atoms. Why you can't have a proton with a muon going around it. You can. There is such a thing as called a mu-mesic atom, in which the mu takes the place of an electron. And its energy levels are all computable and everything by the regular way they do for electrons. The numbers are much bigger. Instead of emitting light, this atom emits X-rays. But those are just numbers. Just shorter, higher frequencies. But the thing that's interesting is the muon, oh, by the way, like the electron has an antiparticle, which is a positron with charge 1. That's true of all these particles. Everybody going forward can go backwards in time, like the electron, when it turns around becomes a positron. The muon is negative. There's an anti-muon, which is positive, and presumably, yes, definitely, an anti-tau, which is positive. Anyway, the muon, which is written as mu minus by make it look nice, disintegrates, and it emits an electron. The muon sits here, and in about 2 millionths of a second, an electron comes shooting out, sometimes fast, sometimes slow. But the conservation of energy doesn't allow that. What really turns out, what careful experiments have shown, that there are 2 additional particles coming out, one of which is called an antineutrino E, and the other one a neutrino mu. So I have to tell you about neutrinos now. So I put those in the same list. We have a thing called a neutrino, or rather more precisely, the electron neutrino, neutrino E, which I write a nu E, because I'm getting tired of writing the word. That's just a symbol, neutrino E. It has a mass, as nearly as we can tell, a mass at rest of 0. It always seems to go along at the speed of light. Its charge is 0. So it doesn't interact with photons. And it doesn't interact with nuclei. If it never interacted with anything, we would never find it. But we did find it, so we have to learn something. Now it turns out there's another kind of a neutrino. There's another neutrino, the neutrino mu. You're not going to get tired of this because you're going to keep piling these things on until you're drugged. There's so many particles. I can't help it. I'm trying to tell you how horribly complex, apparently, the world really looks. And if I would give you the impression that since we solved 99% of the phenomena with electrons and photons, that the other 1% of the phenomena will take only 1% as many additional particles, it turns out to explain out, takes 10 times or 20 times this number of particles. Okay, this one also has a mass 0, although, of course, experiment can only measure to a certain accuracy, and I'm not sure. It might be as big as an electron or 2. And charge 0. The tau, huh? What about it? Have another one, huh? Neutrino for the tau. Well, I put it in parentheses, things that everybody thinks are there but have not had the slightest experimental information. They don't know whether there's one. And we certainly don't know whether the mass is 0. But we surely know it's neutral because we define it. Anyway, what's in parentheses are good guesses. Okay? Now, about these neutrinos. This process is understood this way. By saying a muon comes along here, this is the present view of it. Well, the first way. And it turns into a neutrino, the mu type. Okay? This is time going this way in space. And then, I think maybe this is in the way. You're clever. All right, now it's your way. Okay. And at the same time is produced an electron. Use the square chalk. I've got the round chalk. And an antineutrino. Let's put the arrows forward for the particles and backward for the antiparticles. So the antineutrino would be coming in this way. Okay? And the four of them come to a junction. And the theory is, present theory, which works nicely in predicting the rate, the properties of this reaction, is that this is done by a wiggly thing like a photon, eh? You would say, hey, it's like a photon. You put a photon in here and everything's all right. Except a photon can't change the charge of a particle. If the junction that photons satisfy go between mu and mu, not between mu and neutrino. So this has got to be a new particle. And furthermore, the fact that this goes as slowly as it does means that this particle is either coupled very, very weakly, and the coupling is extremely low, or that it's coupled with some more or less reasonable strength, but the mass of this is not zero like the photon. It turns out that the present theory, the one that works very well, made by Salam and Weinberg, is that this object, which goes back and forth here, which is the analog of the photon, has a very high mass. And so we start another list of particles. Let's see, I got all of them here. These are all the leptons. And the list goes on. We don't know where it goes, okay? Now I'm going to make another list. I guess the best place to make the other list is here, which are called bosons, or if you would like better, would be the interacting particles. They are, the first one, how do I do it? I give the name, the rest mass, and that's all I'm going to talk about here. The name is the first one, is the photon. Ah, yes, the photon. Its rest mass is 0. That means the mass that you put into the D function. Now this time we just have to put a different mass in for the D function, so the other particle is called a W. It's a horrible, we haven't got a good name for that, a W boson or something. Or W intermediate boson. Horrible name. Anyway, we ought to get a nice name for this one, which we haven't got. Maybe we should call it a Winon or something. And its mass is 53,000 expected. It's theoretically calculated by how much mass you have to put in here to make that rate right. Okay? And the coupling constants in here are about the same as the C over there. Like 3/8 of the C, or 1/4 of the C, or something like that. That is, the constant, though, it's just the same kind of coupling as it is to a photon, but the mass is much higher. And that makes that happen at a very slow rate, so it takes 2 millionths of a second, 2 1/millionths of a second. That's slow. Because, as you know, the frequencies we've been talking about have 10 millions and millions and millions, hundreds of millions and millions and millions per second. And this is only a million per second. So now this particle, in the particular case that I explained, if you imagine the particle went from here to here, has another property that I have to explain. It turns out that electric charge is never lost. In this particular experiment, the negative electric charge on the mu appears in the electron. But through the intermediary here it goes, and therefore this intermediate is electrically charged. So this thing is charged. So if we wrote here charge on our list, that's the wrong thing to do is when you get stuck with the wrong colors, then you have to keep remembering which hand has which. Okay, charge. And a photon doesn't interact with a photon, so it's got a charge of 0. The charge means how does a photon interact? And the answer is this has -1. Oh, I could use green. I can use green. -1 for the charge. But if this thing, the timing were reversed and this was a little lower than that, then you would see that this would have to, thinking of it going backwards, would have to have a positive charge. And it's the antiparticle, so that these W particles and their antiparticles are found both with -1 and +1. And in addition, it's been found that there is another W, which is neutral, and that they now form a nice little triplet, but the neutral one has a higher mass, probably, about 70,000 MeV. So we have here, in this theory, we have a thing that looks very, very similar to electrodynamics, in the sense that you make the same kind of diagram, in the sense that the coupling is the same order of magnitude. The only differences are a rule, two differences actually, a rule about the charges, about what you're allowed to couple to, and the fact that you use the mass in here. And one other technical detail, which is very interesting and has a good history, is that the coupling is not exactly the same as electrodynamics. I said in these problems that there are many polarization cases, and the couplings are 1s and -1s and sometimes 0. This one has half as many cases that are not 0. It has many zeros that a photon doesn't have. So it's coupled just a little differently. By a neutral one, that means that there'll be a process like this. For instance, it could be that a neutrino comes along and comes out as a neutrino and hits an electron. It goes out as an electron, and what happens is that one of these W bosons goes across, but this time it's a neutral one. That has been discovered within the last 4 or 5 years. It's called neutral currents for some horrible reason, but it caused a lot of excitement. So we now have this other particle, and what does it couple to? It couples to the neutrino and the mu. In other words, what we have to ask is now, what are the rules that tell you what kind of junctions it makes? Let's take the junctions with the W minus the -1. What pairs of particles can go? We already know a neutrino, even a square chalk, a neutrino mu and a mu is a pair of particles which can be on the junction of a W minus. So they belong together. And the other neutrino goes on a junction with the electron. That's why we named them that way. And it turns out, of course, that the tau, well, we're guessing on that. You see, we believe there must be one. It's some people who are very, very unbalanced who might suggest that that's the same one as this, but of course it's almost certainly a different one. Now, it also turns out that, for instance, a neutron, I'm talking about a strongly interacting particle, and I'm not supposed to be able to talk about that yet, I'll come to that in a minute, but a neutron disintegrates into a proton, an electron, and an antineutrino. And that means that something in the neutrons and protons, the quarks in fact, can also couple to the W. And so this list isn't quite finished, and I'll finish it later on in the lecture. These are the pairs of particles which couple to a W particle, and we just have to keep making lists of those. So for every particle, there's a sort of pair, friend, or something that you get from the ones that will couple with a W minus. So for the electron, there's this, and so it goes. It's a kind of, we don't understand any of this. We just find this out. And if you can figure out what this pattern is all about, then you will have contributed mightily to theoretical physics. That sums up all of the oh yes, one more important thing. Because this is charged, the photon couples to it, and there are diagrams which would be like this, that let's say like this is going across, so you can have another gamma ray coming out of here. Photon, it could be coupled to the W. And it also turns out that the theory is nice and neat if you allow a three junction like this, in which a W naught and a W plus and a W minus can all come together like that. So we have this and we have that. And the coupling constant is much the same. Therefore, the possibility exists that the idea that there's one kind of thing, a photon, and another kind of thing, 3W, is not right, that their four belong together somehow. And so the theory of Weinberg and Salam was to try to put the quantum electrodynamics with what's called the general weak interaction into one theory. And they did it. But if you just look at the result that they've written, you can see the glue. What I mean is it's not a nice job, okay? There is at the present time, it's very likely that it's interconnected. It's very clear that it's interconnected, that they're different aspects of the same thing. But at the present understanding of the knowledge, it's still not possible to see them very clearly as different objects of the same thing. You can make it look like the same thing, but you can see the seam between the things at the present time. It's not been smoothed out yet so that it becomes more beautiful and therefore probably more correct. But it is part of our theory today that these things belong together, and the reason they belong together in such a way that you can explain the connection between the coupling constant there and the coupling constant there, but that at the present time is not explained numerically. It just has to be measured. All right? That's the end of the weak interactions. We can breathe a sigh of relief. That's a limited number of particles. You're still within the possibility of keeping this in your head. But now, if we start with the protons and the neutrons and hit them together, we get this enormous number of particles. And the nice thing, if I would give these lecture perhaps 10 years ago, I would show you all these particles and make a long list of them. Then my list that's starting here would have 405 objects and so forth, and I'll tell you all about the properties of them. And then I would explain to you that I believe that none of them are fundamental in the sense that they're propagated by one of those nice little formulas where you put a mass in, because they all appear methods. Behavior is not like that. But in the meantime, in the 10 years, there's been developed a theory to explain this multitude by supposing that they're made out of other simpler things called quarks. Simpler in the sense that their propagators are simple functions where all you do is change the mass number. Okay? Now this theory, the theory of quarks, is what I must next describe and represents the theory of strong interactions. So let's use this. I see. There are more particles here, you see, but this board doesn't go into here. It goes under, and we can't see it. All right? Now, here's a new piece of paper on top of the other one, which are the strongly interacting particles, and I'm not going to list those, but the particles that they're made out of, which are called quarks. And we're going to make a list of the quarks. By the way, I have to say something. I've been leaving out polarization all the time, the polarization effect, and I'm not going to explain it now. But the electron has a different type of polarization than the photon. But all these particles in this list have that type. It's called spin a half, is the technical language for that kind of polarization. And the polarization of a photon is called spin 1, and the W also has spin 1. So this list corresponds to a kind of polarization of spin 1, and this list up here is spin a half, and as it turns out, the quarks are also spin a half. Same, all the same. Now, what are these quarks? What is the story? It turns out that a thing like the quarks come in there are many different quarks, just like there are many different leptons. And they have names, which are so bad, I'm going to give them letters instead of names. The names are up, down, strange, charm, beauty, and so on. Forget it. I prefer to call it U-type, D-type, S-type, C-type, and so on. So instead of giving them long names, we have the following kinds of quarks. A U-type, a D-type, an S-type, a C-type, a B-type, recently discovered. As we'll go along, we'll see there must be more, almost certainly. And the next letter that we're sure we're going to use when we find it is T. Some idiot named this charm particle, and this one beauty particle, and this one truth particle. And I can't stand it, so I have to my letters. These are then the quarks, And a proton, for example, is supposed to be made out of 2 U quarks and a D quark, 3 quarks inside, going around inside, 3 of them. 2 U's, U type, 1 D. The neutron is 2 D types and 1 U. All right? Now, of the 405 particles that I don't, well, 405, that's silly. The hundreds and hundreds of particles I was talking about before, they go into 2 classes. Those which, when they disintegrate, ultimately end up as a proton at the lowest energy, and that like a neutron does, for instance. And those are all objects which they're called baryons, and they have made out of 3 quarks. So some of these particles are made out of 3 quarks, a certain class. Another class is called mesons, of which pions are an example, are made out of a quark and an antiquark, and that's all we found. There ain't no 4 quark guys, or 2 quark guys, or even 1 quark guy. What? No 1 quark guy? That would mean that you can't get these quarks apart so you can see one. So far we have been unable to get these quarks apart so you can see one. You can hit those protons together as hard as you want, I mean as hard as we're able to, and the quarks never come out. All they do is move around, produce new pairs, and form new groups of 3s and particles and antiparticles. We can't get one separated. As soon as you get one separated, new pairs form in its neighborhood, particle, antiparticle, quark, antiquark, and they group up so that the quark, antiquark pairs are groups of 3. At any rate, the problem is, of course, what holds these quarks together inside a proton? And that force is large. That's what's strong. And that has to be done by another thing. Because the W's are coupled weak and the photons coupled weak, we need something that couples strong, and so I need another color for my chalk. Actually, I need 3 colors for my chalk. But I won't play with the colors right now. We have pictures of what the quarks do inside a proton. For instance, we would say, here's a proton. Let's say, just to make it nice. No, I better not do that. There's a U and a D quark going along. And then, from time to time, there's a kind of photon, but it's not a real photon. It's a different thing. It's called a gluon. You can imagine the level at which the physicists who can call that truth, they can't. Why is it called a glue? Because it's a particle like glue holding these things together, so it's a gluon. And the gluons go across and do various things in here, in a complete analogy to the way the electrons have photons go between them in an atom. And the gluons, then, are the next particle, and why the colors are shifting here, I'm not quite sure, but there are gluons. Okay? And they have a rest mass 0, like photon, and a 0 charge. But they couple strongly. I should put down here, couples to electron, or couples to charge. This one couples to those pairs, and this one couples to quarks. All right? The particle has the same polarization character as the photon, and so on. We just repeated, it just looks like I've just repeated quantum electrodynamics at a different scale with a stronger coupling. It's almost that. It's very close to that. It's almost exactly the same as electrodynamics on a different scale. I would now, I think, I don't know whether it's worth describing exactly the difference. It's rather curious and interesting. And I see I have a little time, so I'm going to do that. Before I do that, I have to finish with 2 remarks. One, we still have to ask, how does something like this happen? And the answer is, it's the quarks which are doing it. It's the U quark which can turn to a D quark, an electron and neutrino, so that inside here, I'm sorry, I got it backwards, D turns to a U, so that the DDU comes to the UUD. Surprising, but you only have to change one of them to do that, because they're moving around. So the D turns to U. So really, this is not the fundamental rule, but the fundamental, damn this, excuse me, square is that the D particle quark can turn into a U quark plus an electron plus a neutrino, and that's pictured by supposing that on that line that we can have the following diagram. Let's see, for some dumb reason, I've caught myself by making all the quarks blue and so on. It's terrible. I don't mean anything by these colors, but this is to remind you it's a quark. This is a D quark turning into a U quark with the emission of a green thing. A W meson, and then going into, I got myself into a pickle, okay? I should have anticipated that I'd get in this difficulty. The colors are just to keep track of different types of particles to help you a little bit. Electron, neutrino. Did I get the sign wrong? Yes, I got the sign wrong. It's neutrino, electron. Oh, yes, in this diagram, it's an antineutrino. That just means this arrow's up there. So that's all right. That's clever. You know how to turn that up there. And this is a quark coming in here. So we have to say, in addition, that the W particles couple not only to these pairs, but also to other pairs. And another pair, it involves the quarks. For example, here would be that it was the U quark coupling to the D. All right? This is not quite right. I'll put that there to remind you. Not quite right. This turns out that the C quark couples to the S. Not quite right. And nobody knows what the heck goes on beyond. What's not quite right is, well, I'll say one more thing. That tells us how the W's couple to the quarks almost. There's a slight fixing I have to do. Now, I also say that the photons couple to the quarks. We know that because we know the proton is electrically charged, and if it's going to be made out of quarks, then the quarks have to be electrically charged. Electrical charge means that the photon couples to it. Now, the electrical charge in this case has to add up to 1. The electrical charge in this case has to add up to 0. And the difference between these two must be 1 in order for that to work. Well, anyway, when you get finished, you find that the U's have to have a charge of plus 2/3. In other words, the charge of these particles goes like this. Plus 2/3 for the U, and minus 1/3 for the D, and minus 1/3 for the S, and plus 2/3 for the C, and let's see, the B is probably minus 1/3, but now we don't have too much, it's a good guess. So we haven't checked it, but the others are much better understood. And so, of course, the T is no doubt plus 2/3. But that's waiting to be found. Now, with regard to the mass, I cannot really give an answer. There's no way to define the mass because you can't get the particle out separate. And so we have technical arguments as to different ways of defining the mass. And everybody who defines the mass differently comes to different numbers here. So the numbers I'm going to write here are not accepted by everybody, and I won't accept them myself on another lecture when I redefine the way I define it. But for the main feature, I'll define it somehow, and with some particular way of defining it. This is 400, and this is 402. And this one is 500, roughly. And this one is 1800 or 1900. No, 1600. And this is 4500. When they get heavy, everybody agrees with the definition. But when they get light, the problem is the interaction energies are so big that you can't tell how much is due to mass and how much is due to coupling, and it's hard to define. The feature that we do know is that these two are the same, and this is more. And then when they get heavy, we got the numbers. Okay? These are lighter. So that the lightest of all of the strongly interacting particles are made of U and D quarks. Heavier ones involve sometimes an S. For many years, we thought the only kind of quarks we would have were the U, D, and S. By the way, the names of these different, when you want to say different kinds of quarks, you say different flavor quarks. The flavors that we had for many years are just these three. And in 1974, we found a particle called the psi meson, which could not be made out of these quarks. And there was also a very good theoretical argument that there had to be a fourth quark, having to do with that theory over there, the Weinberg and so on. And that's called the C quark. That one belongs with this number. And that checks out, and very, very recently, within a year or so ago, we found another funny particle, which means there has to be another clone, another flavor, all right? And so that, putting down these charge numbers and telling you what pairs couple to the W's and making all these pictures tells you almost the whole theory. The only thing that's not quite right is this. It turns out that the U, which I drew here, let's say the U is connected to a D. The U can also be connected to an S. And in fact, when the U goes through like this, it turns into a D or an S, one amplitude for a D, another amplitude for an S. So that what really happens here is a combination, some amplitude for D, and also some amplitude for S. And in here, it's a big amplitude for D and a small amplitude for S. Here it's the other way, a small amplitude for S and a big amplitude for S and a little amplitude for D. It is very likely that there's some amplitude for B in here also. In fact, there's pretty good evidence that there's a very small amplitude for B, so I could put that in, but it's not known very well. Why it chooses these proportions for those two amplitudes is utterly unknown. So I got everything out. It's a terrible mix-up. And you'd say, it's a hopeless mess physics has got itself worked into. It has always looked like this. It always looks like a horrible mess. But as we go along, we see patterns and we push them back down so that we put theories together. We combine this stuff and a certain clarity comes and it gets simpler. It's a lot better than the terrible mess I would have made with the 405 particles a few years ago. The thing that I would finish with, I think it's just as well that I finish a summary rather than to describe in more detail how these gluons work. It turns out there are 8 different kinds and so on. But I'm not going to complicate that. The thing that I would like to emphasize, though, is this. That all these theories are very similar to quantum electrodynamics. They have little tricklet changes, little small counting changes, but they're very similar. They all involve the interaction of a spin 1/2 type object with a boson of spin 1 type object. One case is obscure because it has a mass, but as a matter of fact, all the masses are obscure. So now let me talk now about the grand problem. The character of the theories, forget about the masses for a minute, the character of the theory certainly indicates, well, looks like they're the same somehow. They're very, very similar. But remember something. We have not yet checked quantitatively this theory with the gluons. It might be wrong. We have only got a few experiments to check the W boson. That might be wrong. On the other hand, why does it look like it could be the same thing repeated? There's several possibilities. One, it's a limited imagination of man. When he sees a certain theory and he sees a new phenomenon, he tries to fit it with that theory, and until he's made enough experiments, he doesn't know that it doesn't work. And so when he gives a lecture in 1979 in New Zealand, he thinks it works, and he says this is the way it works, and look how wonderfully similar they are. It's not because they're similar really, it's because all we've been able to think of is the same damn thing over and over again. Another possibility is that, as a matter of fact, it is the same damn thing over and over again, and that nature has only one way to do it, so to speak, and she keeps repeating her story from time to time. And there's a third possibility. And that is, they look very similar because they're different aspects of the same thing, that there's some larger picture from which is to be understood that the thing breaks down into what looks like different things, but they're different cases of the same thing, not different cases. Well, it's very hard since I haven't got the right theory. I can't exactly explain myself, but I'll try the best to say that there is one large object which has supposedly a first approximation, well, has a whole lot of fingers, and these are the different fingers. But they all belong on the same hand. They all got the same characteristics. And the reason, therefore, that they repeat the pattern of having the same kind of interacting particles and the same kind of coupled particles is that they have the same, they really come from the same thing. And so there are many people, of course, working, trying to get the grand picture, which puts all this together in one super-duper model. And have promised you in these lectures not to talk about speculations, but things that have a reasonable experimental check. None of the speculators agree with any of the other speculators as to what the grand picture is. Throughout this entire story, however, there remains one unsatisfactory feature, and that is the mass numbers. There is no really satisfactory theory of the origin of these masses. We can write this stuff down and we see the pattern, but we don't know where these numbers come from. There are theories which suppose that there's still another kind of particle which generates mass. It has a different kind of polarization. You'll like that one. It has only one kind of polarization, not two like the electron or photon. It's called spin zero. There's proposals that there are spin zero particles in the world and various theories to show how they might produce numbers of masses, but not one of those theories really produces the numbers that we see in a satisfactory way. It just says maybe they will come out, maybe it'll do this, and maybe it'll do that, and the more you look at it, the less it turns out to be the case that it really does what you want it to do. So we do not have any understanding of the masses, and I believe that from the fundamental point of view, that is probably a very interesting and serious problem. The particular work that I work on is this. It turns out that this theory of the gluons and the quarks is a very definite, precise theory. It has only one constant in it plus those masses, the coupling constant. The coupling constant, however, is large. And the method that we use to make calculations for electrodynamics that were successful, easy calculations, in which we approximate by first finding out the diagram with the least number of these things, and then more and more, because the more you put in, the smaller the contribution because of the 1%. When the coupling is big, the diagrams with many of these and the diagrams with few of them are all important. And the problem is to add everything together in some other order, not just by starting out with no gluons and then putting in one gluon. It'll never work. It is true that at very high energy, in very high energy collisions, it does appear as if it is right to start with an approximation in which you have the minimum number of gluons and make a correction for one more gluon and so on. And in those experiments, you can calculate or predict certain trends which ought to occur, and those trends do occur in experiment, which is the only evidence we have that this theory is on the right track. Because at the present time, although we have a definite theory, we have a situation that's never before existed in the history of physics, we haven't been able to calculate anything from the theory. Therefore, we can't compare it to experiment. It isn't that there aren't experiments. There are hundreds of experiments with the strongly interacting particle, all kinds of experimental accuracy and detail. It's just that we can't calculate anything with this theory, and that's not because the theory is indefinite. We have a definite proposal and a definite result. Let's compare the theory to experiment, the usual thing you're supposed to do. It tells you in books. Science is very simple. You make a theory, compare it to experiment, and if the theory doesn't work, you throw it away. Then make a new theory, compare it to experiment, throw it away. Oh, here's a theory, compare it to experiment. We don't know how. So we're boxed temporarily in making a method of calculation to compare it to experiment. So I'm trying, amongst other people, also trying to figure out how to improve our methods of analysis so we can make a reasonable mathematical analysis of that theory. In all this, I didn't discuss gravitation. The reason I didn't discuss gravitation is this. The gravitational influence between objects is extremely tiny. So tiny it holds you in your seats. Wait. Between microscopic particles, between electrons, for example, or between two muons or photons and so on, the gravitational force is very small. As you know, the force between two electrons varies inversely as the square of the distance and the product of the charges. That's electric force. And this whole gravitational force is the product of the masses and inversely as the square of the distance. And one varies the same way as the other. And one is very much smaller than the other. In fact, the gravitational force, if you don't like big numbers before, you're going to get them now, is weaker than the electrical force between two electrons by one followed by, the factor is 1 followed by 40 zeros, and 41 zeros perhaps. And that's so tiny that you'd say, oh, I will never see gravity at all. The difference is that gravities like attract, whereas in electricity likes repel and so forth. So when you have a lot of objects You have a large number of particles. The gravity keeps adding and adding and adding and adding, but the electricity cancels the plus and minuses. So what we end up is that all the electrical forces, which are so enormous between the electrons and the protons, simply hold the electrons and the protons in a terribly intimate mixture of matter. Matter is a fine mixture of plus and minus charges, so fine they all cancel each other out, so on a large distance there's not much left. But gravity keeps on adding and adding and adding, and so at last, when we get to these ponderously large masses that we are, we begin to measure the effect of gravity on planets, on ourselves, and so on. Because of this, from an experimental point of view, it is impossible at the present time to get any experiment in which any quantum question about gravity is involved. In order to produce a gravitational influence, you have to have so much matter, so many gravitons, if there were any, that the quantum approximation is unnecessary. Of course, it is not possible in the world to have this framework of amplitudes on part of the world and not the rest of the world. So it is not a satisfactory situation to say that when the matter is big enough, I'm going to make this approximation and forget it. So the question does come up, is there a quantum picture for gravity? Yes, there is a quantum picture for gravity, and it's the same kind of business. A thing goes across. We'd have to have a different color chalk for that, and it's called a graviton, and it would appear in this list, except its polarization quality is a little bit different than a photon. It's called spin 2. And the gravitons go back. This picture has it that the gravitons go back and forth. But in any practical situation, there are so many of them that we can use the field theory without thinking about the quantum theory. It's also true that the quantum theory of gravity has infinities like the electromagnetic theory, but they seem to be a little bit more difficult to get rid of. Anyway, that summarizes all that is known by man as far as I knew when I left Caltech before I started to give these lectures. It is always possible that somebody has figured something out in the meantime, or measured something in the meantime, that I haven't yet heard about down here in the Southern Hemisphere, which I am enjoying, by the way, very much. And I hope you've enjoyed this talk, and I'm open to situation to lecture to questions. I guess I'll let you ask me questions. I'm done with this lecture.
Could you tell us something about a possible relationship between quantum electrodynamics and gravitation?
No. I don't see it. They've got a long history. You see, at the time when Einstein worked out his theory of gravitation, there's not a quantum theory. It's what's called the classical approximation of field theory. The other important theory in the world at that time was the theory of electrodynamics, also a field theory, not with the amplitude. And so at that time, the problem was to put always the problem of physics, of put everything together. So at that time, the problem was to put electrodynamics and gravity together. All right? But the electrodynamics and the gravity were both wrong. They should have been quantum theory. And in addition, we find many other things in the meantime. The problem is to put everything together. There's nothing special about trying to put electrodynamics and gravity together, any better than putting quark theory and gravity together, or what? The only one that I know that there's some real advance in understanding how to go together so far is this W meson and photon. That's electrodynamics and weak interaction. The problem is to put them all together, ultimately, and that is the problem I was discussing, and how far we've gotten. It is not very far, but I would not choose, for historical reasons, to think it's more important to put gravity with electricity than to put any other combination together.
Do the correction factors which you mentioned at the beginning of the lecture, and which operate at very short distances, imply that space is quantized?
Yes, that leads to a lot of possibilities. It could be that space is quantized and so on and so on, but all the experiments, you see, are in agreement with supposing that distance is virtually zero. We don't know where it is. It's certainly way beyond the experimental range, which corresponds to 10 to the minus 15 centimeters. It doesn't mean that it could be quantized at 10 to the minus 20 centimeters. But this is an interesting feature. I forget the question. I forgot to repeat the question. The interesting feature is that when people have tried to make a theory that space is quantized, they get into difficulties. Nobody has made up a nice theory that space is quantized that agrees with observation. It's not so easy to make up these theories. What one does all the time is fall into one or another pit. Either you come out that the sum of the probabilities is not 100 of all events is not 100%, or it turns out that you can get states of more and more negative energy. That would be very useful, because what we could do is we could take some object and send it into an energy is conserved. The total energy in the world is conserved. But suppose I have this object, I can put it into a place where it has negative energy and get some positive out, because I start, say, with 0. You want more? Put it in a more negative energy. Get more out. So it's obviously an unstable universe if we can have states of negative energy of ever larger possibility. These are the kind of things that happen to a poor individual who tries to make up a theory with some arbitrary thing like a lattice in space or something. He gets into that type of difficulty. There are very few self-consistent theories, and that's the only ones we really know how to write are ones in which we suppose point like space, time, and these propagators with some masses in them, and one or another of the various kinds of polarization systems, either what we call spin 0, spin a half. Spin 0, we don't have knowledge that there are any fundamental particles. Spin a half, all these. Spin 1, the photon W and the gluon. Spin 2 is, there is possibility in principle of spin 3 halves, but we know of no fundamental particle with that. Spin 2 is the graviton and so on. By the way, there are, it's not the answer to your question, I finished your question, but I must remark that there are many interesting theories which try to put the gravity, electrodynamics, but they always invent a lot new other particles that have to go along with it, such as spin 3 half fundamental particles and so on. But at the present time, the biggest of them is not able to include the particles we do find and invents a lot of particles we don't find.
Why have gluons not been observed yet?
I didn't completely describe the gluon theory, and don't be afraid. I'm not going to. But just like there were 3 of these coming together, so in the gluon theory there's also 3 of these coming together. I say that not in answer to your question, but to make something I had forgotten to say. This is the place that smokes out as clearly as possible that we don't know how to calculate the most simple thing in this theory. The simplest thing would be, what is the interaction energy between a pair of quarks as you pull them further and further apart? In the case of electricity, the energy it takes to pull a pair of particles apart, the force it takes, goes down fast enough that it takes a certain amount of work and you can get them apart. The question is whether in this theory, as you pull the quarks apart, the force decreases fast enough so that you can do it. If the force stayed constant, no matter how far you pulled them, you could never get them apart. It is believed, hoped is a better word, that if we really could analyze this thing, that would turn out to be the case. Now, the first thing you'd try is to suppose it's the other way, and you find, no, there are terms in here that look funny. It's hard to calculate. It's not so easy to show that the force goes to 0 when they get far enough apart. Therefore, it could be that the force doesn't go to 0 as they get far enough apart. All I'm saying is, the theory is complicated enough that we at the moment can't tell. That's why I'm so anxious to figure out how to calculate something. Even the simplest qualitative question as to whether the force increases or falls with distance fast enough or not is not at the present time been analyzed yet from this theory. It's something I think that theoretical physicists should be ashamed of. When you think of how much money is put into doing these experiments and the big apparatus and so forth, and here we just sit around with a beautiful theory and mumble about it and can't calculate any numbers. We shouldn't get our salaries, I think. Or maybe they should be raised. We'd work faster. I don't know.
I'm still worried. Isn't your theory really still a wave theory?
He's worrying about the wave-particle duality that I described in lectures 1 and 2, and says, effectively, that I convinced him that it's particles in lecture 1, and then I did a lot of calculations of amplitudes, which seemed to him to be nothing but the analysis of waves, which is the same kind of calculations that we do for waves, and why don't I admit that it's a wave theory that I'm really using? And I tried to explain that in two features about it. I chose to talk about amplitude to go from one place to another directly as a given answer. It is also possible to analyze that by saying, and I did say this, that you could think about the amplitude to go from here to here, and then the amplitude to go from there to there. And in that method of analysis, you can write it as differential equations, if you want, a mathematical form that's the same mathematically when you're dealing with a single photon as the Maxwell equations for the wave. There are two differences. First, let's take the case of a single photon, in which it turns out that the calculation of my amplitudes is precisely the same mathematically as the calculation of the electric field according to Maxwell's equations, which is a wave theory. The difference is in the interpretation of the answer. The square of the electric field, for example, in that theory, is supposed to be the energy density in space. The square of the wave function, although mathematically determined by exactly the same equation, is the probability of finding a photon. So another way to answer it for the case of single photons is to say this. We calculate as if the light is a wave, but we interpret the intensity of the wave, what used to be called the energy density of the wave, not as the intensity of the light, but as the probability of finding a photon. It's that duality of interpretation which produces the difficulty, because if this were really a wave coming in, we couldn't understand how the photon counter would acquire enough energy to go off sometimes immediately when you turn it on. Nor, you see, if, for example, a wave is shining on a surface, a metal surface, we find the following, that if you shine light on a surface and you shine a lot of light, a lot of electrons come out, with each one with a certain energy. If you decrease the intensity of the light, that is, weaken the waves, you would have thought that the wave would kick the electron less, and so you get a lot of electrons out with less energy. That's not what happens. You get fewer electrons with the same energy. And when your wave has gotten so weak it could hardly shake an electron at all, you still see an electron come out with a full jab of energy only once in a great while. And that paradox has to be described by not changing. It would be a miracle if the mathematics would change, because nobody was going to play around with this wave theory that long if it didn't agree with experiment. So there's something right about those equations, the behavior of the amplitudes they were describing. It wasn't interpreted right. First. Second, I've talked about, not sufficiently, and this is a difficulty that many people, I answered somebody else this way, have with this wave particle business and this quantum mechanics, is that the first thing to do when you're giving a lecture is to take the simplest example. And the simplest example is always one particle. But suppose the same way we take two particles, two photons. I've talked about amplitudes for two photons to come to 2 points. Now the amplitude, if you thought of it as a differential equation, is an amplitude defined. Let's take electrons, or they have 2 electrons. The amplitude defined, if you understand it, I'm writing it mathematically because you're asking me a mathematical question. The amplitude defined one particle at a position in space I'll call x1. It's a vector position. It's a three-dimensional. And the other particle at a position x2, that's a function of time. When there's only one particle, it's a function of x, the position of that one particle, and time. Now, it's characteristic of electric fields, of fields in general, that they're functions of position and time. But when there are 2 electrons or more, the amplitude is the amplitude to find, just like the probability, to find 2 electrons, one here, one there, at the time t. This kind of a function is not a wave. It's a function of 2 positions in space and time. That's a new one. When there's only one particle, it's a function of one position in time, then it's like a wave. When there's several particles, the functions or the amplitudes we have to talk about are functions of several positions in space and time. And that's not a wave in the normal sense. So knowing that that's the case, I emphasize with a slightly different attitude, and I know I'm talking about waves if I was talking about one particle, but not if I'm talking about more. Okay?
You haven't told us very much about quarks and gluons.
It's true that I left out an important thing because of the shortage of time. To make a complete description of these things, I'll just say it, that the quarks of each flavor, like the U-type quark, really comes in 3 varieties. we call them colors, a red one, a green one, and a blue one. They have all the properties the same. They're all the same charge and mass. They're all exactly the same. It's just red, green, and blue. That's three different kinds. And the three quarks that form a proton as one red one, one green one, and one blue one always. Always the three different ones. The way the gluons work, just to make a quick thing, I'll be done in a minute. Let's suppose that now I'm going to change the color system and draw pictures with the right colors for the quarks, you see, red, green, or blue. So if I would say I have a green D quark, okay, and it could turn into a red U quark, for instance. And in doing so, it emits a gluon, which I've been drawing as orange, but it's a special kind of a gluon. It's a gluon which has if it went out, a green in it and anti-red. It's like, if to draw it correctly, I should draw colors for it, green and red going the other way. And what happens is if you draw these things, the colors always check out. For example, this could connect to a red, let's say it could be a connection between another quark. Let's say a red D would then turn into a green U or something like that, or a green S or something. No, I'm sorry, you don't change the type. I'm sorry. It has to, with the gluons, you keep the flavor fixed. So this is, say, a U and a D interacting. But the colors get exchanged. What the gluons do is they carry colors back and forth. And the reason why there's a 3 thing is that gluons couple to any kind of color business. So if you have a gluon, which is the green anti-red one, say, you can connect it to an anti-green blue one, for instance. If you emitted a anti-red blue one. So the quarks, the gluons, have colors. And since there are 3 colors, and you have every kind of combination, you would expect 3 times 3 or 9 different kinds of gluons. Actually, there are only 8 different kinds of color combinations. The particular combination, which has an equal amplitude to be red anti-red, blue anti-blue, and green anti-green, doesn't exist. And that describes the theory much more completely than I did before. With that game with the colors, we have a pretty good understanding of why it's only that 3 particles come together, or a quark and anti-quark. Only colorless combinations which are symmetrical in color, that don't have any bias in color, are the low energy states. Any other states presumably take infinite energy to make or something. Can't be made. So you need a red, green, and a blue. You need 3. Okay? Yes. Thank you all very much, and thank Rob for the opportunity to give these lectures. I've often thought I've never been able to figure out how to explain electrodynamics and quantum electrodynamics, and I thought that this was an opportunity to try on a poor, unhappy audience to see whether it was at all possible to explain this subject in a finite number of lectures. And I chose to come to a part of the world as far distant as possible from my home, so that if I were not quite successful, I wouldn't have to suffer so directly. Thank you very much for the opportunity and for your patience in coming all the time to the lectures. Thank you.